Momentum and impulse. We have two curves right in front of us, A and B. They're identical, as you can clearly see. They both have a mass of 2000 kgs. I want you to think of something. Let's say you had to stand in the path of one between the two cars and push the car until it comes to a complete stop. For car A, it is moving with a velocity of 10 meters per second. And then car B is moving with a velocity of 20 meters per second. If you had to push one between the two cars to a complete stop, which car would you choose? They have the same mass. They differ in velocity. Car A has a velocity of 10 meters per second, while car B has a velocity of 20 meters per second. Which car would it be easier to stop between the two? Obviously, it is going to be car A because it has a speed of 10 meters per second. It has less speed compared to car B, right? So it would be easier to stop. Here we don't have identical cars anymore. We have car A with a mass of 1500 kgs and car B with a mass of 2000 kgs. If car A is moving with a velocity of 10 meters per second and car B is also moving at a velocity of 10 meters per second, then which car would be easier to stop between the two cars? It should be easy to see that car A would be easier to stop between the two cars, right? Even though they're moving at the same speed, car A has less mass, so it would be easier to stop because of the mass. If you ask a grade 10 learner these questions, they will probably get them right, even though they don't know the physics behind it. But in our case, we have to find out why that is the case. So let's go ahead and do that. Momentum is the product of an object's mass and its velocity. From the previous video, I'm sure you have seen that when you change the mass, something happens to the momentum. And when you change the velocity, the momentum also changes. So the formula we have for momentum is P is equals to M multiplied by V, where P is equals to the momentum. So P is the symbol we use for momentum. The SI unit is in kg meters per second. That will make sense very soon. P is equals to M multiplied by V. P is the momentum and M is the mass. In chemistry, the mass is in grams. In physics, the mass is in kg. Okay, so the mass is in kg. If you find that you're given the mass of an object in grams, you obviously have to convert it to kgs by dividing by 1000. That's how it works. And then V is the velocity in meters per second. Nothing new there whatsoever. V is the velocity in meters per second. So momentum is the product of an object's mass and velocity. Mass is a scalar and the velocity is a vector. So the product of a scalar and a vector will give you a vector. So momentum is a vector. We need to put into consideration the direction when we are solving our problems. So let's just recap. Momentum is the product of an object's mass and its velocity. P is the momentum in kg meters per second, M is the mass in kgs, and V is the velocity in meters per second. Let's take a look at these two examples. But before we look at the examples, there are some guidelines that we should always follow. The first one being that always convert the mass to kgs and velocity to meters per second. Like I've said, right? We need to convert the mass to kgs and the velocity to meters per second. That is bullet point number 1. And bullet point number 2, remember to indicate direction using a plus sign and negative sign. This is when you substitute, okay? And then the third bullet point, provide your answer with the unit and direction. we need to include the direction because momentum is a vector, like I have said. Okay, so that is the third bullet point. The fourth bullet point, if you obtain a negative answer for a vector, it only means that the direction is opposite to what you chose as positive. That's all it means, nothing more than that. So there we go. Those are the things we need to remember as we calculate. Okay, let's take a look at the first question. A dog with mass 30 kgs runs at a velocity of 45 meters per second. Calculate the momentum of the dog. Well, this is pretty much straightforward. The mass is in kgs, so no problem there whatsoever. And the velocity is in meters per second. So we're going to write our formula. P is equals to M multiplied by V. And then we're going to substitute. P is equals to the mass, which is 30, multiplied by the velocity, which is 45. This is equals to 1,350, the magnitude. We include the units, which is kg meters per second, and lastly, we include the direction. We need to give the magnitude, the SI unit, and the direction. The direction is in the direction of the motion, okay? But usually, when we solve problems, you're going to be given whether it's to the left, to the right, west, east, and so on. So that is the first question. No trickery there whatsoever. You should be able to make sense of that. And then the second question, a car is traveling at 60 kilometers per hour. If the mass of the car is 250 kgs, calculate the momentum of the car. Well, there's a slight problem. We have the mass, which is 250 kgs. That's okay, right? There's no problem there whatsoever. The problem arises with the speed or the velocity. It is 60 kilometers per hour. And we need our velocity to be in meters per second, not kilometers per hour. So we need to convert that 60 kilometers per hour to meters per second. How do we do that? We divide by 3.6. If you divide by 3.6, you're going to get 16.66666. 6 recurring, right? So, right, you just have to, if your velocity is in kilometers per hour, you divide by 3.6 to convert it to meters per second. That's all you have to do, right? Not only in this problem, even if you come across a different problem, if the velocity is in kilometers per hour, you just divide it by 3.6 to convert it to meters per second. The mass is 250. There is no problem there, okay? We multiply the two numbers and we have a momentum of 4,166.67 kgs meters per second in the direction of the motion. There we go. Momentum depends on mass and velocity. So if the velocity of an object can change, then the momentum can also change. Change in momentum. Let's go ahead and take a look at that. So delta P is equals to P final minus P initial. P final being the final momentum and P initial being the initial momentum. The SI unit is still the same because it's just momentum minus momentum, right? The SI unit is still kg meters per second. We need to remember that initial momentum, final momentum, and change in momentum are vector quantities. Direction is very important and should be included in your substitutions. So when you're calculating either the change in momentum, the final momentum, or the initial momentum, it's important to remember that these are vector quantities. We need to account for the direction. Change in momentum is related to Newton's second law. Let me show you why that is the case, okay? Newton's second law. We know that F net is equals to ma. So we have F net being equals to ma. From vertical projectile motion, one of the equations we have is Vf is equals to Vi plus A multiplied by change in t. If we take a look at this equation and make a the subject of the formula, we're going to have Vf minus Vi being equals to A multiplied by delta T. Let's go ahead and divide both sides by delta T. If we do that, we're going to have Vf minus Vi divided by delta T being equals to A. What we want to do now is to substitute Vf minus Vi divided by delta T in place of A in F net is equals to MA. If we go ahead and do that, we're going to have F net being equals to M. In place of A, we have Vf minus Vi, everything divided by delta T. If we multiply out, we're going to have the mass multiplied by Vf minus the mass multiplied by Vi, everything divided by delta T. What is mass multiplied by velocity? That is momentum, right? So we have momentum final minus momentum initial divided by the change in time. So F net is just change in momentum divided by change in time. Formally, we say that the net resultant force acting on an object is equal to the object's rate of change of momentum. This right here is very important. We're going to use it at a later stage for sure. Let's give these two examples a try and get familiar with the concepts. A tennis player serves a tennis ball towards his opponent. The ball moves through the air with a momentum of 11 kg meters per second east, right? It is a vector, so the magnitude and the direction. The opponent hits the ball back in the opposite direction, and the momentum of the ball changes to 8 kg meters per second west, right? And then the question, calculate the change in momentum of the tennis ball. So let's go ahead and take a look. We have the initial momentum. The initial momentum is 11 kg meters per second east, right? So in questions like this, we need to decide on a direction we take in as positive and a direction we take in as negative. Same way we do in vertical projectile motion. Well, let's take direction to the east as positive. If we take direction to the east as positive, then the initial momentum is 11 kg meters per second. And then the final momentum will be 8 kg meters per second to the west. So when we substitute that, we're supposed to put a minus sign because it is to the west and we're taking direction to the east as positive. So momentum final is 8 kg meters per second to the west. What are we interested in? We're interested in the change in momentum. We know fully well that this is equals to momentum final minus momentum initial. So the final momentum is 8 kg meters per second to the west. So that will be minus 8. This is because we're taking direction to the east as positive. So we have minus 8 minus the initial momentum, which is positive 11 kg meters per second to the east. So what is minus 8 minus 11? That is minus 19, right? So this is just 19 kg meters per second to the west, right? So this is our final answer. We have the magnitude and the direction. So here we had a negative answer, but we know that the negative is just an indication of the direction. So we need to code again without a negative sign and then give the direction, just like I'm doing right here. So it is 19 kg meters per second to the west. So there we go. That is how we can solve a problem like that. The second problem, an arrow is shot with an initial momentum of 20 kg meters per second towards the target. It penetrates the target and its momentum changes by 4 kg meters per second. Okay, in the opposite direction, right? Calculate the final momentum of the arrow. Okay, so we are given the initial momentum. Again, let's take, okay, here we don't have east or west, right? We have towards and away. So let's take towards as positive and away, or in the opposite direction, as negative. So an arrow is shot with an initial momentum of 20 kg meters per second. So the initial momentum is 20, and then it penetrates the target and its momentum changes by 4 kg. So we have the change in momentum, which is equals to 4 kg meters per second in the opposite direction. So the change in momentum is minus 4. We are interested in the final momentum. So we're still going to use the same equation. We're going to have the change in momentum being equals to momentum final minus momentum initial. We have the change in momentum, that is minus 4. We have the final momentum. Well, we don't. That's what we're interested in. So momentum final, and then minus the initial momentum, which is just 20, because it is in the direction we're taking as positive. So minus 4 plus 20, because we're going to add 20 on both sides, right, to make the final momentum decided on the formula. We're going to have 16 being equals to the final momentum. So the final momentum is just equals to 16 kgs meters per second towards the target. It's positive, so it must be towards the target. Let's talk about impulse. Impulse is derived from Newton's second law. F net is equals to ma, and in place of a, you substitute Vf minus Vi divided by the change in time. Okay, so from Newton's second law, we have the resultant force, or the net force, being equals to the change in momentum divided by the change in time, of which we know that the change in momentum is the mass multiplied by the final velocity minus the mass multiplied by the initial velocity, everything divided by the change in time. Obviously, we can cross multiply. If we cross multiply, we get the resultant force multiplied by the change in time being equals to the change in momentum. So the resultant force multiplied by the change in time is what we call the impulse of a force, right? Of which the impulse of a force is equals to the object's change in momentum, right? Of which the force is applied on. We need to remember this. The impulse of a force is equals to the change in momentum of an object. When a force is applied to an object for a short space of time, it will bring about a change in the momentum of the object. Let's dive deep into impulse by studying with the definition. So the impulse is the product of the force applied and the contact time. That is the impulse. The impulse is the product of the force applied and the contact time. So since force is a vector quantity, impulse is also a vector quantity, and its direction is the same as the direction of the force, right? You will see this in detail when we start solving some problems. Like we've said before, impulse is equals to the change in momentum. Impulse is very important when it comes to safety of vehicles. Let's take a look at that. So impulse and safety considerations. To avoid more serious injuries, if an object can be stopped over a long period of time, a smaller force will be required and thus less damage caused. Because we're saying that F net is equals to the change in momentum divided by the change in time. So if we increase the contact time, F net is going to decrease, right? They're inversely proportional to each other. Okay, so this occurs in the cases of airbags, seat belts, and arrestor belts for trucks and planes. We have a ball moving at a velocity of 30 meters per second. It has a mass of 0.5 kilograms. After it gets hits, it moves to the opposite direction with a velocity of 40 meters per second. The first question is saying, let's find the impulse applied by the bat. And then the second question, determine the force applied by the bat to the ball if they're in contact for 0.1 seconds. Take original direction as positive. So let me show you how we can answer the first question. We know fully well that the impulse is equals to the final momentum minus the initial momentum, which is just mv final minus mv initial. We know that the mass of the object is 0.5 kgs. There we go. And the final velocity is 40 meters per second in the opposite direction, right? So that is going to have a minus sign. So that is why we have 0.5 multiplied by minus 40. And then the mass of the object still 0.5, and its initial velocity is 30 meters per second in the original direction, of which we are taking as positive. If you put that in your calculator, you should get minus 35 kgs meters per second. This is to the opposite direction. So now that we have the impulse, it should be quite easy to calculate the resultant force, because we know that the resultant force is the impulse divided by the change in time. So let's go ahead and see how that will look like. As you can clearly see, the impulse divided by the change in time. So we have minus 35 divided by 0.1, which is minus 350 newtons. Explain the meaning of the term elastic collision. So an elastic collision is a collision in which both the total momentum and the total kinetic energy are conserved. A collision in which both the total momentum and total kinetic energy are conserved. Not so complicated. So that is 4.1. Let's go ahead and take a look at 4.2. So in 4.2, we are asked to calculate the velocity Vy for 5 marks. So let's go ahead and take a look at our question statement and make sense of the situation. So a ball X of mass 10 kgs is moving eastwards with a velocity of 2 meters per second. It collides elastically with another ball Y of mass 2 kg, which was moving with an unknown velocity Vy. So this is the unknown velocity Vy we're interested in, and that is in diagram A. Okay, we can see ball X with a velocity of 2 meters per second and ball Y with unknown velocity Vy. Immediately after the collision, ball X comes to rest and ball Y moves eastward with a kinetic energy of 36 joules. So X is now at rest and ball Y has a kinetic energy of 36 joules. So based on the variables we have here, there's two ways I'm thinking of right now that we can use to find Vy. Okay, we can use the fact that the sum of the kinetic energy before the collision will be equals to the sum of the kinetic energy after the collision, because the collision is elastic. Or we can use the conservation of linear momentum, because if the collision is elastic, then the momentum will be also conserved. Okay, but if we use the conservation of linear momentum, we have to convert these 36 joules to velocity. Okay, but if we use the conservation of kinetic energy in an elastic collision, we would have to convert these 2 meters per second to kinetic energy. So whatever way we use, we must get to the same answer. Let's just go ahead and use both and see what happens. So if we use the kinetic energy, because our collision is elastic, we can say that the sum of the kinetic energy before the collision should be equal to the sum of the kinetic energy after the collision. Okay, so like I've said previously, our first statement should be that the kinetic energy is equal to F mv squared. Okay, so now let's go ahead and calculate the sum of the kinetic energy before the collision. For ball X, as we can see on the diagram, we're gonna have F. The mass for ball X is 10 kgs, so we have 10 kgs multiplied by 2 squared, that is its velocity, plus the kinetic energy of ball Y. So we're gonna have F, the mass of ball Y is 2 kgs multiplied by Vy squared. Vy is what we're interested in. Okay, and then after the collision, ball X comes to rest, so the kinetic energy is 0 at that point. If the velocity is 0, the kinetic energy is going to be 0. So we have 0 plus the kinetic energy of ball Y. It is already given to us as 36 joules. So we can just go ahead and write that down. Okay, so let's go ahead and have a look. 2 squared, that's 4. 4 multiplied by 10, 40 divided by 2, or multiplied by a half, that is 20. So we have 20 half multiplied by 2, that will be 1. So plus Vy squared is equals to 36. So Vy squared is equals to 36 minus 20, that is 16. So Vy squared is equals to 16. So Vy is equals to plus or minus 4. But let's take a look at our situation and see what makes sense. Ball Y, initially it's moving to the west. Okay, we can make that conclusion because ball X comes to a stop after colliding with ball Y. So the Vy is 4 meters per second to the west. This is if we use the fact that the kinetic energy is conserved. We're going to have an answer of 4 meters per second to the west. So now let's go ahead and use the fact that momentum is conserved and see what answer we're going to get to. So let me get rid of all of this. So what am I proposing now? I'm proposing that we can easily say that the sum of the momentum before the collision should be equal to the sum of the momentum after the collision. Our objects are separate before the collision and still separate after the collision. So we're going to have mx v initial plus my v initial being equals to mx v final plus my v final. Okay, obviously we have the mass mx and my, okay, together with mx and my after the collision. The mass doesn't change. We have vi for our ball X before the collision. Vi for our ball Y is what we are interested in. Okay, that is our unknown variable. And then after the collision, we have Vf for our ball X. It comes to a stop, 0 meters per second. But we don't have Vf for our ball Y after the collision. We have the kinetic energy, so we can convert that kinetic energy to velocity. Okay, we know fully well that Ek is equal to half mv squared. The kinetic energy is 36 joules. This will be equal to half. The mass for ball Y is 2 kgs v squared. So 36 is equal to a half multiplied by 2, that is 1. So 36 is equal to v squared. So plus or minus 6 is equal to v. It is moving to the east. So we're going to have 6 meters per second east being equals to v. So there we go. We have the velocity for our ball y. So we can go ahead and substitute. We are taking direction to the east as positive, right? We're going to do that for all the questions that we are going to answer, unless the question says otherwise. Okay, so mx, that is 10. So we have 10 multiplied by vi, which is 2, plus my, that is 2. And then this vy is what we're interested in. Mx, that is 10. Final velocity is 0, plus the mass of ball y, which is 2 kgs. And then vf for ball y, we just calculated it. It is 6 meters per second to the east, and hence we're substituting it with a positive sign. So 10 multiplied by 2, that is 20. So we have 20 plus 2 vy being equals to 10 multiplied by 0, it's 0. 2 multiplied by 6, that is 12. So we're gonna have 2 vy being equals to 12 minus 20, that is minus 8. So vy is equals to minus 4, which is just 4 meters per second to the west. So there we go. We get to the same answer if we use the fact that momentum is conserved, or if we use the fact that kinetic energy is conserved. There we go. There's probably more options. There's probably another way you can use to answer this question. Okay, so that is 4.2. Let's take a look at 4.3. So in 4.3, the balls were in contact with each other for 0.1 seconds during the collision. Calculate the magnitude of the force that ball X exerted on ball Y during the collision. For ball Y, the initial velocity, which we just calculated, is 4 meters per second to the west. So 4 meters per second to the west. And the final velocity, we also calculated it in 4.2 when we're using the fact that kinetic energy is conserved. We found it to be 6 meters per second to the east. And then the mass obviously is equals to 2 kgs, and the change in time is 0.1 seconds. Yeah, the balls were in contact with each other for 0.1 seconds. So with this information, which equation can we use to find F net? Obviously, we can say that F net is equals to the change in momentum divided by the change in time. So the change in momentum will be the mass multiplied by Vf minus Vi, everything divided by the change in time. So the mass, that is 2 kgs, Vf is 6 minus Vi, which is minus 4. Okay, everything divided by 0.1. So let's go ahead and take a look. So we're gonna have 6 minus 4, so that is 10 multiplied by 2, it's 20, divided by 0.1 is 200. So we have 200 newtons. So there we go. This is the magnitude of the force that ball X exerted on ball Y during the collision. Product of mass and velocity, that is momentum, is the object's product of mass and velocity. That is 4.1. Let's go ahead and take a look at 4.2. So in 4.2, we are supposed to calculate the velocity of ball Q after the collision. So let's go ahead and take a look at what is happening. So we have a ball P of mass 0.16 kilograms moving east at a speed of 10 meters per second. It collides head-on with another ball Q of mass 0.2 kgs moving west at a speed of 15 meters per second. We can clearly see that from our sketch before the collision. After the collision, ball P moves west at a speed of 5 meters per second, as shown in the diagram below. We can clearly see that. Ignore the effects of friction and the rotational effects of the ball. If the question says that we must ignore the effects of friction, then we have an isolated system. We have a closed system. Momentum is conserved, right? Linear momentum is conserved. So let's take a look at our question. Calculate the velocity of ball Q after the collision. Based on the information we have the mass, the velocities before and after the collision. That leads us to use the conservation of linear momentum. Before the collision, we have two separate bodies. Even after the collision, we have two separate bodies. So this is how our equations are going to look like. The first statement we need to make is that the sum of the momentum before the collision is equal to the sum of the momentum after the collision. So this is the first statement you need to make. Just writing this in the final examination, you will get a mark for just writing this. Obviously, you cannot get this wrong. You just say sum of momentum before is equal to the sum of the momentum after. You will get a mark for just saying this. So after these steps, then we can say, okay, we have two bodies. We have ball P and ball Q. So we're going to have MP multiplied by its initial velocity plus MQ multiplied by its initial velocity being equals to MP multiplied by its final velocity plus MQ multiplied by its final velocity. So there we go. That is the equation we are going to use because we have two separate bodies before and after the collision. Okay, so if you get a mark for this statement, you're not gonna get a mark for this following statement. You only get a mark for one between the two, but I just prefer writing both for the sake of clarity. So we are always going to take direction to the east as positive unless the questions state otherwise. For all the questions you're going to solve, that is going to be the trend. East is positive unless stated otherwise. So the mass of ball P is said to be 0.16 kilograms. So we're going to have 0.16 kilograms multiplied by the initial velocity, which is 10 meters per second, plus the mass of ball Q. It is 0.2 kgs. Its initial velocity is 15 meters per second to the west. So we're going to substitute it with a minus sign because it is to the west and we are taking direction to the east as positive. The mass of ball Q, that is 0.16, and its final velocity is 5 meters per second to the west. So minus sign, minus 5. So now let's move to the mass of ball Q. The mass of ball Q, it is 0.2, and we're interested in the final velocity of ball Q. On the left hand side, we're gonna have minus 1.4 being equals to 0.16 multiplied by minus 5, which will be minus 0.8 being equals to 0.2 VF. So I'm going to take minus 0.8 to the left hand side. So that will be minus 1.4 plus 0.8, which is minus 0.6. So minus 0.6 is equals to 0.2 VF. At this point, we need to divide both sides by 0.2. If we do that, we're going to get minus 3 being equals to VF. Minus 3 is just the direction, which is to the west. So we have 3 meters per second west being equals to VF. So there we go. We have the final velocity of ball Q after the collision. Let's go ahead and do the question that follows. 4.3. Calculate the magnitude of the impulse on ball P during the collision. So we need to focus on ball P, right? Its initial velocity, as you can clearly see here, is 10 meters per second. So we have 10 meters per second. Its final velocity, as we can clearly see, is 5 meters per second. And we know that its mass is equals to 0.16 kilograms. So with this information, we can calculate the impulse. Okay, so the impulse delta P is going to be equals to the mass VF minus VI, right? Momentum final minus momentum initial. We are just taking the mass as a common factor. So the mass is 0.16. The final velocity is 5 meters per second to the west. So that is minus 5. Minus VI, 10 meters per second to the east. So it's just going to be minus 10. So the change in momentum is going to be equals to minus 2.4. This is just equals to 2.4 newtons multiplied by seconds. I'm deciding to use newtons multiplied by second because the question said impulse and not change in momentum. If the question had said change in momentum, I was going to use kg meters per second. But if you use kg meters per second, you will still get your mark. Explain what is meant by an isolated system as used in physics. So an isolated system is a system in which the net external force is 0. That is what we mean by an isolated system. The net external force is 0. That is 4.1. Let's go ahead and take a look at 4.2. So 4.2, the magnitude of the momentum of the bullet before it enters the block is 24 kg meters per second. Calculate the mass of the bullet. Okay, let's go and see what is happening here. So a bullet moves at a velocity of 480 meters per second. It hits a wooden block that is fixed to the floor. The bullet takes 0.01 seconds to move through the stationary block and emerges from the block at a velocity of 80 meters per second east. See the diagram below. Ignore the effects of air resistance and consider the block bullet system as an isolated system. Alright, so again, let's take a look at our equation. The magnitude of the momentum of the bullet before it enters the block is 24 kg meters per second. So we have the momentum, or at least the magnitude of the momentum, being 24 kg meters per second. Calculate the mass of the bullet. So we have the momentum. We want to find the mass of the bullet. This momentum is for the bullet before it enters the block. And we know that before it enters the block, it is moving with a velocity of 480 meters per second. So we have V being equals to 480 meters per second. So obviously with these three variables, we're going to use P is equals to M multiplied by V. This has to be one of the easiest questions I've ever came across, most especially in a final exam. But anyway, stories. Let's go ahead and substitute. P is 24. The mass is what we're interested in. The velocity is 480. So let's go ahead and divide both sides by 480 and see what we end up with. So 24 divided by 480, we're going to have 0.05 kgs, being equal to the mass of the bullet. So there we go. We have our solution to 4.2. Quite an easy question, to be honest. No trickery whatsoever. Let's go ahead and do 4.3. So 4.3, calculate the average net force exerted by the wooden block on the bullet. Okay, so this is paying attention to the bullet. As the bullet strikes the wooden block, it has an initial velocity of 480 meters per second to the east, right? And then when it leaves the block, as it emerges, we have a final velocity of 80 meters per second. This is to the east. So let's take a look. We have VI, we have VF. Obviously, we have the mass of the bullet as we calculated it in 4.2. The mass of the bullet is 0.05, so we're gonna have 0.05 kgs. Another piece of information we have is the time taken for the bullet to move through the stationary block. It takes 0.01 seconds. Here it is on our question statement. So we're gonna have delta t being equals to 0.01 seconds. So there we go. This is the information we have. We want to calculate the average net force exerted by the wooden block on the bullet. This should be easy to do, right? It should be easy for you to see which equation we have to use here. We will use F net is equals to the change in momentum divided by the change in time. So F net will be equals to the mass multiplied by VF minus VI, everything divided by delta T. So the mass is 0.05. If we take direction to the east as positive, VF is 80 minus VI, which is 480, everything divided by 0.01. And if you put that in a calculator, you're gonna get minus 2000, which we know that it is just equals to 2000 newtons to the west, right? Because the negative sign is to the west if we take in east as positive. Momentum is the product of the mass of an object and its velocity. Okay. The second question, 4.2, will the girl roller skate combination move to the left or to the right after the parcel is thrown? Name the law in physics that can be used to explain your choice of direction. So let's go ahead and take a look and see what is happening. Initially, a girl on roller skates is at rest on a smooth horizontal pavement. The girl throws a parcel of mass 8 kgs horizontally to the right at a speed of 4 meters per second. Immediately after the parcel has been thrown, the girl roller skate combination moves at a speed of 0.6 meters per second. Ignore the effects of friction and rotation. We can clearly see the girl on the roller skates and the parcel that is being thrown. So back to our question, will the girl roller skate combination move to the right or to the left after the parcel is thrown? Okay, so let's take a look. The parcel is thrown to the left with a force of a certain magnitude, right? According to Newton's third law, if you apply a force on an object, the object will also apply force on you of equal magnitude but in the opposite direction. So the girl roller skate combination will move to the right because the girl is applying a force on the box to the left, right? On the parcel, not the box. The girl roller skate combination will move to the left because of Newton's third law. Right, so there we go. That is 4.2. Let's go ahead and take a look at 4.3. So 4.3, the total mass of the roller skates is 2 kilograms. Calculate the mass of the girl. Okay, so let's take a look. We want to find the mass of the girl. We have the mass of the roller skates, obviously. We have the velocity initial of the roller skates and the girl, right? Because before the parcel is thrown, both the parcel, the roller skate, and the girl, they are at rest. The initial velocity is equals to 0, right? That is before the parcel is thrown. So we have our VI, which is equals to 0 before the parcel is thrown, right? So this is before the parcel is thrown. So now let's take a look at what happens after the parcel is thrown. So after the parcel is thrown, the mass of the girl is still unknown. We have the mass of the roller skate, obviously. We also have the mass of the parcel, right? It's 8 kgs. So we have the mass of the parcel, but now we have the final velocity of the girl and roller skates, which is equals to 0.6 meters per second to the left. We know that the roller skate girl combination will move to the left. That's our answer to 4.2. And we also have a final velocity for the parcel. We know that it moves with a velocity of 4 meters per second after being thrown. So with these variables, you can see which equation we're supposed to use, which law we're supposed to use, right? We're supposed to use the conservation of linear momentum. So we can say that the sum of the momentum before the girl throws the parcel should be equal to the sum of the momentum after the girl throws the parcel, right? So let's take a look at the girl and the roller skate first. So let's pay attention to that. Well, the girl and the roller skate, they are one body. We can refer to them as one body, right? I'm saying that because the girl is on roller skates. If the girl is moving with a velocity of 20 meters per second, the roller skates are going to be moving with a velocity of 20 meters per second. So let's take the girl and the roller skates as one body, of which, if we do that, we're going to have mass of girl plus mass of roller skates multiplied by VI plus mass of parcel multiplied by VI, okay, being equals to mass of girl plus mass of roller skates multiplied by VF plus mass of parcel multiplied by VF. So there we go. This is before the girl throws the parcel, and this is after the girl throws the parcel. So let's go ahead and substitute. The mass of the girl is what we are interested in. The mass of the roller skates is 2 kgs. The initial velocity is 0. Plus the mass of the parcel, 8 kgs. The initial velocity is 0. This is before the girl throws the parcel, okay? Being equals to the mass of the girl, what we're interested in, mass of the roller skates, 2 kgs, multiplied by VF, which will be minus 0.6, right? 0.6 meters per second to the left. If we take direction to the right as positive, then that velocity should be negative. Plus the mass of the parcel, 8 kgs, multiplied by its velocity, 4 meters per second. So this is going to give us 0. And we're also going to get 0 from that part also. So we're going to have 0 being equals to the mass of the girl. Let's multiply out here. Let's multiply out. 0 being equals to minus 0.6 mass of the girl plus 2 multiplied by minus 0.6. So that will be minus 1.2. And then plus 8 multiplied by 4. So 8, 16, 32. So we have plus 32. Okay. If we take minus 1.2 and 32 to the left hand side, we're gonna have plus 1.2 minus 32. So we're gonna have minus 30.8 being equals to minus 0.6 mass of the girl. So what is minus 30.8 divided by minus 0.6? We get the mass of the girl being equals to 51.33 kilograms. So there we go. We have the mass of the girl is 51.33 kilograms. Right, let's move to the question that follows. 4.4. So in 4.4, we're supposed to calculate the magnitude of the impulse that the girl roller skate combination is experiencing while the parcel is being thrown. Okay, so the initial velocity is 0, and then after the parcel is thrown, the velocity is minus 0.6. Well, velocity cannot be minus, so let me write 0.6 meters per second. I just need to remember that this is to the left, right? So the mass of the girl and the roller skates, so the mass is equals to 51.33 plus 2, which will give us 53.33 kgs. We want to find the impulse on the girl roller skate combination. So the mass is going to be the mass of the girl plus that of the roller skate, which will give us 53.33. So now we can go ahead and calculate the impulse. The mass multiplied by VF minus VI. The mass is 53.33 multiplied by VF, which is 0.6 to the left, so minus 0.6 minus VI, which is 0. So the impulse is minus 32. We're only interested on the magnitude, so we don't have to stick the direction. Minus 32 kg meters per second. State the principle of conservation of linear momentum. Well, in an isolated or closed system, the total linear momentum is conserved. In an isolated or closed system, the total linear momentum is conserved. So that is the answer to 4.1. We just have to state the principle of conservation of linear momentum. Let's go ahead and take a look at 4.2. So in 4.2, we're supposed to calculate the magnitude of the velocity of trolley Y immediately after the collision. So let's go ahead and take a look at our question statement and figure out what is going on. So we have a trolley X of mass 1.2 kilograms that travels at 8 meters per second east and collides with trolley Y of mass 0.5, which is initially at rest. So we know that its initial velocity is equals to 0. That's what at rest implies in physics. Okay, let's carry on. Ignore all frictional effects. So if the question statement says we must ignore all frictional effects, it means that we have a closed system. Momentum is conserved. So you need to always check that in your question statement. Does it say you can ignore the effects of friction? If it says so, then momentum is conserved. Let's carry on. The velocity time graph below shows the velocity of trolley X before, during, and after the collision with trolley Y. Okay, so like we have read on our question statement, the initial velocity, the velocity of trolley X before the collision is 8 meters per second. So right here is before the collision at 8 meters per second. Okay, and then this will be after the collision. So this is VI, which is 8 meters per second, and this is VF, which is 4 meters per second for trolley X. Okay, so let's go ahead and calculate the magnitude of the velocity of trolley Y. How are we going to do that? We'll start by saying that because we are told we can ignore the effects of friction, momentum is conserved. That tells us that the sum of the momentum before the collision will be equals to the sum of the momentum after the collision. Okay, we have two trolleys, X and Y, right? So initially, before the collision, we're gonna have M1 V initial plus M2 V initial being equals to the sum of the momentum after the collision. So they don't stick together after the collision, right? There is nowhere in the question where that is mentioned. So after the collision, we will have M1 V final plus M2 V final. Okay, so there is a mark for this statement. The sum of the momentum before is equal to the sum of the momentum after. So let's go ahead and start with trolley X. Trolley X, before the collision, the mass is 1.2. The initial velocity is 8 meters per second to the east. Let's take direction to the east as positive. So we're going to have 1.2 multiplied by 8 plus M2, the mass of trolley Y. This is 0.5. Before the collision, it's at rest, so the velocity is 0. This is equals to M1, 1.2, and after the collision, the velocity of trolley X is 4 meters per second. So we have 4 right here. And then plus M2, the mass is 0.5, and we want to find VF. So what is 1.2 multiplied by 8? We have 9.6 being equals to 1.2 multiplied by 4, because 0.5 multiplied by 0 will give us 0. So now we are doing 1.2 multiplied by 4, which is going to give us 4.8 plus 0.5 VF. So we have to take 4.8 to the left hand side. We're going to have 9.6 minus 4.8 being equals to 0.5 VF. So 9.6 minus 4.8, that is 4.8, which is equals to 0.5 VF. We can take, we can divide both sides by 0.5. We're going to have 9.6 meters per second being equals to VF. So there we go. This is the final velocity of trolley Y immediately after the collision. So there is a mark for this step and a mark for this step, making a total of 4 marks. So, ladies and gentlemen, this is how we apply the conservation of linear momentum. This is how we do it. Let's move to the question that follows. So 4.3, the question says, calculate the magnitude of the average net force that trolley X exerts on trolley Y during the collision. So we are interested on trolley Y, right? We want to determine the magnitude of the average net force that trolley X exerts on trolley Y. So let's go ahead and pay our attention to trolley Y. With regards to trolley Y, the initial velocity, it starts at rest. So Vi is equals to 0. And its initial velocity, that of trolley Y, what we just calculated, 9.6. So its final velocity is 9.6, like we just calculated. And then its mass is equals to 0.5. We're just trying to gather all the information we have so that we can be able to choose a formula. We don't choose a formula and force the information. No. The information guides us to the formula we need to use. So there we go. We have the initial velocity, the final velocity, and the mass. We are interested in the force, right? So it seems like we can use F net is equal to the change in momentum divided by the change in time. This is because the change in momentum is just mass Vf minus Vi, everything divided by delta T. So we want to use this equation. Do we have the mass? Yes, we do. Do we have Vf? Yes. Vi? Yes. Do we have delta T? We do have delta T, but it's not obvious that we do. But if you take a look at the velocity time graph we're given for trolley X, you will realize that this is where the collision starts at Vi, and this is where it ends at Vf. And we have the corresponding time. They collide at 20.1 seconds, and at 20.2, that's where the collision comes to an end. So we can have the mass of the object being equals to 0.5. Vf is 9.6. Vi is 0. And the change in time final is 20.2, right? And the time initial is 20.1. If you put this in your calculator, you're gonna get 48 newtons. This is the magnitude of the average net force that trolley X exerts on trolley Y. There we go. Let's move to the question that follows. 4.4. Is the collision elastic or inelastic? Explain the answer by means of a suitable calculations. Right. All the subtopics we have covered are all coming together now. We are interested on whether a collision is elastic or inelastic. So let's go ahead and take a look at how that will look like. Before we answer this question, the first thing we want to do is to say that EK is equals to a half mv squared. This is just the equation for kinetic energy. You want to write that equation down. As soon as you write that equation down, you have a mark, right? And then after that, you can then determine whether the collision is elastic or inelastic. So how do you determine that? You calculate the sum of the kinetic energy before the collision and see if it is equal to the sum of the kinetic energy after the collision. So when we were talking about collisions, we say that for a collision to be elastic, momentum needs to be conserved and kinetic energy needs to be conserved. But we know that there's no frictional force in our system. So momentum is already conserved. We know that, okay? We used that fact to answer 4.2. Now, we just need to check the kinetic energy. Is the kinetic energy conserved? So let's go ahead and find out. If I start with trolley X, before the collision, we're going to have a half. The mass is 1.2. The initial velocity is 8 meters per second squared, right? And then plus a half. This is for trolley Y now. The mass is 0.5. Initially, it's at rest. So we're going to have 0 squared. This is equals to, we get 38.4 joules. The SI unit of energy is joules. So this is the kinetic energy before the collision. Let's go ahead and take a look at the kinetic energy after the collision. We're going to have a half concentrating on trolley X first. The mass is still 1.2. The velocity is 4 meters per second. We square that plus the kinetic energy of trolley Y. The mass is 0.5 and the velocity after the collide, which we calculated in 4.2, is 9.6, and we square that. If you put that in your calculator, you're gonna have 32.64 joules. So there we go. We have EK before and after the collision. So we can go ahead and conclude and say that the collision is inelastic, right? And why do we say so? EK before is not equals to EK after, right? If this is the case, then our collision is inelastic. It would be elastic if EK before is equals to EK after. So there we go. This is how we determine whether a collision is elastic or inelastic. Momentum and impulse topic test. Let's take a look and see what is going on. So, question 1, multiple choice questions. Let's see how we approach this kind of questions. 1.1, which one of the following best describes an inelastic collision? So, before we even look at our options A, B, C, and D, we know that a collision is deemed inelastic when momentum is conserved but kinetic energy is not. So that's what we are looking for essentially in our options A, B, C, and D. Option A, both momentum and kinetic energy are conserved. That would be an elastic collision, not an inelastic collision. So A cannot be our answer. B, total kinetic energy is not conserved, but total linear momentum is conserved. We need to look no further. The correct answer to 1.1 is B. 1.2, in the equation F net multiplied by delta T is equals to delta P, the product of F net delta T represents the impulse, right? We know that from theory. There's nothing we are calculating here. There's nothing we need to figure out. We're just taking our answer as it is. So 1.2, the answer is C. F net delta T is the impulse. There's really no need for an explanation here because that is just theory, okay? But things get interesting when we go to 1.3 and 1.4. Take a look at 1.3. So a body is moving at a constant velocity and has kinetic energy E and momentum P. The velocity of the object is doubled. Which one of the following correctly gives the magnitudes of both the kinetic energy and momentum? Right, so it has the velocity v initially, and it is then changed to 2v. So the momentum when the velocity is v will be p is equals to mv. And then the kinetic energy when the velocity is v will be a half mv squared. Let's take a look at the scenario where the velocity is now 2v. The momentum will be p is equals to, let me say, px, right? Px will be equals to m multiplied by 2v, which is equals to 2mv. So this is 2p. So the momentum doubles when the velocity doubles. Now let's take a look at kx. We're gonna have a half m instead of v, we have 2v, and we square that. This is gonna be equals to a half m multiplied by 4v squared. This is equals to 4, right, multiplied by a half mv squared. We know fully well that a half mv squared is just k. So kx, the new kinetic energy, is 4 times the initial, and the momentum is 2 times the initial. So which option gives us that? So option A, we have 2e, 2p. Our answer is option C, where we have 4e, and 2p. So the answer to 1.3 is C. So there we go. This is how we solve these kind of questions. We're going to use the same technique or something close in 1.4. So 1.4 says a ball of mass m strikes a wall perpendicularly at a speed 2v. Immediately after the collision, the ball moves in the opposite direction at a speed v, as shown in the diagram below. The magnitude of the impulse of the ball is. So impulse is equals to the change in momentum, right? But it is also equals to F naught delta t. So we're going to have m Vf minus Vi. So m is just m, and then let's talk about v. It strikes the wall with a velocity of 2v, and then it leaves the wall with a velocity of v. But if you look at the direction, this is to the right and that is to the left. So we need to think about that when we substitute. So which direction do we need to take to the do we need to take as positive, and which direction is going to be negative here? If we take direction to the right as positive, we'd have 2v minus v, which will be plus, right? So this is going to give us 3mv, which is option D. That is 1.4. We need to be comfortable with working with variables. Okay. Question 2. Let's take a look. The diagram below shows a 65.4 kg dancer who jumped in the air and landed a foot on the floor at 7 meters per second. She came to a complete stop in 0.5 seconds. Right, let's take a look. 2.1. Define the term impulse in words. Well, I'm gonna let you do that. And then 2.2, let's take a look at 2.2.1. We are supposed to calculate the impulse of the dancer. So F net multiplied by delta t, not delta p, but delta t, as I'm saying, is equals to delta p. Delta p is the impulse, but it is also equals to the change in momentum, right? So we have our initial velocity and we have our final velocity, right? We just need to decide on which direction we are taking as positive, right? If we take upwards as positive, we're going to have the mass of the dancer being 65.4. Let me just verify. Right. And then the final velocity, the dancer comes to a complete stop in 0.5 seconds. So the final velocity is 0 minus the initial velocity. We are taking up as positive. So we're going to have minus 7. So if you put that in your calculator, we are going to get 457.8 newtons multiplied by seconds. Right. If the question had said change in momentum, it would be kg meters per second. But because you're looking for the impulse, newtons per second. Not newtons per second, but newtons multiplied by seconds. Right. 2.2.1. 2.2.2 on the other hand, the magnitude of the force which the floor exerts on the dancer's foot. So take a look at this. We are looking for the force, right? We have calculated delta P and we have delta T. Seems quite straightforward. So F net will be equals to the change in momentum, the impulse, divided by delta T. So we already have delta P, which is 457.8 divided by the change in time, which is 0.5 seconds. So we have 0.5 seconds, right? And when I put that in my calculator, I'm getting a 915.6. Since our answer is positive, this will be upward, right? Because we're taking upward as positive. Okay, 2.2.2. Let's take a look at 2.3. Right, 2.3 is quite an interesting question. In the diagram below, a 600 grams football, which is initially at rest, is thrown at the wall. The following graph shows the change in the applied net force over a period of time. We can clearly see there the graph forms a triangle. And then 2.3.1, we're supposed to state Newton's second law. in terms of momentum. Right, so what does it say in terms of momentum? Take a look at this. F net is equals to ma, that is terms of acceleration. In terms of momentum, we have F net being equals to delta p over delta t. So how do we then state Newton's second law in terms of momentum? The net force acting on an object is equals to the rate of change in its momentum. There we go. That is Newton's second law in terms of momentum. And then 2.3.2, calculate the magnitude of the impulse exerted to the football. Okay, so take a look at this once more. The impulse F net delta t is equals to delta p. So what is the impulse? F net multiplied by delta t. If you take a look at our graph, we just need to calculate the area of the triangle in order to have our impulse. Right, the area of the triangle there will give us the impulse, because in order to calculate the area, we are saying half base multiplied by the height, of which we have F net and delta t. Okay, so let's go ahead and do that. Delta p is going to be equal to half base multiplied by height. So delta p is going to be equal to a half the base time taken from 0 to 12 seconds. So that is 12. And then the height from, let me just take out my ruler. Right, this is our height. This is our height. So we needed to go to a graph and see where it cuts on the y-axis. So let's take a look. This is 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Right. So you can clearly see that it cuts at 34. So we have 34 right there. And then now it's just a matter of putting that in our calculators and see what we have. So let me just do that. I'm getting 204 newtons multiplied by seconds, as I've said. Right, that is 2.3.2. 2.3.3 says that use the calculation to show that the velocity at which the ball or at which the football hits the wall is 340 meters per second. The velocity at which it hits the wall is 340 meters per second. Right, so let's see what we have. We have delta p, right? We calculated it using the area of the graph, but delta p is also equals to m vf minus vi. So we can use this in order to find the velocity. We are using what we're given to find that which we don't have, that which the question is asking us to find. So delta p, that is 204. The mass of the ball is 600 grams, so that is 0.6 kgs. And then the final velocity is what we are interested in, right? Minus the initial velocity. The ball comes from rest, so this is 0. Okay, so it's just a matter of dividing both sides by 0.6 in order to find VF. So VF is equals to 204 divided by 0.6. This is 340 meters per second. Somewhere close to the speed of sound in air. But anyway, stories. Let's take a look at question 3. Right, so question 3, in the diagram below, a trolley of mass 5 kgs moves at 4 meters per second east across a frictionless horizontal surface. So we don't have any friction there. A box of mass 1.5 kg is dropped onto the trolley. Then the trolley and the box continue to move in the same eastward direction. Take eastward direction as positive. 3.1, I'm going to let you state the law of conservation of linear momentum. And then 3.2.1, we're supposed to calculate the velocity of the trolley box system after the box is dropped onto the trolley. Right. So usually in physics, if 3.1 says state the law of conservation of linear momentum, and 3.2 you're supposed to calculate something, that's something which you're supposed to calculate, you are most likely to use the law that you've stated. So if we use the conservation of linear momentum here, we're going to say that the momentum before is equals to, well, not the momentum, but the sum of the momentum before is equals to sum of the momentum after, right? After the brick. Is it a brick? After the box has been dropped down to the trolley, not a brick, right? So we have M1 V1, that is the momentum of the box, M2 V2, that is the momentum of the trolley. And then after the box falls onto the trolley, right, after it is dropped onto the trolley, we're gonna have M1 plus M2 multiplied by VF, because they now move as one unit. So the box as it is being dropped onto the trolley will have a mass of 1.5, but its velocity along the x-axis is 0, right? Plus mass of the trolley, which is 5. Its velocity, it says 4 meters per second to the east. We're already told that we must take direction to the east as positive. So that is 5 multiplied by 4. Okay. After the collision, we have 1.5 plus 5 multiplied by VF. So obviously this will give us 20, and this is equals to 6.5 VF. So VF is equals to 3.08 meters per second east. So there we go, 3.2.1. 3.82.2, we want to calculate the change in momentum of the trolley. So change in momentum, M VF minus VI. Initially is, oh well, not initially, because the mass is always conserved, it's the same as the mass is 5, but the final velocity is 3.08. The final velocity is 3.08. And then what about the initial velocity? It is 4 meters per second in the same direction. So the change in momentum therefore is 4.62 kg meters per second. Do you see the difference? When I'm talking about impulse, I use newtons multiplied by seconds. When I'm talking about change in momentum, I use kg meters per second. That's how it's supposed to be done. Right, 3.3. State the condition for an elastic collision. Right, we've already talked about that as we were answering the MCQ. For a collision to be elastic, momentum needs to be conserved, kinetic energy needs to be conserved. And then 3.4 is saying that use a calculator to show that the collision between the box and the trolley is elastic or inelastic. So take a look at this. We don't have to show that momentum is conserved anymore. We actually don't have to do that. Why? We were told in the question statement that the trolley is moving on a frictionless horizontal surface, right? If it is moving on a frictionless horizontal surface, the linear momentum is conserved. That is why we use that theorem in 3.2.1, because how are we using that theorem if the linear momentum is not conserved, right? So already the linear momentum is conserved. We just need to check the kinetic energy, whether it is conserved or not, right? But we cannot start by saying EK before is equals to EK after. The question cannot say show that x is equals to 2 and then you start by saying x is equals to 2, therefore blah 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 blah. Doesn't make any sense. So right, we need to calculate EK before separately, calculate EK after separately, and see if they're equal to each other. So let's do that. EK before, right, the sum. So we're gonna have half mv squared for the box plus half mv squared for the trolley. So for the box, half m is 1.5, it's v is 0 along the x-axis, and then half the mass is 5 for the trolley, the velocity is 4, and we square that. Right, so let me just put that in my calculator and see what I have. This is 40 joules. And now let's calculate EK after the collision. Right, so after the collision, they move as one unit, right? So we are going to have a half 5 plus 1.5 multiplied by 3.08 squared, because after the collision they move as 1 unit. So let me just calculate that and see what happens. I'm getting 30.83 joules. So clearly EK before is not equals to EK after. So we can confidently say that the collision is inelastic. Right, let's move to the following question. Question 4. The diagram below shows shows car A of mass 800 kgs traveling slowly near the traffic light. Car A is hit from behind by car B of mass 950 kgs traveling at 10 meters per second in an eastward direction. I found myself in one of these situations, so it's going to be quite fun calculating, knowing that I've been in such a situation. Right, the change in momentum with time of car A just before and after the collision is represented on the diagram below. Consider the system to be isolated, so momentum should be conserved. 4.1, we're supposed to define momentum. I'll let you guys do that, and then let's take a look at 4.2. Use the information in the graph and the relevant equation to explain why the net force acting on car A is 0 between T10 and T20. Right, the net force between T10 and T20 is 0. The question is saying let's use a relevant equation to explain why. Okay, so between T10 and T0, we can see that the momentum is constant, right? And we know that F net is not only equals to ma, but F net is also equals to delta p over delta t. So the momentum is constant. So what is the change in the momentum if the momentum is constant? The change in the momentum is 0. So we have 0 divided by delta t. So this is going to give us a 0 newtons. So that's how we can easily show that the net force should be 0 between T10 and T20, because the momentum is constant. It is not changing. Right. 4.3. Use the information in the graph to calculate the magnitude of the velocity of car A just before the collision. Well, it's equation, honestly. Just before the collision, the magnitude of, okay, yeah, so just before the collision is at that point, right, before the momentum starts changing. So the magnitude of the velocity, P is equals to M multiplied by V. The momentum is 20,000, is given in the equation, in the graph. And then what is the mass of car A? It is 800 kgs. So we have 800 multiplied by the velocity. So V is equals to, let's see, 25 meters per second. So there we go. That is 4.3. It says the magnitude, so we don't have to worry about the direction. And then 4.3.2, that is 4.3.1. The velocity of car B just after the collision. 4 marks. Okay. B after the collision. Do we need to do some complicated things there? So before the collision, car B, let me see. I'm trying to see if car B is stationary. Right, the diagram below shows car A of mass 800 kg traveling slowly near the traffic light. Car A is hit from behind by car B. Right, car A is hit from behind by car B. Okay, so both these vehicles are moving before the collision. Right, the sum of the momentum before will be equal to the sum of the momentum after. Obviously, I'm able to use that because we are told that our system is isolated, right? So before the collision, this is the graph for car A, right? So before the collision, the momentum of car A is 20,000 before the collision, plus the momentum of car B, which is going to be 950 multiplied by 10. It's here in the equation, right? Car B is moving at a velocity of 10 meters per second in the eastward direction at a speed, right? And this is going to be close to the momentum after. The momentum after of car A is 10,000. Can clearly see that from the graph. It's 10,000. And then plus that of car B after the collision. So 950 multiplied by V. Okay, so now time to press my calculator. So I have 20,000 plus 950 multiplied by 10. This is 29,500, and then this is equals to 10,000, right? 10,000 plus 950 V. So obviously if we take 10,000 to the other side, we're just going to have 19,500, and this is equals to 950 V. Dividing 900 by 950 on both sides, we get the V final being 20, what am I writing there? Being 20.53 meters per second. So there we go, to the east. We have clearly taken the direction to the east as positive here. I hope you're not one of those people that just memorize definitions without knowing exactly what they mean. So here in question 4, the only question I would understand if you got it wrong is 4.5. That is the only question that I think was a bit difficult. Everything else is just basic stuff. So let's go ahead and look at 4.1. We're supposed to define the term impulse. Let me show you something. We know fully well that F net is equals to the change in momentum divided by the change in time. If we cross multiply, the change in momentum or the impulse is equals to F net multiplied by delta t. So what is the definition of impulse? If you look at this formula, the impulse should be the product of the net force and the time it acts on the object from the formula. That's the connection you need to make between definitions and formulas. That is 4.1. Let's go ahead and take a look at 4.2. Use the information on the graph to determine the magnitude of the impulse as the ball hits and bounces off the force sensor. Right, let's go through our question statement and see what is going on. When a ball hits and bounces off a surface, it exerts a force on that surface. Grade 12 learners investigated how this force varies over time as the ball hits a force sensor and bounces off. A 50-gram soft ball was dropped from a height of 1.5 meters vertically above a force sensor connected to a laptop as shown on the diagram. And the graph we're given the force versus the time. The force is in Newton and the time it is in milliseconds. So as soon as you don't realize that the time is in milliseconds, you're probably going to get the question wrong. Let's use the information in the graph to determine the magnitude of the impulse. So the impulse is the force multiplied by the time. We have a shape, we have a triangle. So in order to find the impulse, we need to find the area of this triangle. How can we find the area of a triangle? That is half base multiplied by height. So this will be equals to a half base. Our base is the time in milliseconds. We go from 0 to 15 milliseconds. So we're going to have 15 divided by 1000. Multiplying by 10 to the minus 3 is the same as dividing by 1000. Now we have converted our time from milliseconds to seconds. Multiply by our height. Our height is right here. We are given the value as 64.13. So we have 64.13. That is the impulse, half base times height. If you put that in your calculator, you'll get 0.481 newtons multiplied by seconds. That is 4.2, calculating the impulse. 4.3, state the magnitude and the direction of the change in the momentum of the ball. The impulse is equal to the change in the momentum of the ball. So we already have our answer. We just need to quote it. Right, we need to state the magnitude and the direction. So the magnitude is 0.481 kg meters per second. Why am I using kg meters per second? Because when you are calculating the change in momentum, you use the mass and the velocity. So that's why I have kg meters per second. But when you calculate in impulse, you have newtons multiplied by second. That is the only difference. Right. So we have 0.481 as the magnitude. What about the direction? The ball is being dropped and it hit the force sensor. when it hits the force sensor will apply a force on the ball upwards. So the impulse will be upwards. So this is the direction we need to indicate here, that it is 0.481 upwards. So in 4.4, if the velocity of the ball just before it hits the force is 5.42, so VI is equals to 5.42 meters per second downwards. Calculate the velocity with which the ball will bounce off the sensor. So we're looking for VF. What is VF? That's what we're interested in. We need the mass of our soft ball. The mass is equals to 50 grams, which we're going to divide by 1000 to convert to kgs. And what else do we have? We have the impulse. Delta P is equals to 0.481 upwards. So VI is downwards. We can substitute it with a negative sign because it is downwards. And then the impulse is upwards. So we're going to substitute it with a positive sign. That's if we take up as positive. You can take down as negative, and you can take down as positive and do it the other way around. Anyway, stories. So F net multiplied by the time is equals to the change in momentum. So what is F net multiplied by the time? That is 0.481. This is equals to the change in momentum. The mass multiplied by VF minus VI. So we're going to have 0.481 being equals to 50 divided by 1000 multiplied by VF. VF is what we're interested in. Minus 5.42. The first thing we should be doing here is dividing both sides by 50 divided by 1000. If we do that, we're going to get 9.62 being equals to VF plus 5.42. Now we just need to take 5.42 to the left hand side. We're going to get VF being equals to 4.2 meters per second upwards. That is our final velocity. 4.5, the only question that was a bit tricky. Everything else is just the basic stuff. So let's go ahead and take a look at 4.5. The ball is now replaced with a harder ball of the same size and mass. Will the force on the force sensor increase, decrease, or remain the same? The force is going to increase. Let me show you why. We know that F net is equals to the change in momentum divided by the change in time. If instead of using a softer ball, you use a harder ball, delta T is going to decrease. The time of contact is going to decrease. So if the time of contact decreases and the change in momentum stays the same, then it is easy to see that F net is going to increase. F net is inversely proportional to the time of contact. So the answer to 4.5 is increases. Write down the horizontal speed of the brake just before the girl catches it. So here on the question statement, we are told that the girl, she catches a brake of mass 5 kg, which is thrown vertically downwards from the top of a high wall. So the brake is thrown vertically downwards from the top of a high wall, right? So if a brake is thrown vertically downwards, then it has a horizontal speed of 0 meters per second, right? Because it's only moving along the horizontal. So the answer for 4.1, we're going to have Vx, x being for horizontal, being equals to 0 meters per second. And then now moving to the next question, 4.2. 4.2 is saying that let's calculate the girl's speed just before she catches the brake. Let's calculate the girl's speed just before she catches the brake. So let's go through the question statement and have an idea of what is going on. So we are told here that a girl on roller skates of combined mass to 52 kg moves horizontally at a certain constant velocity. So we have some mass which is equals to 52 kgs, and then the velocity is unknown, right? And then goes on to say that she catches a brake of mass 5 kg. So we have a mass of the brake which is equals to 5 kg. it's been thrown vertically downwards, so it has a horizontal velocity of 0, like we've deduced in 4.1, and then the girl continues to move in a straight line at a speed of 2.4 meters per second after catching the brick. So when we have the girl of mass 52 kgs plus the brick of 5 kgs, they move together at a velocity of 2.4 meters per second, right? Which law are we going to use to solve this problem? We're going to use the conservation of linear momentum, right? So that is to say that the momentum before, the sum of the momentum before will be equals to the sum of the momentum after. So let's go ahead and try calculate the momentum before. So before, we have a mass of the girl, right? And then it's moving at a certain velocity, and that will be the momentum of the girl, plus the mass of the brick. It's moving at a certain velocity, and then that will be the momentum of the brick. And then after the girl catches the brick, we now have m1 plus m2, right? The mass of the girl and the brick, and then they're moving at the same velocity, right? So what is the mass of the girl? We know fully well that the mass of the girl is 52 kgs. And then the velocity initially before catching the brick, it's unknown. It's what we're looking for. And then plus the mass of the brick, which is 5 kgs, and then multiply by the velocity of the brick before the girl catches it. We're interested in the x component, so we're going to have 0 here, and then this will be equals to obviously the mass of the girl plus the mass of the brick, that will be 52 plus 5 multiplied by the velocity at which they're moving at. So we have multiplied by 2.4. So 5 multiplied by 0 is going to be 0, right? So we're going to just be left with 52 multiplied by the velocity of the girl before catching the brick. So if we solve for that, right, we're gonna get a velocity being equals to 52 plus 5 multiplied by 2.4. And then everything divided by, we divided by 52, the coefficient of V. And then the answer here is 2.6308 meters per second to the direction the girl was initially moving at, right? Yeah, this question doesn't really say a lot about the direction, whether the girl is moving to the east or the girl is moving to the right. But since the question says speed, we can just forget about the direction and just write the magnitude, right? And then now let's move to 4.3. So what do we have here on 4.3? The girl brick combination moving at 2.4 meters per second moves on to a rough surface. She comes to rest after moving 2 meters along the rough surface. And then 4.3 is saying that let's write down a pair of action reaction forces acting while the girl catches the brick. So when the girl catches the brick is going to apply a force on the girl, right? So we're going to have the weight of the brick, and then a force opposing the weight of the brick. That will be the normal force of the girl's hands, right? Because the brick is going to lay on the girl's hands. The reason why the brick doesn't go and hit the ground, it is because the girl is holding the brick and exerting a normal force, because we know that if you put an object on top of another, then there's going to be a normal force. So we have a normal force there exerted by the girl's hands, right? And then another pair, we can start with Fg, the force of gravity, right? The force that the earth is pulling the girl with. We know fully well if the earth is pulling the girl, then the girl is also pulling the earth. So we have that force there. And then those are our action reaction pairs. And then now moving to 4.4. So let's solve 4.4, right? The question is saying that let's calculate the magnitude of the net force exerted by the rough surface to bring the girl brick combination to a stop after 2 meters. So let's look at the information that we have and see what we can do, right? So we know that after the girl catches the brick, they start off at an initial velocity of 2.4 meters per second. And then they come to a complete stop. So we have VF being equals to 0 meters per second. And then what else do we have? We have the mass of the girl brick system. So that will be 57 kgs, right? And then we're looking for Fnet, right? So based on the variables we have here, you can easily see that Fnet, we can find it using Newton's second law in terms of momentum, right? So we have delta P divided by delta T, right? So Fnet is equals to, so what is delta P? The mass multiplied by VF minus VI, right? So we have VF minus VI divided by delta T. So let's just go ahead and substitute and find our answer real quick. So the mass will be 57 kgs. VF is 0, they come to a complete stop, and then VI is 2.4, and then divided by delta T. Right, now we have a problem. We need delta T and we don't have it. So how can you calculate that? Let's look at the variables we have again. We have VF, we have VI, and then apart from that we have delta X, right? And then we're looking for delta T. So which formula can we use to find delta T? It should be easy to see that we can say that delta X is equals to VF plus VI divided by 2 multiplied by delta T, right? Yeah, very rarely do we use this formula, but then yeah, look at us now, we have to sort of use it. So delta X is 2, VF 0, VI 2.4 divided by 2 multiplied by delta T, right? So we divide both sides by the coefficient of delta T. So delta T, so we have delta T is going to be equals to what? 2 divided by 2.4 divided by 2. So our delta T is 1.6667 seconds, right? So now we can substitute this delta T on the equation we had, right? So if we do that, we're gonna have Fnet. So we have Fnet being equals to, so 57, and then 0 minus 2.4 divided by delta T, which we now know is 1.6667. And then if you put that in your calculator, we shall get minus 82.0784, right? So we can just say 82.0784 newtons. And then we don't have to think about the direction because the equation said the magnitude. Let's just leave it like that. Question 4 says a simple rocket system consists of 2 parts. A of mass 3m. So let me jot that down. So we have A, and then they're saying that the mass is 3m kg or some unit, and then B of mass 2m. So we have B, which is mass of 2m kg or some unit. I'm not so sure. As shown in the diagram, below, B is stacked on top of A, and if you look on the left hand side, there it is. Before the collision, B is on top of A, and then after the collision, A is going down, and then B keeps on going up, I'm assuming. 4.1 says state the principle of conservation of momentum in words. That is just the total linear momentum in an isolated system is conserved, right? The sum of momentum before is equals to the sum of momentum after in an isolated system. And then 4.2 says the rocket is traveling vertically upward at a constant speed v. So let me write that down. A, when it's with B, their velocity, let me write that down. Their velocity is 1 divided by 3 v. No, it's actually, the velocity is v, I'm sorry. When an internal explosion causes A to move downwards at a
speed 1 divided by 3v. So there's a explosion, an internal explosion, and now A is moving downwards at v equals to 1 divided by 3v, right? And then for B, we don't know what is going on. Then the question says, okay, ignore all external forces on the rocket. The question now says, calculate the velocity of B in terms of V immediately after the internal explosion. So this is our scenario. Let me get it. This is our scenario before the explosion, and then this is what we have after the explosion. So this momentum here before is supposed to be equals to this momentum here after. That's what the conservation of momentum states, that the sum of the momentum before is equals to the sum of the momentum after, if the system is isolated or is closed. And then the question says, ignore all the forces on the rocket. So that tells us that the system is closed. Okay, so before the masses are together, right? So that will be m of body A plus m of body B, and then they're traveling at the same velocity. That's what the question states. And then after they're saying that A goes down, so we'll have m A, the mass of A, and then the velocity of A, which we're given. Now that they've exploded, they're no longer together, so the masses are apart. So we're gonna have the mass of B and then the velocity of B. The mass of A is said to be 3m, so we're gonna put 3m plus the mass of B, which is 2m, and then the velocity is just given as v, so that's exactly what we're going to have. The mass of A, we've already said that is 3m, and then the velocity of m is 1 over 3v. But then I want you to realize that A is going down, and common sense says we always take up as positive. If you take down as positive, that's fine, but then to me it doesn't make sense. Up is positive. So because A is going down, instead of 1 over 3v, I'm going to put minus 1 over 3v, right? Minus 1 over 3v plus m of B is 2 meters. So, it's 2m, I'm sorry. So we're going to have 2m multiplied by the velocity which we are interested in. So that's what we are supposed to find. So 3m plus 2m will give you 5m, then multiply by v, that's 5mv, right? That's our left hand side of the equation. Then 3m multiplied by minus 1 over 3v, that will give you minus 1v, right? So, minus 1mv, right? Because this 3 here on the denominator is gonna cancel out with this 3. And then plus 2 v. Let's denote this as v of b, so that we don't confuse our variable v with the v of b we're trying to determine. So the next step is to take this term here to the left hand side, so that we can isolate v of b. So we're gonna have, when it goes to the other side, it's gonna change its sign, obviously. So we're gonna have 6 m v equals to 2m v of b. We divide both sides by 2m, so that we can isolate v of b. Divide by 2m. Yeah, we're gonna be left with 3 here, because 6 divided by 2 is 3, right? So this will imply that v of the body B is equals to 3v. The question says we must find it in terms of v, so that is what we're going to find. So it's 3v upwards because we're taking up as positive. That's how we do the problem. It's not really complicated, apart from the fact that now we have a vertical. We're working on the vertical, and usually on momentum and impulse, you're working on the horizontal. But then apart from that, it's just straightforward. The masses are joined initially, and then after that they're separated. So for EP before, you're going to add the masses and have one velocity, and then for EP after, you're going to have the separate masses with the different velocities. Yes, I think I should do a separate introductory video on momentum and impulse. So you can let me know in the comment if that's something you'd be interested in. So if we move ahead, we have 4.3, which says the graph below shows the average force exerted by A on B during the internal explosion as a function of time. And then there we have it. On the y-axis we have average force, and then on the x-axis we have time. The question says, name the physical quantity represented by the area under the graph. So to calculate the area under the graph, you have to multiply the length by the breadth, right? Assuming that the length is going up, then it means you're gonna have force, the average force. So force average multiply by the time, right? But then the time doesn't start at 0, so it's basically delta t, because you have some time initial and some time final. And then which quantity is given by f average multiplied by delta t? That is delta p, right? So the physical quantity represented by the area under the graph is impulse, change in momentum. So that is coming from the formula. So this is what the question is asking for, right? So that is coming from the formula F net equals to delta P divided by delta T. So let's move ahead. 4.4, it says redraw the graph in your answer book on the same set of axes. Sketch the graph on the average. Sketch the graph of the average force that B exists on A as a function of time. So let me just put in an axis there. So that's our Y, that's our X, and then so we have force average, and then we have time in seconds, right? And then that's F A on B, right? The question says find FB on A. Newton's third law says that if body A exerts a force on body B will exert a force on body A of equal magnitude, but then in the opposite direction. So because this graph is on top of the x-axis, we're just supposed to draw the same thing, but then below the x-axis, so that the force has a negative sign, right? Equal magnitude, but opposite direction. So these two are supposed to be equal, this part and this part. And that's it for this question. If you like the video, please subscribe. Trolley X of mass 1.2 kgs travels at 8 meters per second east and collides with trolley Y of mass 0.5 kg, which is initially at rest. And then the velocity time graph below shows the velocity of the trolley X before, during, and after the collision with trolley Y. And then we have a fancy sketch there. And then the first question, 4.1, which is
saying let's state the principle of conservation of linear momentum. We'll leave that for you. And 4.2.1. So for 4.2.1, we're looking for the velocity of trolley Y immediately after the collision. So how can we possibly determine the velocity of trolley Y immediately after the collision? We are going to use the principle of conservation of linear momentum, because we know fully well that the sum of the momentum before a collision should be equal to the sum of the momentum after a collision, right? So what is the momentum before a collision? We're going to have the momentum of trolley X plus the momentum of trolley Y, and then after the collision we're going to have the sum of momentum of trolley X plus the sum of the momentum of trolley Y, right? So if we calculate the sum of the momentum of trolley X, let's not forget that P is equals to M multiplied by V, right? We're going to have 1.2 multiplied by 8. So now we can see that we need to decide on a direction. So let's take direction to the east as positive, right? And then the trolley, the momentum of trolley Y, it is at rest, right? So we have 0.5 multiplied by 0, right? This will be equals to the momentum after the collision of X. We have 1.2 multiplied by the velocity. The velocity is on the graph, right? Because here, this is the velocity before the collision, during the collision, and then immediately after the collision. So we have 4 then, and then plus 0.5 multiplied by the velocity of trolley Y, right? So without wasting any time here, we're gonna say that the velocity of trolley Y should be equals to, so we have this 1.2 multiplied by 8 there, so we're gonna have 1.2 multiplied by 8, and then this, because we're multiplying by 0, is gonna fall apart, right? And then minus this here, which is just 1.2 multiplied by 4, and then everything divided by the coefficient of Vy, which is 0.5. So if we put that in our calculators, we shall get Vy is equals to 9.6, right? We take in direction to the east is positive, so this will be 9.6 meters per second to the east, right? To the east. And now let's do 4.2.2. So 4.2.2 is saying that let's find the average net force that trolley X exerts on trolley Y during the collision. The average net force that trolley X exerts on trolley Y during the collision. We already know that after the collision, trolley Y is going to move to the east, right? So the direction of this net force should also be to the east, right? Irregardless of the sign we're going to get in our calculation, right? Because the sign is going to depend on which body you use, right? Are you using trolley X or are you using trolley Y? But then that shouldn't have an effect on the magnitude, right? So if we use trolley X, right? So we're going to say F net is equals to delta P divided by delta T. Let me explain why I'm using trolley X instead of trolley Y. The velocity of trolley Y, we calculated it ourselves, right? So what if that velocity is wrong and then we use it again, right? There's a good chance that that answer will also be wrong, assuming that there's no positive marking. So let's just stick to trolley X because we're going to be using the velocities that are given to us. So there's no way we can go wrong with the values, right? Momentum final will be 1.2 multiplied by 4. Minus momentum initial, which is 1.2 multiplied by 8, and then divided by the change in time, which I've indicated here in our graph, right? It happens from 20.1 to 20.2 seconds. So here we're going to have 20.2 being the final minus 20.1 being the initial. So if I just, put that in my calculator, let me see what I get here. I'm getting minus 48, right? But we've already said that we don't care about the sign, right? We know that it's supposed to be 48 newtons to the east, right? To the east.
And yeah, I think that's it for 4.2.2. Let's see what we can do for 4.3. So 4.3 here is saying that let's determine if the collision is elastic or inelastic, right? And explain the answer by means of a suitable conclusion. So what is the prerequisite for an elastic collision? So if a collision is elastic, then we need two things to be conserved, right? We need the momentum to be conserved, and we need the kinetic energy to be conserved. So in 4.2.1, we calculated the value of y, assuming that momentum is conserved. So it will make sense if we calculate the momentums again, right? Because that's what we're assuming. We're assuming that the momentum is already conserved. So we're just going to calculate the kinetic energy and see if it is conserved, right? Yeah, so let's go ahead and do that. So we're going to say EK before and then calculate that and see if it's equals to EK after. So EK before will be equals to just the kinetic energy of trolley X, because trolley Y was stationary. So when I have 1.28 and squared, right? So if I just put that in my calculator, I have 1.2 multiplied by 8 squared, and that is 38.4 joules, right? And then EK after, now I have 1.2 multiplied by 4 squared, plus this is for our trolley X, right? Plus the EK for our trolley Y. We have the mass, which is what is the mass again? The mass is 0.5, so we have 0.5 multiplied by the velocity, which we calculated, right? 9.6, and then we square that. So let me just put that in my calculator real quick and see what I get. So multiply by 0.5 multiplied by 9.6 squared, I'm getting 32.64 joules. So since EK before is not equals to EK after, then we deem this collision inelastic, right?
I want to shoot a cannonball up in the air with an initial speed of 10 meters per second. I want to show you something, okay? When I shoot it up with an initial speed of 10 meters per second, that's how the trajectory looks like. Now let me go ahead and increase the speed to 15 meters per second and shoot it up once more, okay? You can see the trend. When I increase the initial speed, the maximum height reached by the ball increases. Now let me go up to 20 meters per second. We can clearly see that there's a trend, but the question really is, can we use this initial speed to determine the maximum height reached by the ball? That's one of the things we address under vertical projectile motion. Let's go ahead and take a look. We're interested on the vertical motion of a projectile. Well, we know what vertical implies. We know what motion is. Let's go ahead and define a projectile. What are we even talking about when we say a projectile? So a projectile is any object that has been given an initial velocity and then only moves under the influence of gravity. If you throw an object upwards, it is a projectile. You've given it an initial velocity and then now it's only moving under the influence of gravity. If you throw it downwards, if you drop it, so on and so on. Before we can talk about graphs and equations of motions, I want us to talk about the path of a projectile. We've already defined what a projectile is. Let's go ahead and explain what vertical projectile motion is all about. What is really going on? Okay, that's what you are interested in. So we have defined projectile. There's one last term that we need to go through: free fall. Free fall is the motion of an object where the only force acting is gravity. So projectile is an object, right? That's how the definition starts for projectile. And then for free fall, it is the motion. That is the difference between the two. So projectile, it is an object that has been given an initial velocity and now moves under the influence of gravitational force only. While free fall is the motion of an object of which the only force acting is gravity. So that is the difference between projectile and free fall. Okay, any object that is a projectile is in free fall, is falling freely, right? It is only being influenced by gravitational force. Now let's talk about the forces that are acting on a projectile. Like we've said, in the absence of friction, the gravitational force of the earth is the only force acting on a free falling body. If you throw a ball upwards, why does it come down? It comes down because it's being pulled downwards by the earth, right? It is accelerating towards the earth. As you can see, if a projectile is moving upward, then it must slow down. And if a project is moving downwards, then it speeds up. If you throw a ball upwards, it's gonna start slowing down until it reaches a maximum height and then starts going down. And if you throw it downwards, if you throw an object downwards, its speed is only gonna increase. The acceleration due to gravity is a constant. All free falling objects have the same acceleration due to gravity. The acceleration is 9.8 meters per second squared downwards. Let's go back to the simulation and see how that will look like. There's two things I want to point out. First, let's focus on the acceleration. The acceleration is always 9.8 meters per second squared downwards at any part of the motion, at the maximum height, at the start of the motion, and as the ball strikes the ground. At any part of the motion, the acceleration is 9.8 meters per second squared downwards. Let me show you how that will look like. I'm going to shoot the ball up with an initial speed of 15 meters per second. If I go ahead and do that, the trajectory will look something like the following. Okay, I'm going to include something. Now I'm going to include the vector that shows you the acceleration. Let me just go ahead and do that. Let me shoot it up once more. As you can clearly see, as the ball goes up and down, there's a vector of which the length is not changing, right? That shows you that the acceleration is constant and it is pointing downwards. That is the acceleration due to gravity, 9.8 meters per second squared. Let's do it again, but this time move a bit more slowly, okay? As you can clearly see, we have the acceleration here. This vector shows you the acceleration. It's pointing downwards from the get-go at maximum height and as we strike the ground. During the entire motion, the acceleration is the same and it is pointing downwards. It is always pointing downwards, okay? You will need to recall that, whether in a long question or in a multiple choice question, but that is essential to remember. A lot of people, they think that the acceleration at the maximum height is 0, but that is not the case. The acceleration is always 9.8 meters per second squared downwards, okay? So let's go. As you can clearly see, the length is not changing, right? And even at the maximum height, we still have an acceleration of 9.8 meters per second squared downwards, okay? Let's carry on. The acceleration is still the same, it's still pointing downwards. That's what I want you to know. You will need to recall that. So, right, we've covered the acceleration. We've showed clearly that the acceleration is always 9.8 meters per second squared downwards. Now let's move from the acceleration and talk about the velocity at maximum height. So, at maximum height, the velocity is 0. You will need to recall that. There's no way around it. At maximum height, the velocity is 0. But again, let me show you, okay? So now what I'm going to do, I'm going to show you a vector that shows the velocity instead of the acceleration and shoot the ball in the air once more. Let me go ahead and do that. As you can clearly see, we have the velocity vector. It is pointing upwards. Let's carry on. And as our object is going upwards, the length of the vector is getting shorter and shorter. That is because the velocity is decreasing, right? As our object gets pulled down by gravity. Let's see. Up until the maximum height where the velocity is 0, you can see here that the arrow becomes non-existent essentially, right? For a split of a second, the velocity is 0 at the maximum height. And then as the object goes down, the velocity will start increasing once more, like we have talked about on the theory, okay? So yes, that is how it looks like. At maximum height all the time, the velocity is equals to 0. Let's just do that once more, okay? There we go. Velocity is decreasing. At maximum height, it is equals to 0. And as the object goes down, it starts to increase. So, for instance, if we are interested in the time taken to reach the maximum height, you would already know that the acceleration is 9.8 meters per second squared, and Vf is equals to 0, the final velocity, right, at the maximum height. That is why it is essential to recall this. I think we can go ahead and solve some problems. In grade 10, you should have talked about motion in one dimension, right? And the equations that accompany that topic. We have Vf is equals to Vi plus A multiplied by the change in time, right? And another formula we have delta x is equals to Vf plus Vi divided by 2 multiplied by the change in time. And then Vf squared is equals to Vi squared plus 2A delta y. Lastly, delta x is equals to Vi delta t plus a half A delta t squared. Instead of delta x, when you're talking about vertical projectile motion, we usually use delta y, right? But the equations still work because vertical projectile motion is still motion in one dimension. So these are the equations we are going to mainly use to answer our questions under vertical projectile motion. In our first example, we have an object that is dropped from a height of 50 meters above the ground. Determine the time it takes for the object to reach the ground. Before we can even attempt answering our question, let's visualize. Let's see how our situation will look like. There we go. We have our object being dropped from a height of 50 meters. We have to use one of those 4 equations. But which equation are we going to use? That is going to be determined by the information we have. So what we need to do in this case is to jot down all the information we have. The information you have is what leads you to the equation you need to use. Let me show you what I'm talking about. When an object is dropped, it simply means that Vi is equals to 0 meters per second. If you drop an object, its initial velocity is 0, okay? We will need to remember this at some point of time. Let's carry on. So we have delta y. Delta y can be equals to 50 meters or minus 50 meters, depending on which direction you take as positive. If you take up as positive and your object is going down, then the displacement is going to be negative. But if you take it down as positive and your object is going down, then your displacement is going to be positive. Unless the question states otherwise, I'm always going to take up as positive. So in this case, my displacement will be minus 50 meters. The object went down and I'm taking up as positive. So I have Vi, I have delta y. Another variable I have is the acceleration. The acceleration is always 9.8 meters per second squared downwards. As I'm taking up as positive, then my acceleration will have a minus sign to show that it is going in the opposite direction. Minus 9.8 meters per second squared. What am I looking for? I'm looking for the time it takes to reach the ground. So these are the 4 variables I have. Which equation can I use when I have these 4 variables? Delta y is equals to Vi multiplied by delta t plus a half acceleration delta t squared. Why am I saying so? I have delta y minus 50 meters. I have the initial velocity, which is 0. Okay, I'm interested in the time, so that is my variable. I have the acceleration, obviously, which is 9.8 meters per second squared downwards. So on this equation, I have all the information I need except from the time, which I'm interested in. So I can go ahead and use this equation. That is how you choose a formula. You don't choose a formula first and then look for variables to substitute. No, it is the variables that lead you to the formula you need to use. So if we go ahead and substitute, the displacement, or delta y, is minus 50 meters. So I'm going to have minus 50 being equals to vi, the initial velocity, that is 0, like we've talked about, multiplied by the change in time. The change in time is our variable. This is what we're looking for. Plus a half, the acceleration is minus 9.8 multiplied by delta t squared. We're going to have minus 50 being equals to 0 multiplied by delta t. That will give us 0. 1 divided by 2 multiplied by minus 9.8 will give us minus 4.9 delta t squared. This is just going to be minus 50 being equals to minus 4.9 delta t squared. We need to divide both sides by minus 4.9. So let me just go ahead and do that. I get 10.2041 being equals to delta t squared. So the rounding off, before the final answer, you want to round off to 4 decimal places, okay? And then at the final answer, that is where you're going to round off to 2 decimal places. And then now we can take square roots on both sides. If I do that, I get 3.19 seconds being equals to delta t. So it will take this object 3.19 seconds to strike the ground or to reach the ground. In this example, an object is thrown vertically upward with an initial velocity of 15 meters per second. Determine the time it takes for the object to reach its maximum height. Let's go ahead and have a sketch. Okay, so we have an object that is being thrown upwards with an initial velocity of 15 meters per second. So we have vi that is equals to 15 meters per second. We want to find the time it takes for the object to reach its maximum height. So delta t is what we're interested in, okay? But it is the time taken to reach maximum height. Like I've said previously, at the maximum height, v is equals to 0. So we have vf being equals to 0 meters per second, okay? That is always true at maximum height. At maximum height, the velocity is equals to 0. But the acceleration is and always is equals to 9.8 meters per second squared. So we have 9.8 meters per second squared. I'm sure you saw it in our previous example that it is important for us to choose a direction we want to take as positive. Either we take up as positive or down as positive. I'm going to take up as positive. So I'm taking up as positive. So from those 4 equations that we have under motion in 1 dimension, which equation can we use in this problem? Based on the variables we have, we can use Vf is equals to Vi plus a delta t. Let me explain why I'm choosing this formula. I have Vf at maximum height, which is equals to 0. I have Vi, which is equals to 15 meters per second. I have the acceleration, which is 9.8 meters per second squared downwards. And the time is what I'm interested in. So this formula works because it has the variables I have and I'm interested in. If I go ahead and substitute, Vf is equals to 0. So we don't have to worry about whether it is positive or negative because it is just 0. And then vi, on the other hand, our object is thrown upwards. We are taking up as positive. So we must substitute that 15 meters per second with a positive sign. So we're going to have 15 plus the acceleration. The acceleration is always downwards. We're taking up as positive. So the acceleration should be minus 9.8. Delta t is what we're interested in. We'll take 15 to the left hand side. If we do that, we're going to get minus 15 being equals to minus 9.8 change in time. If I divide both sides by 9.8 minus 9.8, I have delta t. So let me go ahead and do that. So I'm dividing with minus 9.8 on both sides. If I do that, I'm going to have delta t being equals to 1.53 seconds. With time, we don't have to worry about direction. It is a scalar and not a vector. In this example, we have an object that is thrown vertically downwards with an initial velocity of 15 meters per second. After falling for 6 seconds, it is caught at a lower position. Determine the distance the object traveled during this time. Okay, let's make sense of our situation. So we have an object that is being thrown down at an initial velocity of 15 meters per second, right? And after 6 seconds, it is caught on its way down. What we're interested in is the displacement of the object from the time it is thrown downwards to the time it is caught 6 seconds later. Okay, so let's jot down the information we have. Which variables are we dealing with? Well, we have an initial velocity of 15 meters per second. Before we write all that down, let's decide on the direction. As always, let's take up as positive. If we do that, then we're going to have our initial velocity being equals to minus 15 meters per second. And then it is caught 6 seconds later. So we have our change in time. Delta t is equals to 6 seconds. What else do we have? We are supposed to determine the distance traveled during that time. So we want delta y. That is what we're interested in. We have the acceleration. The acceleration is minus 9.8 meters per second squared. Of the 4 equations we have, which equation can we use to find delta y? It should be easy to see that we can use delta y is equals to vi multiplied by delta t plus a half a delta t squared. Why am I saying so? Delta y is what we're interested in. We have vi and we have the time and the acceleration also. So this is the right equation to use, okay? So let's go ahead and substitute. Delta y will be equals to vi, which is minus 15, multiplied by delta t, which is 6, right? Plus a half, the acceleration is minus 9.8. Delta t is 6, and we square that. So delta y will be equals to, now it's just a matter of putting that in your calculator, and it will be getting minus 266.4 meters. In this example, an object thrown vertically upward from a balcony with an initial velocity of 12 meters per second. It is caught at the same height. Determine the time it takes for the object to be caught. So let's make sense of this situation. We have an object that is being thrown up from a balcony to some maximum height, and then on its way down, it is caught at the same height it was thrown at. So its displacement is equals to 0 meters. Okay, we can deduce that. In order for us to be able to answer this question, there's 2 concepts I need to introduce you to. One concept is that the time it takes from an object to reach its maximum height is the same time it takes for the object to come from maximum height to the starting position. So what am I saying? If we calculate the time it takes to reach its maximum height and multiply that by 2, we would have the time it takes for the object to be caught, right? From the time it is thrown upwards. So that is one thing that is true and that we can utilize in order to answer this question. Another concept you can use is that if it is thrown upwards with a velocity x, when it goes down at the same position, it will have a velocity of minus x. So it's really up to you to choose which concept you want to use in order to answer this question. But let's go ahead and use both. So the first concept, I say that the time it takes to go from starting position to maximum height is the same amount of time it takes to go from maximum position or maximum height to the initial position it was thrown from. Let's jot down our variables and see if we can use this concept. So the initial velocity vi is equals to 12 meters per second. Why is it positive? We're taking up as positive like we always do. So that is where we are starting. vi is equals to 12 meters per second. And then at the maximum height, we know that vf is equals to 0 meters per second all the time at the maximum height. So we have vi and we have vf. Obviously, we have the acceleration. It is minus 9.8 meters per second squared. We're taking up as positive. That's why our acceleration is negative. The time is what we're interested in, delta t. So with these four variables, which equation can we use? Vf is equals to vi plus a delta t. So let's take a look. Vf is 0, vi is 12, plus the acceleration, which is minus 9.8 multiplied by delta t. If we take 12 to the left-hand side, we're going to have minus 12 being equals to minus 9.8 multiplied by the change in time. We need to divide both sides by minus 9.8. So let's just go ahead and do that. Delta t will be equals to 1.2245 seconds. We are rounding off to 4 decimal places because we are not at the final answer. We only round off to 2 decimal places when we are at the final answer. What more do we need to do? Well, not much. Delta t, or the entire time for the motion, is 1.2245 multiplied by 2, which will give you 2.45 seconds. This is the entire time taken for the ball to get thrown upwards and come back down to the initial position until it is caught. So this is one technique we can use. As I'm saying, we can also use the fact that if it is thrown up with a velocity of x at the same position as it is going down, the velocity will be minus x. We can also use this concept. So let's just go ahead and try it out and see if we're going to get the same answer. In this scenario, our vi is still equals to 12 meters per second. What is changing is vf. Vf is equals to minus 12 meters per second. The acceleration is the same as it always is, 9.8 meters per second squared. We're interested in delta t. Which equation can we use? The same equation we used previously. Vf is equals to vi plus a delta t. Vf is minus 12 because when the object is going down, the velocity is going to be negative because we are taking up as positive. So we have minus 12 being equals to vi. Vi is positive 12. So 12 plus the acceleration minus 9.8 multiplied by the change in time. We need to take 12 to the left-hand side. We're going to have minus 24 being equals to minus 9.8 multiplied by delta t. We're dividing both sides by minus 9.8 once more. And if you do that, you're going to get delta t being equals to 2.45 seconds. So as you can see, we end up with the same answer. So in this kind of situation, it's really up to you to decide on which concept you want to use. Let's talk about this special case. How do you deal with a problem where an object is dropped from a moving reference? For instance, a hot air balloon. How do you deal with a case where an object is being dropped from a hot air balloon, like in this case of ours? Well, when an object is dropped from a moving reference, a hot air balloon, for example, the initial velocity will be that of the reference. What does that mean? If you have a hot air balloon that is going up at a constant velocity of 5 meters per second and you drop an object, the initial velocity of that object is going to be that of the reference, of which in our case will be 5 meters per second. But then after dropping it, the acceleration of the object will be 9.8 meters per second squared, irregardless of that of the reference, right? Whether the reference was moving at a constant speed or it was accelerated, as soon as you drop it from the reference, it only takes its initial velocity. The acceleration will be 9.8 meters per second squared. Let's get right to the problem solving and cement the idea. So in this example, a hot air balloon ascends with a constant velocity of 5 meters per second. A ball is dropped from the hot air balloon at a height of 50 meters and falls vertically towards the ground. Determine the velocity of the ball when it reaches the ground. So let's take a look at the initial velocity, because with the moving reference, that is the first thing we should be tackling. So our object is being dropped from a hot air balloon that is ascending, that is going up at a constant velocity of 5 meters per second. So we have VI being equals to 5 meters per second. If you drop an object from a moving reference, its initial velocity is that of the reference. That is why we are saying that the initial velocity of the object is 5 meters per second. But its acceleration is not that of the reference. Its acceleration is and always is 9.8 meters per second squared. Okay? And then it is dropped from a height of 50 meters and is going towards the ground. So when it strikes the ground, its displacement will be 50 meters. Whether it's supposed to be plus 50 or minus 50, we'll take care of that later. Okay? And then what are we looking for? We want to determine the velocity of the ball when it reaches the ground. So that is VF. We want to find VF. With these 4 variables, which equation can we use? We need to use VF squared is equals to VI squared plus 2A delta Y. So VF squared will be equals to, we're taking up as positive. The hot air balloon is ascending, it is going up. So VI for the object is 5 meters per second upwards, okay? So we're going to substitute that as 5. So we have 5 squared plus 2 multiplied by the acceleration. If we're taking up as positive, the acceleration will be negative. So we have minus 9.8. And then delta Y, it is dropped from a height of 50 meters and is going down, right? We're interested at its velocity when it strikes the ground. So the displacement is minus 50 because we are taking up as positive. So we will have VF squared being equals to 1005. What we need to do now is to take square roots on both sides. If you do that, you're going to have 31.7 meters per second downwards. Velocity is a vector, so we always need to give the direction when we get our final answer. As you can see, this is quite an easy one. As soon as you sort out your initial velocity, we just stick to the basics. We write down our variables, we look for an equation, and it is direct substitution. But what if you're not dropping an object from a moving reference, but you're throwing it up or you're throwing it down? For instance, let's say we were not dropping the ball from the balloon, but we were throwing it up at the velocity of 10 meters per second. Then what would be its initial velocity? Will it be that of the balloon, 5 meters per second, that of which we are throwing it at 10 meters per second? Well, let's go ahead and find out. This is another scenario you might come across. A hot air balloon ascends with a constant velocity of 10 meters per second. A ball is dropped from the hot air balloon at a height of 100 meters and falls vertically towards the ground. Very similar to the last example, but let's hear how it differs. Determine the distance between the hot air balloon and the ball 2 seconds after the ball is dropped. Okay, let's conceptualize. Let's have a clear understanding of what is happening in our situation. Our hot air balloon is ascending, it is going upwards, and then a ball is dropped from the balloon. Okay, if the balloon is going up at a velocity of 10 meters per second, then when you drop a ball, it is going to have an initial velocity of 10 meters per second upwards, because if it is dropped, its initial velocity will be that of the reference. So we expect the ball to go up, reach maximum height, and start going down. This is what we expect to see. But what we want is the distance between the hot air balloon and the ball 2 seconds after it was dropped. So this is what we do in this type of situation. Our hot air balloon is still going up at a constant velocity of 10 meters per second. So we will find the displacement of the hot air balloon. After finding the displacement of the hot air balloon, we will find the displacement of the ball. And then with those two values, we're going to be able to find the distance between the ball and the hot air balloon. Let's go ahead and start with the displacement of the balloon. So for the balloon, it is moving at a constant velocity. So our acceleration is equals to 0. And its velocity is 10 meters per second. It's not changing whatsoever. We have the time, which is 2 seconds, and we're interested in the displacement. The equation we need to use with these variables is delta y is equals to vi delta t plus a half acceleration delta t squared. So delta y will be equals to the initial velocity of the hot air balloon, that is 10 meters per second, multiplied by 2, which is the time, plus a half, the acceleration is 0, multiplied by 2 squared. So delta y will be equals to 20 meters. After 2 seconds, the hot air balloon has covered 20 meters. That is the displacement of the hot air balloon. Let's now go ahead and take a look at the displacement of the ball. Its acceleration is and always is 9.8. Its initial velocity will be that of the hot air balloon, 10 meters per second. The time is 2 seconds, and we want to find the displacement. We are going to use this same equation, of which if we substitute, we have delta y being equals to vi is 10, delta t is 2, plus a half, the acceleration is minus 9.8 multiplied by 2 squared. The displacement of the ball is 0.4 meters. We're taking up as positive, okay? So this is the displacement of the hot air balloon, and this is the displacement of the ball. They started at the same position. 2 seconds later, the displacement of the hot air balloon is 20 meters, while that of the ball is 0.4 meters. We're interested in the distance between the two, which will be 20 minus 0.4. The distance is going to be equals to 20 minus 0.4, which is equals to 19.6 meters. Well, in the previous problems we have been solving, A ball is always dropped from a hot air balloon, but that is not always the case. Sometimes it is thrown while it is on a moving hot air balloon. In that case, the velocity of the ball, the initial velocity, is no longer just that of the hot air balloon. It is actually a combination of that of the balloon and that which you are exacting on the ball. Let me show you what I'm talking about. A hot air balloon ascends with a constant velocity of 5 meters per second. A ball is thrown downwards with a velocity of 3 meters per second from the hot air balloon at a height of 50 meters. Determine the velocity of the ball 3 seconds after it is thrown downwards. Let's concentrate on the initial velocity of the ball before we worry about everything else. So the initial velocity of the ball will be that of the balloon plus that at which it is projected at. But we need to pay close attention to the direction. The balloon is going up. So if we take up as positive, then the velocity of the balloon will be 5 plus the velocity at which it is projected. It is projected at 3 meters per second downwards. So if up is positive, down will be negative. So we have 5 plus minus 3, which will give us 2 meters per second. So this is actually the initial velocity of the ball. This is the approach we take all the time when you have a moving reference and you project a ball at a certain speed x. It will be that of the reference plus that at which you project your object at, okay? But paying attention to the direction. It is not that complicated. You just add in the two velocities while respecting that velocity is a vector, not forgetting the direction. Well, we have the initial velocity of the ball. We want to determine its velocity 3 seconds after it is thrown downwards. Let's take a look at the other information we have. The acceleration, obviously, 9.8 meters per second squared. We have the time, delta t, which is equals to 3 seconds. We are interested in the velocity, so we want vf. With these four variables, it's quite easy. We have vf being equals to vi plus a delta t. Vf will be equals to, what is vi? The initial velocity is 2 meters per second plus the acceleration, which will be minus 9.8 if we are taking up as positive. The time, the scalar, always positive, so we multiply that by 3. Minus 27.4 meters per second. Well, this is just 27.4 meters per second downwards. That negative sign tells us that it is downwards because we're taking up as positive. So just like that, we have solved the problem. It's not that complicated. Just a tiny adjustment and we have figured it out. If you were multitasking, this is probably a good time to stop because we have a scenario involving two balls. So let's take a look and see what is happening. A ball is dropped from a height of 20 meters. At the same time, another ball is thrown vertically upward from the ground with an initial velocity of 15 meters per second. Determine the time it takes for the two balls to meet. Let's take a look at the sketch. So we have the ball that is being dropped. Let's call that ball A, okay? And then we have the other ball that is being thrown up at an initial velocity of 15 meters per second. Obviously, they're going to meet somewhere in the middle. What we want is the change in time, is the time it takes for the two balls to meet. Let me show you how we tackle this type of problems. So let's say that A and B, they meet at this point, okay? This is the displacement for ball B, and this is the displacement for ball A. The only thing you need to realize now is that if they meet when A has traveled a distance x, then the distance that B will have traveled is 20 minus x, because they are 20 meters apart from each other. This is the only thing you need to realize. As soon as you make sense of this question becomes extremely simple. So let's go ahead and see how everything else will look like. Let's pay our attention to A first. So for A, we have delta y, which is equals to x. It is being dropped, so vi is equals to 0. The acceleration is 9.8 meters per second squared. What else do we have? We are interested in the time. The equation that we're going to use, we're going to say that delta y is equals to vi delta t plus a half acceleration delta t squared. So delta y is x meters, right? If we take up as positive, then that should be minus x, being equals to vi multiplied by delta t. Vi is 0 multiplied by delta t plus a half. The acceleration is minus 9.8 delta t squared. Minus x will be equals to 0 multiplied by delta t, that will be 0. And then a half multiplied by minus 9.8, that is minus 4.9 delta t squared. We have two variables, x and delta t. So let's call this equation 1 and use ball B to find equation 2. Let me just get rid of this. For ball B, we're going to have delta y being equals to vi delta t plus a half acceleration delta t squared. The displacement of ball B, we've already deduced that it should be 20 minus x. So 20 minus x will be equals to its initial velocity, which is 15 meters per second, multiplied by delta t, plus a half. The acceleration is minus 9.8 delta t squared. So 20 minus x is equals to 15 multiplied by delta t, minus 4.9 delta t squared. So if we make minus x the subject of the formula, we're going to have minus x being equals to 15 multiplied by the change in time, minus 4.9 delta t squared minus 20, equation 2. We can go ahead and equate these two equations, right? If we do that, we're going to have minus 4.9 delta t squared being equals to 15 delta t minus 4.9 delta t squared minus 20. If we take minus 4.9 delta t squared to the left-hand side, we're going to have minus 4.9 delta t squared plus 4.9 delta t squared, which will give us 0. So we have 0 being equals to 15 delta t minus 20. Minus 15t to the left-hand side, minus 15 delta t is equals to minus 20. If we go ahead and divide both sides by 15, we get 1.33 seconds. That is the time it takes for the two balls to meet. Let's see if it really makes sense. Let's substitute delta t into equation 1, okay? We're going to have minus x being equals to minus 4.9 multiplied by 1.33 squared. So minus x is equals to minus 8.67. So x is equals to 8.67 meters. And 20 minus x will be equals to 11.33 meters, which makes sense. But what if the balls are not thrown at the same time? What if one between the two balls is thrown a second later? How do we deal with such a problem? This example is very similar to the one we did before. The only difference is that the second ball is projected 1 second later. Let's go ahead and take a look and see what is happening. So a ball is dropped from a height of 20 meters. 1 second later, another ball is thrown vertically upward from the ground with an initial velocity of 15 meters per second. Determine the time it takes for the two balls to meet. So we can say that this is ball A and this is ball B. So let's go ahead and concentrate on ball A before we can move to ball B. So for ball A, we have the initial velocity. It is dropped. So we have VI is equals to 0. We have the acceleration, obviously, 9.8. What else do we have? Do we have the time? No, we don't have the time. But we have the displacement. We can take the displacement of ball A as a variable k. If we take up as positive, we must substitute k with a negative sign. So the displacement is equals to k. I think that is all we need to see that we can use our equation delta y is equals to vi delta t plus a half acceleration delta t squared. The displacement will be minus k meters because we are taking up as positive. So everything going down should have a negative sign. So minus k is equals to vi, which is 0 multiplied by delta t, plus a half. The acceleration is minus 9.8 t squared. So let's just use t squared instead of delta t. We're going to have minus k being equals to minus 4.9 t squared. We have two variables, k and t. We call this equation 1. And then we can use ball B to find equation 2. We're going to use the same equation for ball B, but we must remember that delta y, the displacement for ball B, is 20 minus k. If we remember that, then we should be good to go. So let me go ahead and erase that and carry on with the problem. This is for ball A, and then for ball B, substituting into the same equation, we're going to have 20 minus k being equals to 15 multiplied by delta t. But ball B was projected 1 second later. So if for A, we're saying that the time is t, for ball B, the time should be t minus 1 because it is projected 1 second later. If it was projected 2 seconds later, it will be t minus 2. So that is how you sort of account for the time being 1 second later. Okay, so t minus 1 plus a half, the acceleration minus 9.8 t minus 1 squared. So 20 minus k will be equals to 15 multiplied by t, that is 15t, minus 15, right? 15 multiplied by minus 1. And then a half multiplied by minus 9.8, that will be minus 4.9. And then t minus 1 squared, that is t squared minus 2t plus 1. So 20 minus k is equals to 15t minus 15 minus 4.9 t squared plus 9.8t minus 4.9. So minus k will be equals to 15t plus 9.8t minus 15 minus 4.9 minus 20. We're taking this from the left hand side to the right hand side. And lastly, minus 4.9 t squared. Minus k will be equals to, what is 15t plus 9.8t? That will give us 24.8t. Minus 15 minus 4.9 minus 20 will give us minus 39.9, and lastly minus 4.9 t squared. This is equation 2. Now we can go ahead and equate equation 1 and 2. If we do that, we're going to have minus 4.9 t squared being equals to 24.8 t minus 39.9 minus 4.9 t squared. Obviously, minus 4.9 t squared and minus 4.9 t squared will cancel out when you take either to one side. So we're going to have 24.8 t minus 39.9 being equals to 0. So 24.8 t is equals to 39.9. If we divide both sides by 24.8, so let me just go ahead and do that. We're going to have 1.61 seconds. If I had to rate the difficulty of this question, I would say that it is a 2 out of 3. It's not that difficult, but it requires you to go ahead of the basics. Let's take a look. The first question, explain the term free fall. Like we've said before, the definition you're supposed to give is the definition on the exam guidelines. It says that free fall is the motion of an object under the influence of only gravity. The motion of an object under the influence of gravitational force, and only gravitational force, nothing else. If that is the case, then an object is in free fall. The second question, calculate the time it takes for ball A to return to its starting point. Let's take a look and see what is happening. So we have a ball A that is thrown vertically upward at a height h with a speed of 15 meters per second. At the same instant, a second identical ball B is dropped from the same height as ball A, as shown in the diagram below. Both balls undergo free fall and eventually hit the ground. Let's take a look at our question once more. Calculate the time it takes for ball A to return to its starting position. So this is where ball A is projected. It goes up to maximum height and starts going down, right? And then on its way down, it is obviously going to pass its starting position. So we want the time taken by the ball to go from its initial position, maximum height, and back to its starting position. Like I've said before, the time taken to go from the starting position to maximum height is the same time taken to go from maximum height to starting position on the way down. So we can basically calculate the time taken to reach maximum height and multiply that by 2 to get the entire time for the motion, starting position, maximum height, and back down to the starting position. That is one way of doing it. There's 2 ways of actually answering this question. I will show you both. So the first way, I'm taking the motion from the starting position to the maximum height. At the maximum height, we know that V will be equals to 0. Vi is equals to 15 meters per second. We have our acceleration being equals to 9.8, and we are interested in the time. With these 4 variables, the equation we need to use is Vf is equals to Vi plus A delta t, of which Vf is 0. Vi is positive 15 if we take up as positive, plus the acceleration minus 9.8 multiplied by delta t. So we have minus 15 being equals to minus 9.8 delta t. We just need to divide both sides by minus 9.8. We're going to have 1.53 seconds being equals to the change in time. But that is not the time we're interested in. 1.53 is the time taken to go from starting position to maximum height. we need to multiply that by 2 to get the entire time for the motion. So our time is 1.53 multiplied by 2, which is equals to 3.06 seconds. There we go. Time taken for ball A to return to its starting position. That is one way of doing it. Let me show you the other way. The other approach involves realizing that if our ball is projected with a velocity of 15 meters per second, when it passes the same point on its way down, it is going to have a velocity of minus 15 meters per second. This is always true. So considering the entire motion, using the same equation, Vf is equals to Vi plus A delta t, Vf would be minus 15. If we consider the entire motion, Vf is equals to 0 if we consider the motion from the starting position to the maximum height. If we consider the entire motion, Vf is minus 15. So we are going to have minus 15 being equals to 15 plus minus 9.8 multiplied by delta t. If we take 15 to the left hand side, we're going to get minus 30 being equals to minus 9.8 delta t. If we divide both sides by minus 9.8, we're going to get 3.06 seconds being equals to the change in time. So that is another way you can use to answer the second question. The third question, calculate the distance between ball A and ball B when ball A is at its maximum height. How much time is taken by ball A to reach its maximum height? We know fully well that it takes 1.53 seconds. So there we go. We have our time. Like I've said previously, when a question is talking about distance, you have to be thinking of displacement. How can you calculate displacement? In 1.53 seconds, ball A reaches its maximum height. So let's take a look. We have ball A going upwards to reach its maximum height. And then ball B is dropped. So it is going downwards. And we're interested in the displacement of A and B in 1.53 seconds. Let's start with the displacement of ball A. The displacement of ball A will be equals to Vi delta t plus a half acceleration delta t squared. So what is the initial velocity of ball A? That is 15 meters per second. With the positive sign, if we take it up as positive, delta t 1.53 plus 1 divided by 2, the acceleration is minus 9.8. Delta t it's 1.53, and we square that. This is equals to 11.48 meters upwards, right? As we can clearly see. And then on the other hand, the displacement of ball B, using the same equation, the initial velocity, it has been dropped, so that is 0. Delta t is 1.53 plus a half. The acceleration is minus 9.8. The time 1.53 squared. This is equals to minus 11.47 meters downwards, right? The negative sign is just showing us that it is moving downwards. So for ball A, we have a displacement of 11.48 meters upwards. And then for ball B, we have a displacement of 11.47 meters downwards. What we want is the distance between the two. So the distance will be equals to 11.48 plus 11.47. Distance is a scalar. You don't have to worry about the minus signs. You just add everything with a positive sign. This will give us 22.95 meters. They're 22.95 meters apart from each other. Calculate the speed with which ball A hits the surface of the water. Let's take a look at what's happening. A man throws ball A downwards with a speed of 2 meters per second from the edge of a window 45 meters above a dam of water. 1 second later, he throws a second ball B downwards and observes that both balls strike the surface of water in the dam at the same time. Ignore air friction. So we have a ball A that is being thrown downwards with an initial velocity of 2 meters per second. And 1 second later, we have a ball B that is also thrown vertically downwards. But they strike the ground at the same time, even though ball B is thrown 1 second later. The question is saying, let's calculate the speed with which ball A hits the surface of the water. Let's go ahead and see what information we have. We have the initial velocity of ball A. It is 2 meters per second downwards. It is thrown from the edge of a window 45 meters above a dam of water. So we have a height which will lead to a displacement of 45 meters. Obviously, we have the acceleration. The acceleration is 9.8. We're interested at the speed at which ball A is the surface of the water. So we want to find VF. With these four variables, we can say that VF squared is equals to VI squared plus 2A delta Y. We're interested on VF. VI, 2 meters per second downwards. If we take up as positive, VI should be minus 2 squared plus 2 multiplied by the acceleration. The acceleration is always downwards, so that is minus 9.8. When a body is in free fall, the acceleration is always 9.8 meters per second squared downwards. And then delta Y is minus 45, right? When it strikes the ground, it is minus 45 meters from the starting point. So we're going to have VF squared being equals to 886. We're going to have VF being equals to 29.77 meters per second. The question says we should calculate the speed, so we don't have to give the direction. If we had to give the direction, it would be downwards because it strikes the ground on its way downwards. That is the first question. Let's take a look at the question that follows. So question 2, calculate the time it takes ball B to hit the surface of the water. Calculate the time it takes for ball B to hit the surface of the water. Okay, 3 marks. So we're not really supposed to be doing a lot of work. Well, we have a problem. With regards to ball B, we know that delta Y is equals to 45 meters downwards because it is projected from the same height. What else do we know? We know the acceleration, obviously, but we have 2 variables. We need a third variable in order for us to be able to find the time taken for ball B to hit the surface of the water. So you cannot use ball B to find the time taken by ball B to hit the surface of the water. You actually have to use ball A. By realizing that ball B is thrown 1 second later, but they strike the ground at the same time. Let me show you how we can use ball A. Using ball A, we have the initial velocity, which is 2 meters per second. Okay, we just calculated the VF above. We know what the acceleration is. We can go ahead and find the time for ball A. So to find the time for ball A, we're going to have VF being equals to VI plus A delta T. Ball A strikes the ground with a velocity of minus 29.77, and then it was thrown with an initial velocity of minus 2 plus the acceleration minus 9.8 multiplied by the time. If we take minus 2 to the left hand side, we're going to get minus 27.77 is equals to minus 9.8 multiplied by delta t. So now it's just a matter of dividing both sides by 9.8. If we divide both sides by minus 9.8, we're going to get 2.83 seconds being equals to delta t. It takes ball B 2.83 seconds to hit the surface of the water, and ball A and ball B strike the ground at the same time. The only difference is that ball B is thrown 1 second later. So how much time is taken by ball B? The time will be equals to 2.83 minus 1. It was thrown 1 second later, which will be 1.83 seconds. That is another sneaky situation you have to be aware of. Let's move to the following question. Question 3. Calculate the initial velocity of ball B. Okay, so let's take a look at the information we have with regards to ball B. We now know that the time taken by ball B is 1.83 seconds. We know the acceleration, 9.8. We know the displacement, 45 meters downwards. And we are looking for the initial velocity. With these four variables, we can say that delta y is equals to vi delta t plus a half acceleration delta t squared. So delta y, that will be minus 45 meters downwards. Vi is what we're interested in. The time is 1.83 plus 1 divided by 2. Acceleration is minus 9.8 and the time is 1.83 squared. So we're going to have minus 45 being equals to 1.83 vi minus 16.4096. Right, so taking minus 16.4096 to the left hand side, we are going to have minus 28.5904 being equals to 1.83 vi. If we divide both sides by 1.83, we're going to have vi being equals to minus 15.62, which is just equals to 15.62 meters per second downwards. That's all the negative sign implies. It implies that the initial velocity is downwards. So there we go. Question 3. Let's go ahead and take a look at question 4. So on the same set of axes, sketch a velocity versus time graph for the motion of balls A and B. Clearly indicate the following on your graph: initial velocities of both balls A and B, the time of release of ball B, and the time taken by both balls to hit the surface of the water. Right, let's go ahead and have our set of axes. This is our time in seconds, and this is our velocity in meters per second. Because ball A strikes the ground in 2.83 seconds, on the time axis, we can have 1, 2, 3. The initial velocity for ball A is minus 2 meters per second. That is at t is equals to 0. So we have a coordinate right there. And for ball B, the initial velocity is 15.62 meters per second downwards. So let's go ahead and have minus 15.62. It is at t is equals to 1. So this is the first point for ball B. And then ball A strikes the ground at 29.77 meters per second downwards. So minus 29.77. That is at t is equals to 2.83. So somewhere here, it's where ball A strikes the ground. Now we just have to go ahead and join the dots. So for ball A, we're going to have something like that. And then for ball B, we're going to have something very similar. They strike the ground at the same time. So the two graphs should end at the same place. So somewhere here is where the two graphs should end. So right, this is our velocity time graph. Let's see if we indicated all that we need to do. Initial velocity for both balls A and B. Initial velocity for ball A, initial velocity for ball B, which is 15.62. The time of release of ball B, that is at t is equals to 1. So we are able to indicate that. The time taken by both balls to hit the surface of the water, t is equals to 2.83, somewhere here. We've indicated that. So there we go. We have all that we need. The marker location is 5 marks. As you can see, we have 1, 2, 3, 4 ticks. The 5th tick is probably coming from ensuring that these two lines are actually parallel to each other. Why do we need the two lines to be parallel to each other? Because the gradient is 9.8 on both lines, the acceleration. This is A and this is B. We need to indicate that. A ball is dropped from the top of a building 20 meters high. Ignore the effects of air resistance. There isn't a lot going on in this question. The first question, define the term free fall. So free fall is the motion. Keyword, motion. Free fall is the motion of an object under the influence of only gravity. The motion of an object under the influence of only gravity. Question 2. Calculate the speed at which the ball hits the ground. So again, our ball is just being dropped from a height of 20 meters. There isn't a lot going on. So we know that VI is equals to 0 meters per second. If it is being dropped, the initial velocity will be 0. We always have the acceleration. 9.8 meters per second squared downwards. We have VI, we have the acceleration. We need one more variable. We need one more data point in order for us to answer this question. We're interested on the speed at which the ball strikes the ground. It is dropped from a height of 20 meters. So we have our displacement as it strikes the ground. Our displacement is 20 meters downwards, of which when we substitute, when we are taking up as positive, we'll put a minus sign. Now what we want is VF, the velocity at which the ball hits the ground. We're going to have VF squared being equals to VI squared plus 2A delta Y. So VF squared will be equals to 0 squared. Well, you might be asking yourself, why are we saying 0 squared? I mean, we know that 0 squared is 0. So is it necessary? Do we really have to do that? Yes, it is necessary. Even though we know that 0 squared is 0, we need to show that, right? There's a mark for substituting. If you don't show that 0 squared is 0, you're not going to get that mark. Plus 2A. A is the acceleration, minus 9.8, right? 9.8 meters per second squared downwards. And then delta Y, the displacement, it is also downwards. So we're going to have minus 20. So VF squared is equals to just 2 multiplied by minus 9.8 multiplied by minus 20. I'm getting 392. So what we need to do at this point is to take square roots on both sides. So VF is equals to 19.7989. If we round that off to 2 decimal places, we're going to have 19.8 meters per second downwards. Well, we don't have to indicate the direction. The question says the speed, so we are only interested on the magnitude and not the direction. But anyway, stories. That is question 2. Let's move to the third question. So the third question, calculate the time it takes the ball to reach the ground. Calculate the time it takes the ball to reach the ground. Let's see how we can do that. We have our initial velocity, obviously, which is equals to 0 meters per second. We have our acceleration, which is 9.8. We have our displacement, which is minus 20, right? And then we have our, what else do we have? Well, we're looking for the time, delta t. We're interested on the time. With these four equations, with these four variables, we can use delta y is equals to vi delta t plus f acceleration delta t squared, of which delta y is minus 20. Vi is 0, so we're going to have 0 multiplied by the change in time, right? Plus f, the acceleration is minus 9.8. Delta t is what we are interested in. Obviously, you can also use the equation Vf is equals to Vi plus A delta t, because we calculated Vf above, but I don't want to use that equation. Let me tell you why I'm running away from that equation. Let's say my answer was Vf is equals to 30 meters per second. This is wrong. We know that Vf is supposed to be 19.8, but let's say I made a mistake and my Vf was 30 meters per second. This will imply that my answer to question 3 will also be wrong, because I'm using a wrong value. So all the time, if I can answer a question without using a value that I calculated myself, I will always choose that approach, right? I always try not use a value that I calculated myself. If I can, most of the time you can't, but in a position like this, I can, so I'm not going to use a value that I calculated myself. I'm going to use the values that I'm extracting from the question itself. It is really helpful. So minus 20, 0 multiplied by the change in time, that's 0. And then a half multiplied by minus 9.8, that is minus 4.9 delta t squared. So what are we doing? We're dividing both sides by minus 4.9. We're going to have delta t squared being equals to 4.0816. So let me go ahead and take square roots on both sides. I'm going to have delta t being equals to 2.02 seconds. There we go. We have the time taken by the ball to reach the ground. Question 4. In question 4, we're supposed to sketch a velocity time graph for the motion of the ball. No values are required, right? It doesn't get easier than this. We're not even supposed to indicate any values. So there we go, our y-axis and our x-axis. And then on the y-axis, we have the velocity in meters per second. On the x-axis, we have the time in seconds. The initial velocity of our ball when t is equals to 0 is 0. And then our ball starts going down, right? So its velocity will be negative right after. That is because we are taking up as positive. We're supposed to have something like that, and that is all we need to do for this question. No values are required whatsoever. The velocity time graph we are asked to sketch in this problem is a thing of beauty. Stick around so I can show you what I'm talking about. The first question, why is the ball considered to be in free fall during its motion? Let's go through the question statement and figure out what's going on. So we have a ball that is projected vertically upwards with a speed of 10 meters per second from point A. The ball hits the ground after 3 seconds. It is in contact with the ground for 0.2 seconds and then bounces vertically upwards, reaching a maximum height of 8 meters at point B. See the diagram below. We can clearly see this is point A where it is projected, and this is the maximum height B it reaches after its first bounce. So the first question, why is the ball considered to be in free fall during its motion? That is because the only force acting on the ball is gravity. When the only force acting on the ball is gravity, we deem it to be in free fall. We deem it to be a projectile. It has been given an initial velocity and now it's moving under the influence of only gravity. That is the answer to the first question. The second question, calculate the height of the building. We want to calculate the entire height of this building. How can we possibly do that? Let's take a look at the information we have. We have the velocity at which the ball is projected at, our VI, which happens to be 10 meters per second. Obviously, we always have the acceleration. It is 9.8 meters per second squared downwards. That is when our object is in free fall. Another piece of information is the time taken to hit the ground. Delta T is equals to 3 seconds. And then what we want is delta Y, the height of the building. The height of the building will be delta Y because the displacement of the ball will give you the height of the building. We don't care about the fact that the ball goes up first. That will not affect our displacement. Our displacement will be the height of the building. That is the only thing we are interested in. Okay, so with these four variables, obviously, we can say that delta Y is equals to VI delta T plus a half acceleration delta T squared. Let's go ahead and substitute. We take up as positive, so VI will be 10, delta T is 3 seconds, plus a half. The acceleration is minus 9.8 multiplied by 3, and we square that. So let's take a look. 10 multiplied by 3 plus a half multiplied by minus 9.8 multiplied by 3 squared. That is equals to minus 14.1. So our height is equals to 14.1 meters. That is the height of our building. Right, let's take a look at the question that follows. Calculate the speed with which the ball hits the ground. Calculate the speed with which the ball hits the ground. So let's take a look at the information we have. We have the initial velocity, which is still 10 meters per second. We have the acceleration 9.8 if it's free falling. What else do we have? We have delta T. Delta T is equals to 3 seconds, and we want to find the velocity at which it hits the ground, which we can take as VF. Okay, with these four variables, pretty much straightforward, right? It doesn't get easier than this. We are gonna have VF being equals to VI plus a delta T. VF is what we're interested in. VI is 10, the acceleration is minus 9.8, and the time is 3 seconds. So let me just go ahead and put that in my calculator. Let me see what I get. I have minus 19.4. So VF is minus 19.4, which is just 19.4 meters per second. We don't have to indicate the direction because the question is asking for the speed and not the velocity. Well, there we go. Let's move to the question that follows. Question 4. So question 4, calculate the speed with which the ball leaves the ground. Okay, so we know that our ball will strike the ground, right? And then after some time, 0.2 seconds to be specific, it is going to leave the ground and then go up until it reaches point B, its maximum height. So when it reaches its maximum height, we know that we're going to have a VF which is equals to 0. The velocity at the maximum height is 0. We're interested in VI, the initial velocity, the velocity as it leaves the ground. Okay, we cannot use 10 meters per second anymore. No. We're interested on the velocity as it leaves the ground. Right, so the acceleration still 9.8, and we are given delta Y, the displacement from the ground to point B is 8 meters. So with these 4 variables, which equation can we use to find VI? VF squared is equals to VI squared plus 2A delta Y. That should be quite easy to see. VF is 0, so we have 0 squared being equals to VI, what you're interested in, plus 2. Acceleration is minus 9.8. Delta Y is 8. Okay, so if we take VI squared to the left hand side, we're going to have minus VI squared. So minus VI squared is equals to minus 156.8. Dividing both sides by minus 1, VI squared is equals to 156.8. Let's take square roots on both sides. We're going to have VI being equals to 12.52 meters per second upwards, right? That is the velocity as it leaves the ground. Well, the question says speed, so let's not indicate the direction because the question says speed. There we go. That is question 4. Let's move to the last question, question 5. The question we're interested in, the velocity time graph. Let's go ahead and take a look. So the velocity time graph, the question is saying draw a velocity time graph for the complete motion of the ball from A to B. Show the following on the graph: the magnitude of the velocity with which it hits the ground, the magnitude of the velocity with which it leaves the ground, and the time taken to reach the ground, as well as the time at which it leaves the ground. Okay, right, let's go ahead and see how we can possibly do that. We need our set of axes, obviously. So there we go. We have our y-axis and we have our x-axis. In our y-axis, we have the velocity, obviously, in meters per second. And on the x-axis, we have the time in seconds. So this is velocity in meters per second. So let's go ahead and fill out the x-axis. It hits the ground after 3 seconds. So let's say 1, 2, 3, 4, 5, 6. Okay, and then its initial velocity, we're taking up as positive. Its initial velocity is 10 meters per second. That is its initial velocity. Okay, so it starts here, and then gravity is acting against our motion, right? Our object is going up, gravity is going down. So the velocity decreases until it reaches its maximum height. Well, we don't have the time taken to reach maximum height, but we have the time taken to hit the ground. But what is the magnitude of the velocity as it hits the ground? We calculated that above, so let's go ahead and find out. The velocity is 19.4 meters per second, and then as it leaves the ground is 12.52. Okay, so let's go ahead and have that. As it hits the ground, the velocity is minus 19.4. okay, so if 10 is somewhere here, then minus 19 should be somewhere here, right? So in 3 seconds, this is what we have. Our object is striking the ground. So let me just go ahead and join those 2 dots for the sake of clarity. It is in contact with the ground for 0.2 seconds. It then leaves the ground with a positive velocity because it is going up with a velocity of 12.52. Let's say this is 12. So somewhere here is where it leaves the ground with a velocity of 12.52 meters per second upwards. So we need another data point somewhere here. And then it is going to go up until it reaches maximum height. Okay. We don't have the amount of time taken to reach maximum height, but that doesn't matter. Okay. There's no mark for that if we didn't calculate it. So yes, we're going to have something like this. But as you can see, there's a gap here what do we do in a situation like this? We have to join the two lines with a dotted line. We have to join the two lines with a dotted line. So something like this. Right, there we go. This is our velocity time graph. So let's see if we included all that we needed to include. The magnitude of the velocity with each it hits the ground. Here we go, minus 19 point something, okay? And then the magnitude of the velocity with which it leaves the ground, we have indicated it, 12.52. And then the time taken to reach the ground, 3 seconds, we have indicated that. And then as well as the time at which it leaves the ground. We're supposed to indicate the time at which it leaves the ground. This is another special problem. Let's go ahead and take a look. The first question, we are supposed to calculate the time taken for stone A to reach its maximum height. But before we can do any of that, let's go through the question statement so I can show you what is special about this problem. We have a stone A which is projected vertically upwards with a speed of 12 meters per second from a height h above the ground. At the same instant that stone A is projected upwards, stone B is thrown vertically downwards from the same height, right, at an unknown speed v downwards, as you can clearly see from the sketch. So that is the information we have. The question, calculate the time taken for stone A to reach its maximum height. So with regards to stone A, we know that it is projected vertically upwards with an initial velocity of 12 meters per second. We know the acceleration, like we always do in free fall, that is 9.8 meters per second squared. Apart from the acceleration, we have VF, because we are interested on the time taken to reach maximum height. We know that the velocity at the maximum height is 0. We are interested on the time, delta t. With these four variables, we can use VF is equals to VI plus a delta t. VF is 0 because we are interested in the maximum height. VI is 12 meters per second with the positive sign because we are taking up as positive, plus the acceleration minus 9.8. That is because the gravitational acceleration is downwards and we are taking up as positive. Delta t is what we are interested in. We are obviously going to take 12 to the left hand side. We're going to have minus 12 being equals to minus 9.8 delta t. It should be quite easy to see what we need to do at this point. We have to divide both sides by 9.8, minus 9.8, okay? So we're going to have delta t being equals to minus 12 divided by minus 9.8. If you put that in your calculator, you're going to get 1.22 seconds. So it takes 1.22 seconds for stone A to reach its maximum height. That is quite basic. There's nothing special we're doing there. But take a look at the question that follows. Question 2. So question 2, it says that when stone A reaches its maximum height, the speed of stone B is 3v. They are projected at the same time, right? When stone A is being projected upwards, stone B is being projected downwards with an initial velocity of v. But when stone A reaches its maximum height in 1.22 seconds, the speed of stone B is 3v. The question is saying calculate the speed v with which the stone B is thrown downwards. As you can see, this is not a usual style of questioning we come across. We have to deal with variables, right? Vi, the initial velocity of our stone B, is v, and then Vf is 3v, right? At the instant stone A reaches its maximum height, when delta t is equals to 1.22 seconds, the final velocity of stone B is 3 volts. So we have vi, which is v, we have vf, which is 3v, we have delta t, which is 1.22 seconds, and we also have the acceleration, 9.8 meters per second squared downwards. We want to find the variable v. How can we do that with these four variables? Again, vf is equals to vi plus a multiplied by delta t. I'm being guided by the variables, okay? So the most important thing in questions like this is to not panic. As soon as people see variable, they usually just conclude that, no, I've not solved a problem like this before, we didn't cover this in class, it's so unfair, I'm just gonna skip it. But no, this is a very basic question. There's just one twist to it that you need to realize. As soon as you break down this question, it will be relatively easy. It's not that difficult, right? You just need to take your time, go through the basics, pick the formula, and solve your problem. Let's carry on. Vf will be minus 3v. That is because we are taking up as positive, right? And then Vi will be minus v. Yeah, because it is a variable, it doesn't mean that now we have to throw all the physics out of the window. No. We still have to respect the physics. We still need to respect scalars, treat them as such, treat vectors the way they need to be treated, putting into consideration the direction, so on and so on. Plus the acceleration, which is minus 9.8. The time is 1.22. So we're going to take minus v to the left hand side, is going to be plus v. So we're going to have minus 2v being equals to, what is minus 9.8 multiplied by 1.22? That is minus 11.956. Clearly, we need to divide both sides by minus 2. And when I do that, I get 5.98 meters per second. This is the speed v with which stone B is thrown downwards, okay? Not difficult at all. You just need to identify your initial velocity, your final velocity, and maybe the time was also a bit tricky because the speed of stone B is 3v when stone A is at its maximum height. And we know fully well that stone A is at its maximum height in 1.22 seconds. So I guess it was also a bit tricky to identify that the time is supposed to be 1.22, but apart from that, we're just sticking to the basics. Okay, the question that follows, question 3. At the instant stone A passes its initial position on its way down, stone B hits the ground. Calculate the height h. We're supposed to calculate the height h. Right, so let's see. We can use stone A or we can use stone B. I think both can work, but let's try using stone B. If we're using stone B, our VI is going to be equals to 5.98 meters per second downwards, right? It's what we just calculated above, the value of V. And then the acceleration, 9.8, obviously. And then we're supposed to calculate the height h. The displacement of stone B as it strikes the ground will be the height h, right? So delta y, it's what we are interested in. Which other variable do we have? We actually have the time. Let me show you how. Let's take a look at the question again. At the instant stone A passes its initial position on its way down, stone B hits the ground. Calculate the height h. We've talked about this previously, right? If it takes 1.22 seconds to go from initial position to the maximum height, this is 1.22 seconds. It will take 1.22 seconds to go from the maximum position to the initial height once more. It will also take 1.22 seconds. So the time taken for the entire motion is 1.22 multiplied by 2. And we know fully well that that is the time taken by stone B to strike the ground. As stone A passes its initial position on its way down, stone B strikes the ground. Okay, so we have the time, but it is not easy to see. You have to think about it a bit. But we've covered this in our previous problems, so it should not be an issue whatsoever. You should be able to answer this question using just the knowledge we have covered. Right. So let's see. If we have delta t, vi acceleration delta y, we can obviously say that delta y is equals to vi delta t plus a half acceleration delta t squared. So vi, that is minus 5.98. I'm always taking up as positive unless stated otherwise. And then the time is 1.22 multiplied by 2, which will be 2.44. So we have 2.44. Always positive is a scalar. Plus a half, the acceleration is minus 9.8. The time is 2.44. And we square that. This is equals to minus 43.7638. So h will be equals to 43.76 meters. That is the height h, which we are supposed to calculate. Question 3. Let's move to question 4. Velocity time graph. Let's go ahead and take a look. So sketch velocity time graphs for the complete motions of stone A and B on the same set of axes. Label your graphs for stones A and B clearly. Show the following on the graphs. The time taken for stone A to reach its maximum height, 1.22 seconds, and the velocity with which stone B is thrown downwards. Let's say 0.5, 1, 1.5, 2, 2.5. Okay, let's use that time interval. Okay, I'm deciding to use this time interval because the entire motion of both balls takes 2.44 seconds. So we're supposed to indicate the time taken for stone A to reach its maximum height. It takes 1.22 seconds. We know that for sure. But its initial velocity is 12 meters per second. So let's see, 12 meters per second is somewhere here. So this is its initial position, its initial velocity when t is equals to 0. And then in 1.22 seconds, its velocity is equals to 0, right? Because it reaches its maximum height. It starts going down until it passes its initial position when t is equals to 2.44. Okay, we know that for sure. And then its velocity should be minus 12 when it passes its initial position. So let's go ahead and join those dots. There we go. This is the graph for stone A. Let's go ahead and have the velocity time graph for stone B. Its initial velocity is minus 5.98. Let me reach 5. Okay, yes, minus 5.98. So if this is minus 6, then somewhere here, minus 5.98. In 2.44 seconds, its velocity is 3v, right? We should be very close to minus 18. So let me just draw that line. This is where our stone B ends up. So there we go. We have the velocity time graphs for the two stones, A and B. Determine the time that the ball is in contact with the floor before the first bounce. That is the second question. This is a very special problem, okay? We are given a position time graph, as you can clearly see on the left hand side, and we're supposed to answer questions based on that position versus time graph. So let's go ahead and take a look and see what's happening. A small ball is dropped from a height of 2 meters and bounces a few times after landing on a cement floor. Okay, we can see clearly from the position time graph that it is indeed dropped from a height of 2 meters. Okay, it is dropped, so that gives us the velocity. We now know that the initial velocity at 2 meters above the ground is 0 meters per second. Okay, let's carry on. Ignore air friction. If we're ignoring air friction, then as soon as it is dropped, it is in free fall. It is a projectile. The only force acting is gravitational force. The position time graph below, not drawn to scale, represents the motion of the ball. Right, that's all we have. Let's go through the question once more. Determine the time that the ball is in contact with the floor before the first bounce. Okay, so our ball is being dropped from this point and it starts going down. Okay, it strikes the ground at this point when t is equals to 0.64, and then it leaves the ground at t is equals to 0.67. So between 0.67 and 0.64, our object is in contact with the ground. So how much time does the object spend in contact with the ground? We're going to have t being equals to 0.67 minus 0.64. Okay, so what is 0.67 minus 0.64? We have 0.03. So t is equals to 0.03 seconds. The ball spends 0.03 seconds in contact with the ground. That is the answer to the second question. Okay, the third question, on the other hand, determine the time it takes the ball to reach its maximum height after the first bounce. What we are interested in is the time taken by the ball to reach its maximum height after the first bounce. So this is what we are interested in. How much time does it take after leaving the ground to reach the maximum height? That's what you are interested in. Okay, there's a couple of ways we can answer this question. We can use equations of motions, or we can use the fact that if it takes 1 second to go from the ground to maximum height, it will also take 1 second to go from maximum height and strike the ground. So what I'm proposing here is that this is 1.9 and this is 0.67. We can say t is equals to 1.9 minus 0.67. So let me just go ahead and put that in my calculator. I'm getting 1.23 seconds. So this is the time taken to leave the ground, go to maximum height, and strike the ground again. So what we're proposing is that the time taken to reach maximum height will be equals to, from here to here, it's 1.23. So going from here until maximum height will be half of that. And then maximum height back to striking the ground will be half of that because the acceleration is the same. So delta t will be equals to 1.23 divided by 2. So what is 1.23 divided by 2? I'm getting 0.62 seconds. So if we use that fact, we know fully well that this is correct, right? We're not making an assumption. We know fully well that it is correct. We have seen it time after time that it is correct. Also, if you think about it from an acceleration point of view, you should also see that it holds. So that is one way of doing it. We end up with an answer of 0.62 seconds. Let's do the question that follows. So question 4, we are supposed to calculate the speed at which the ball leaves the floor at the first bounce. So this is where the ball leaves the floor at the first bounce. Okay, if we only consider this part of the motion, you will realize that vi is what we are interested in. Vf is equals to 0 at the maximum height. Delta y is the displacement, which is 1.85 meters, as you can clearly see right here. So there we go, we have delta y 1.85 meters. The acceleration obviously is 9.8 meters per second squared downwards. With these 4 variables, we can say that Vf squared is equals to Vi squared plus 2a delta y. Vf is 0, so we have 0 squared being equals to vi. So that is vi squared plus 2. The acceleration is minus 9.8. We take it up as positive, and the displacement is plus 1.85. So 0 squared, that is 0, obviously. So we're going to have 0 being equals to vi squared. What is 2 multiplied by minus 9.8 multiplied by 1.85? That is minus 36.26. So we have 36.26 being equals to vi squared. What we need to do here is to take square roots on both sides. If I do that, I am getting 6.02 meters per second being equals to vi. The question says the speed, so we don't have to indicate the direction. That is all that we need to indicate. So there we go. That is question 4. Let's go ahead and do question 5. In question 5, we're supposed to calculate the time t indicated on the graph for 6 marks. So let's just get rid of all this for the sake of clarity. We're interested on the time t, and that is for 6 marks. Let's make sense of that. This is the part of the motion that I'm considering. If you pay attention to that part of the motion, you should realize fairly quick that vi is equals to 0, because this is maximum height. So the initial velocity there should be 0 meters per second. Okay, so we have the initial velocity. We also have the acceleration, like we always do in free fall, 9.8. So vi, acceleration. What else do we have? We have the displacement. When we strike the ground, the displacement will be 1.2 meters downwards. You can clearly see here that the position is 1.2 meters above the ground. So vi, acceleration, delta y. Let's find delta t. Okay, but there's a twist to this delta t that we are looking for. But let's figure it out first, and then I'm going to show you what I'm talking about. So with these variables, which equation can we use? Okay, I think delta y is equals to vi delta t plus I have acceleration delta t squared should hold up really well. So there we go. We have delta y 1.2 meters downwards, because we're starting from maximum height until we strike the ground. So we're going to have minus 1.2. vi is 0, maximum height. Delta t is what we're interested in, plus I have acceleration is minus 9.8. Delta t, so what we're interested in, delta t squared. So minus 1.2 is equals to 0 multiplied by delta t, that is 0. So that falls away. I have multiplied by minus 9.8, that is minus 4.9 delta t squared. So what we need to do is to divide both sides by minus 4.9. So let me just go ahead and do that. I am getting 0.2449. I'm rounding off to 4 decimal places because I'm not at the final answer. This is equals to delta t squared. So let's go ahead and take square roots on both sides. When I do that, I get 0.49. 0.49 seconds is equals to delta t. Right, let's go ahead and make sense of this 0.49 seconds. Like I said, there's a twist to it. We're looking for t on the position time graph. These right here. We're not looking for delta t from maximum height until we strike the ground. Okay, so let's make sense of that delta t. We know for sure that from maximum height until we strike the ground is 0.49 seconds, right? But that also implies that from the ground until maximum height, we took 0.49 seconds. So from 1.97 to t is 0.49 plus 0.49. So t is equals to 1.97 plus 0.49 multiplied by 2. So what is 1.97 plus 0.49 multiplied by 2? I'm getting t being equals to 2.95 seconds. Okay, there's other ways you can play around with how you are getting to 2.95 seconds, but whatever way, if it makes sense, you should get 2.95 seconds. This is the answer, right? You can take a different approach. I'm quite sure there's quite a few ways you can get to t being equals to 2.95, but ultimately we should be getting t is equals to 2.95 seconds. Well, this was an interesting question. Until I see you next time. Is the object's acceleration at its maximum height upward, downward, or zero? When the only force acting on an object is gravity, the acceleration always is 9.8 meters per second squared downwards. We covered that at the very start of our series where we use the simulation. So the answer here is downward. When the only force acting on an object is gravity, the acceleration will always be downward, irregardless of the part of the motion. Whether we at the start, whether we at the maximum height, it doesn't matter. The acceleration is 9.8 meters per second squared downward. The only thing special about the maximum height is that the velocity is 0, but the acceleration doesn't change. It is still 9.8 meters per second squared downward. So that is the first question. The second question, calculate the magnitude of the velocity at which the object strikes the ground. Well, let's go through our question statement. An object is projected vertically upwards at 8 meters per second from the roof of the building, which is 60 meters high. It strikes the balcony below after 4 seconds. The object then bounces off the balcony and strikes the ground as illustrated. We are looking for the magnitude of the velocity as the balcony strikes the ground. We have the velocity at the top of our building when our object is projected, which we can use as our VI. So we have VI being equals to 8 meters per second. We have VF, which is what we're looking for. The acceleration is and always is 9.8. On the other hand, the change in time we're given is 4 seconds. The object strikes the balcony after 4 seconds. Which equation can we use with these 4 variables? Well, VF is equals to VI plus A delta T. Taking up is positive. If we substitute, we're going to have 8 plus the acceleration, which is minus 9.8 multiplied by delta T. It's a scalar, so it's always positive. Minus 31.2, which is just equals to 31.2 meters per second. The question says, let's calculate the magnitude. So we don't have to worry about the direction. We can just leave the answer as it is. If we were looking for the velocity, we would have to give the direction, which would be downward because our projectile strikes the balcony on its way down. But here we are only interested on the magnitude, so we can leave it like that. That is the second question. Let's move to the third question. In the third question, we are supposed to calculate the height h of the balcony above the ground. As soon as I hear height, I'm thinking displacement. Some way, somehow, I have to calculate the displacement. Because how can you calculate height without calculating displacement, right? So that is a tip right there. When the question talks about height, you are definitely going to calculate the displacement at some point of time. So we want the height of the balcony from the ground to the balcony. This is the height we're interested in. But let's take a look at the information we have. What we have is the initial velocity at the top of the building, and the velocity as our object strikes the balcony. With that information, we can find the height from the top of the building to the balcony. If we say that the height from the top of the building to the balcony is k, then the height from the ground to the balcony will be 60 minus k, because from the ground to the top of the building is 60 meters like we are given. So we can just find the displacement from the top of the building to the balcony and use that to find the height. Let me go ahead and show you what I'm talking about. Our initial velocity is 8 meters per second. Our change in time is 4 seconds. Our acceleration is 9.8 meters per second squared. We are interested in the displacement. With these 4 variables, which equation can you use? Well, we can say that delta y is equals to vi delta t plus a half acceleration delta t squared. But because we have vf in the equation we just solved, you can also use vf squared is equals to vi squared plus 2a delta y. But let's carry on and just use this one. Vi, that is 8, we're taking up as positive. Change in time 4 plus a half. Acceleration is minus 9.8 4 squared. This is equals to minus 46.4 meters. So this right here is 46.4 meters. The displacement of our projectile is minus 46.4 because we are taking up as positive. So if it is going down, the displacement must be negative. But from the top of the building to the balcony, it will be 46.4 meters. Our height will therefore be equals to 60 minus 46.4, which is equals to 13.6 meters. So the balcony is 13.6 meters above the ground. Questions like this one will always be there in the exam. Questions where you have to analyze the situation in hand. A situation that you'll probably be coming across for the very first time. So don't be comfortable and just think that it's just a matter of writing down the variables and substituting. If you like this video, you will definitely love my course. Go ahead and click the link on my bio and you will land on this page. You will not only find the past exam questions, but introduction videos where I break down complex concepts into small pieces that are easy to digest. It is very important in grade 12 to stay ahead of your teacher, and this is what this course is for. It's very easy to navigate through the course as videos are arranged into collections. You can clearly see that we have electrostatics, work energy and power, Doppler effect, so on and so on. Do you maybe need help with study tips and creating your own timetable? We can talk about that inside the course and I can help you out. It doesn't even take a minute to join. Can't wait to hear from you. This is a topic test on Newton's laws and vertical projectile motion. Let's go ahead and take a look. The first question, 1.1. An object is thrown vertically upwards. Which one of the following regarding the object's velocity and acceleration at the highest point of its motion is correct? Ignore the effects of friction. So we're interested on the velocity and acceleration at the highest point, at the maximum height, right? In other way. So we know fully well that at the maximum height, the velocity is equals to 0. But the acceleration of a projectile is always 9.8 meters per second squared downwards. So we are looking for the option that says the velocity is 0 and the acceleration is downwards, right? 9.8 meters per second downwards. That seems to be option D. So the answer to 1.1 is D. the velocity is 0 at the maximum height, and the direction of the acceleration is downwards. Okay, let's take a look at 1.2. So 1.2, a learner drops an object from the top floor of a high building. 1 second later, the learner drops another identical object from the same position. As both objects are in free fall, the distance between them will. Right, the first option, A, says it will increase. The second option says it will decrease. And then we have C, which says initially increase, then decrease. That does not make any sense, right? And then D says remain the same. So without performing a calculation, we should be thinking about increase or remains the same. There is no way the distance between the two objects will decrease when they are both in free fall. It does not make any sense, right? And even initially increase then decrease, it does not make sense. You are stuck between increase or remain the same. But which one is the correct answer here? There's two ways we can get to the correct answer. One way is to actually calculate and see if the distance increases or remains the same, right? And then another way is to just use the theory. What do I mean by that? So we can say delta y is equals to vi delta t plus a half acceleration delta t squared. These two objects have been dropped, right? So vi is 0. So vi multiplied by delta t, that is just going to give us 0. So we end up with having delta y is equals to a half acceleration delta t squared, right? So we can clearly see that delta y is directly proportional to delta t squared, right? Delta y is not directly proportional to delta t. It is directly proportional to delta t squared. If it was directly proportional to delta t, the distance would remain the same. But we can clearly see that it is directly proportional to delta t squared. So the distance between the object actually increases. The distance between the two objects would actually increase. So that is one way we can reach that conclusion through theory. Another way we can reach that conclusion is through calculation. Let me show you how. So we have object A and object B. Let's just tabulate so that you can see what I'm talking about. So let me, right, so this will be the distance between the two objects. Okay, so let's do it like this. Ball A is dropped first, right? And then ball B is dropped after 1 second. So delta y for ball A after 1 second will be a half acceleration delta t squared. This is obviously equals to a half, let's say 9.8 multiplied by 1 squared. So 1 squared is just 1, 9.8 divided by 2 is 4.9. So after 1 second, A has traveled 4.9 meters, while B has traveled 0 meters, because it is only projected after 1 second. So what is the distance between them? The distance between them is delta x. Right, let's take a look at what happens after 2 seconds. So it's just a matter of substituting 2 there, right? So we get 4.9 multiplied by 4, which is 19.6, right? Oh, the distance between the two objects will be 4.9 meters here. So after 2 seconds, A would have traveled 19.6 meters, while B, that has only been traveling for 1 second, would have traveled 4.9 meters, right? So now we have 19.6 minus 4.9. Well, we can just say 19.6 minus 5, that will be 14.6, and then we add 0.1, so 14.7, right? So somewhere around the neighborhood of 14.7. So you can clearly see that the distance between the object the two objects does not remain the same. It keeps on increasing. Even when you make the third calculation here, you will see that the distance between the two of them will just keep on increasing. Okay, there we go. That is 1.2. Right, let's take a look at 1.3. 1.3, a stone is dropped from a certain height above the ground. Which one of the following combinations is true while the stone is moving downwards? It is dropped and then it's just moving downwards. Okay, net force acting on the object remains the same. Obviously the net force will remain the same because after it is being dropped, the only force acting on the object is gravitational force, right? So the net force is remaining the same there. It's not going to change. It's just gravitational force. So now we are only looking at A and C, right? Mechanical energy of the stone. The mechanical energy of the stone will also remain the same, right? Don't forget that the mechanical energy is equals to the sum of the kinetic energy plus the sum of the potential energy. And then in a closed system, the mechanical energy is conserved in a closed system, right? So we are ignoring the effects of air resistance, and the only force acting on the object is gravitational force. So the mechanical energy is going to be conserved, so it is going to remain the same. So the answer to 1.3, that is C. Okay, let's take a look at question 2. A box of mass 0.5 kg is projected vertically downwards at a velocity of 8 meters per second towards the floor from a height of 1.8 meters. The box is in contact with the floor for 0.01 seconds before it is picked up. Ignore the effects of air friction. If you like this video, you will definitely love my course. Go ahead and click the link on my bio and you will land on this page. You will not only find the past exam questions, but introduction videos where I break down complex concepts into small pieces that are easy to digest. It is very important in grade 12 to stay ahead of your teacher, and this is what this course is for. It's very easy to navigate through the course as videos are arranged into collections. You can clearly see that we have electrostatics, work energy and power, Doppler effect, so on and so on. Do you maybe need help with study tips and creating your own timetable? We can talk about that inside the course and I can help you out. It doesn't even take a minute to join. Can't wait to hear from you. Right. And then the first question, 2.1, is the box in a free fall directly after being projected? Write down only yes or no. Give a reason for your answer. So after it is thrown vertically downwards, it will immediately be in free fall. So the answer is yes. And why are we saying so? The only force acting on the object is gravitational force, right? That is why we are saying it is in free fall. Okay, 2.2. Write down the magnitude and direction of the acceleration of the box immediately after it is projected. So it is already in free fall, just like we said in 2.1. So what is going to be the acceleration? Well, the magnitude is 9.8 meters per second squared, and the direction is downwards, right? There we go. For some reason, some people, sometimes when they are writing the SI unit of acceleration, they will say meters per second when it is clearly meters per second squared. Why do you do that? Well, 2.2, let's take a look at 2.3. 2.3.1. We are looking for the magnitude of the velocity with which the ball hits the floor. Okay, so it is projected downwards and then there it goes until it reaches the floor, right? So let's take a look at the information that we have so that it guides us in order to pick a formula, right? It is the information that we have that guides us, that leads us to the formula. So what do we have? We have acceleration, obviously, 9.8 meters per second squared all the time in free fall. We have the initial velocity, it is projected with 8 meters per second. Or we have delta y, right? The height of, well, it's not a building or anything, it's just been projected. But we have delta y, and then now we're looking for VF. Okay, so it should be easy to see that 2.3.1, the magnitude of the velocity with which it strikes the ground, VF squared is equals to VI squared plus 2a delta y. We have VI, we have acceleration, we have delta y, we are looking for VF. So we're going to have VF squared being equals to, I'm taking up as positive, right? So my VI is going to be minus 8 squared plus 2. My acceleration minus 9.8. And then delta y is minus 1.8. The object is going downwards. The acceleration is downwards. The displacement is downwards. And I'm taking up as positive. So everything else should be positive. Okay. So obviously, we're going to put that in our calculators and take square roots on both sides. We're going to have VF being equals to 9.96 meters per second. Right. So the final velocity is 9.96 meters per second. The magnitude of the final velocity. I will tell you why I'm making emphasis in about a minute or so. So let's do 2.3.2. So 2.3.2, the time it takes the box to hit the floor. Okay, so take a look at this. I have VI, I have calculated VF, I have the acceleration, I'm looking for delta t. Seems quite straightforward. So I'm going to say VF is equals to VI plus A delta t. So take a look at this. VF is 9.96. VI is minus 8 because it's downwards, right? Plus the acceleration, which is minus 9.8 multiplied by delta t. This is the mistake that most people make with this kind of equations. Because take a look at this. 2.3.1 says the magnitude. That's why we didn't care about the direction when we calculated VF. But now we are using that velocity in 2.3.2 as we are attempting to calculate the time. But we have to account for the fact that it is 9.96 meters per second downwards. There's supposed to be a minus sign there because we are taking up as positive, right? So make sure you don't miss those kind of things, right? Because I'm sure there is some people that will make that mistake. Okay, anyway, stories. Let's carry on. We're gonna have delta t being equals to minus 9.96 plus 8, everything divided by minus 9.8. We put that in our calculators and we get 0.2 seconds. So there we go, 2.3.2. Let's take a look at 2.3.3. We are supposed to calculate the net force exerted by the box on the floor. Okay, so let's take a look at what happens. Obviously, the box strikes the ground with the velocity we calculated in 2.3.2. Strikes the ground with a velocity of 9.96 meters per second. And then, does it leave the ground? Let's go back to the equation statement and see what happens. It is said that the box is in contact with the ground or with the floor for 0.01 seconds before it is picked up. Right, so it seems like ultimately our object remains resting on the ground. So we have a velocity of 0 meters per second. What are we looking for? We're looking for the net force. What do we have? We do have the mass of the object, right? The mass of the object is said to be 0.5 kgs. What is F net? F net is equals to ma. We have the mass, so can we find the acceleration? Maybe that is what the question is actually saying. Let's see if we can find the acceleration. We have the initial velocity with which it strikes the ground. We have the velocity after it strikes the floor. It remains on the floor before it is picked up in 0.01 seconds. We have delta t. We can find the acceleration, right? Because it is not in free fall as it strikes the ground, right? So we can also say the acceleration is 9.8. Doesn't make any sense. You would just calculate the weight of the object if you do that. So we're going to have VF being equals to VI plus A delta t. Let's keep taking up as positive. So we're going to have minus 9.96 being equals to, well, that is not the final velocity. The final velocity is 0. So we have 0 being equals to minus 9.96 plus the acceleration, which is well, give us the acceleration. I'm used to saying acceleration is minus 9.8. but in this question we're actually looking for the acceleration. The time with which it is in contact with the ground, that is 0.01 seconds. So the acceleration is going to be 9.96 divided by 0.01. Right, this is equals to 996 meters per second squared. Right, we have the acceleration. So F that will be equals to ma, what is the mass, 0.5, the acceleration 996 meters per, oh well, I don't have to put the SI unit there. What am I doing? Right, so there we go. So 0.5 multiplied by 996. Actually don't have a calculator, so I have to do this by hand. So if we divide 900 by 2, we'll get 450, and then 900, then we have 96. When we divide 96 by 2, what do we get? We get 48. So 50 plus 48, 498. Yes, okay. So there we go. We have 498 newtons. Right, 498 newtons. Does it say the force? Yes, the force, the net force exerted by the box on the floor. So we have to say downwards. Right, so that is 2.3.3. What about 2.4? Sketch an acceleration time graph for the motion of the box. No indication of values is required. Right, okay, so let's do that. So the y-axis and the x-axis. Okay, so this is the acceleration in meters per second squared. So I want to take up as positive, right? And then this is time in seconds. So if I take up as positive, for the part of the motion where it is in free fall, we are gonna have minus 9.8, but it strikes the ground, and there's some acceleration when it strikes the ground. For that is 0.01 seconds. So what is the acceleration? Therefore the acceleration is 996. Okay, so where am I gonna put 996 here? Where am I gonna put 996? Let me just put it here, right? This is not the drawn to scale. Right, so with my ruler, I want dotted lines. It is in contact with the floor for 0.01 seconds. So the angle must not be 90, something like 89 makes sense, because we have to show that it was not in contact with the ground for 0 seconds. Yeah, so something like that. Oh well, why is that turning into an error? Yeah, so that is what we have actually. That is what we're supposed to have as far as the acceleration time graph is concerned, right? There's this part here for the part of the motion where it is in contact with the ground. Yeah, but funny enough, on the memo, I doubt they would include that part. But when we're sticking to the physics, right? No shortcuts. We're supposed to have that part. Okay, 2.4. Question 3. Okay, let's take a look. So we have question 3 and question 4 remaining. Right. Question 3. If you like this video, you will definitely love my course. Go ahead and click the link on my bio and you will land on this page. You will not only find the past exam questions, but introduction videos where I break down complex concepts into small pieces that are easy to digest. It is very important in grade 12 to stay ahead of your teacher, and this is what this course is for. It's very easy to navigate through the course as videos are arranged into collections. You can clearly see that we have electrostatics, work energy and power, Doppler effect, so on and so on. Do you maybe need help with study tips and creating your own timetable? We can talk about that inside the course and I can help you out. It doesn't even take a minute to join. Can't wait to hear from you. A ball of mass 200 grams is dropped vertically downwards from the top of a building to a concrete floor below. The ball bounces off the floor. The velocity time graph below shows the motion of the ball. Ignore the effects of air friction. Take upward motion as positive. 3.1.1. Use the graph only. Okay. And then we're supposed to determine the number of times the ball bounces off the floor. So it is dropped vertically downwards. It seems like this is where it strikes the ground, right? And then obviously we can see now that the velocity becomes positive as it is going up. And then it strikes the ground one more time. Okay, so what is the question saying? To determine the number of times the ball bounces off. Okay, but you can see after the second bounce, it does not bounce off. Right? Oh, not after the second bounce. Does not make sense. After it strikes the ground for the second time, it does not bounce off, right? It remains on the ground. So clearly, the number of times it bounces off the floor is 1. It only bounces the floor 1 time. So that is 1. That is the answer there. The answer is 1. Why is this thing not letting me write? Let's see. Okay. Right, and then 3.1.2, determine whether the collision between the ball and the floor is elastic or inelastic. Provide a reason for the answer. Well, it is inelastic. It is inelastic. Right, let's take a look at this. It strikes the ground with a speed, right? Not direction. I'm only talking about speed. It strikes the ground with a speed of 10 meters per second. And it leaves the ground with a speed of 7.5 meters per second. Clearly, 10 meters per second is not equal to 7.5 meters per second. So the collision is inelastic, right? The collision would be elastic if it strikes the ground with a velocity of 10 meters per second and leaves the ground with a velocity of 10 meters per second. Well, not velocity, but speed, because if we're talking about velocity, we then have to talk about the direction. Right. 3.1.3, to calculate the height from, we want to use the graph only to calculate the height from which the ball is dropped. So this question says use the graph only. So you cannot use equations of motions. You have to use the area of the graph in order to calculate the height. So this is the time at which it is dropped, and then this is the time at which it strikes the ground. So you can clearly see the area that we have. This is the area. We need to calculate that area. It's going to give us the height. So the height will be equals to a half base multiplied by height. Why a half base multiplied by height? Because we have a triangle. So a half, the base is the time, which is 1.5. The height is the velocity, which is clearly 10 as it strikes the ground. Okay, so this gives us 7.5 meters. So there we go. That is the height. We're not supposed to use equations of motions here. We're supposed to use the area, right? If we're looking for the acceleration, we will calculate the gradient, right? That is how it works. Okay, 3.2, calculate the impulse that the ball exerts on the floor when it strikes the floor for the first time. Okay, the impulse, 3.2, right? So let's take a look at the information that we have here. We have the velocity at which it strikes the ground. We have the velocity at which it leaves the ground. So we should be able to calculate the impulse. Take a look at this. F net delta t is equals to delta p. This right here is the impulse, not delta p, right? Delta p is the change in momentum. F net delta t is the impulse. They are just equals to each other. Okay, so F net delta t is equals to delta p, right? So this is equals to delta p, and then in place of delta p we can then say mass vf minus vi. Okay, and then what is the mass of the object? 200 grams. So in kgs that is 0.2. The final velocity, let's take up as positive. The final velocity is 7.5 meters. So we have 7.5 minus the initial velocity, which is minus 10. So that will be 7.5 plus 10. Right. So we have 0.2 multiplied by 17.5. Okay, and then if you put that in your calculator, you should get 3.5 newtons seconds. Right. And then impulse, it should be a vector because we have f net, right? So because it is a vector, we should give the direction. The impulse that the ball exerts on the floor. So the ball is hitting the floor, so it should be downwards. Right, it should be downwards. So there we go. That is how we calculate impulse. Pay attention to the SI unit. The SI unit is Newton seconds, not kg meters per second. Kg meters per second is for the change in momentum. The impulse is Newton seconds. Right? These things are not the same. Should be very careful. Okay. 3.3. In the diagram below, ball A is dropped from a height of 10 meters, and simultaneously, ball B is thrown vertically upward at a velocity of 20 meters per second. Ignore the effects of air friction. Calculate the height from the ground at which the two balls collide. Okay. So obviously, in the course, we have talked about this question and exactly how to approach it, right? But let's just take a look at it again. So let's say the two balls meet at this point, right? If they meet at that point, we can take the displacement of ball A when they meet to be k, right? Obviously, if the displacement, or let's say rather the distance that ball A has traveled is k when they collide with each other, then the distance that B would have traveled is 40 minus k, right? Because this entire thing is 40. So if ball A has traveled k and then the entire thing is 40, ball B should have traveled 40 minus k, so that when we add these two values we get 40, right? So that is the first part that you need to understand. It's very crucial that you understand that part in these kind of problems, right? So we have the displacement of A, which we are saying it is k, and then we have the displacement of B, which is 40 minus k, right? Acceleration is 9.8 meters per second squared, the same for both objects, right? And then they are projected at the same time, so they have the same time also. Because they are projected at the same time. And then what else? Oh, they are dropped. So if they are dropped, we have VI. Because they are dropped, right? So, one object is dropped and the other one is projected upwards. So if we start with ball what? Ball A. Let me just drag these upwards. I don't want to write these in 2 pages if I can write it in one. Okay, so if we start with ball A, we're going to have delta y when it goes to VI delta t plus a half acceleration delta t squared. So the displacement of A, let's take up as positive, right, is going to be minus k, because we're taking up as positive. The initial velocity, it is dropped, so it is 0. So we have 0 delta t plus a half. Acceleration is minus 9.8 delta t squared. Okay, so we're going to have minus k is equals to 0 delta t, that is just going to give us 0. And then we have minus 4.9 delta t squared. Right, so this is where we end with ball A. So let's just let this be equation 1. We don't have to let it be equation 1, but for the sake of clarity, we can do that. And then for ball B, let me just copy down the equation for the faint-hearted ones. VI delta t plus a half acceleration delta t squared. So the displacement will be, it is going upwards, right? and then we're taking up as positive. So that will just going to be 40 minus k. That is equals to vi. It is thrown vertically upwards with the initial velocity of 20. So that is 20 delta t plus a half. Acceleration is minus 9.8 delta t squared. So we're going to have 40 minus k being equals to 20 delta t minus 4.9 delta t squared. Okay. So now at this point we can do a couple of things, right? Because we have two equations now. We're done with the physics. We're just playing around with the math. So we said that minus k, not that we said, we calculated minus k to be equals to minus 4.9 delta t squared. So in place of minus 4.9 delta t squared, let's just sub k, right? Why can't we do that? Why can't we do that? We should be able to do that. And then here we also have minus k. So we're going to do the same thing. We're going to sub minus 4.9 delta t squared. Another thing that we can do, we can make minus k the subject of the formula here. It will be equals to 20 delta t minus 4.9 delta t squared. But what is minus k? Minus k is just minus 4.9 delta t squared. This is equals to, well, we're taking 40 to the other side, so we're going to have minus 40. This is equals to 20 delta t minus 4.9 delta t squared minus 40. So when you take minus 4.9 delta t squared to the left hand side, it's going to be plus. So we're going to get 0 is equals to 20 delta t minus 40. Clearly, delta t is equals to 2 seconds. So the objects, they meet each other after 2 seconds. But we are not interested at the time. We want to calculate the height above the ground. So minus k is equals to minus 4.9 delta t squared. So k is equals to 4.9 delta t squared. K is equals to 4.9 multiplied by 2 squared. We know that delta t is 2. So that is 4 multiplied by 4.9, 19.6. So k is 19.6. So if this is 19.6, this should be 20.1. 20.1, not 20.1, but 20.4. This will be 20.4. So that when we add the 2, we actually get 40. So the height above ground is equals to 40 minus 19.6, which is 20.4 meters. So there we go. That is question 3. Right.
If you like this video, you will definitely love my course. Go ahead and click the link on my bio and you will land on this page. You will not only find the past exam questions, but introduction videos where I break down complex concepts into small pieces that are easy to digest. It is very important in grade 12 to stay ahead of your teacher, and this is what this course is for. It's very easy to navigate through the course as videos are arranged into collections. You can clearly see that we have electrostatics, work energy and power, Doppler effect, so on and so on. Do you maybe need help with study tips and creating your own timetable? We can talk about that inside the course and I can help you out. It doesn't even take a minute to join. Can't wait to hear from you.
A hot air balloon is rising upwards with a constant velocity of 5 meters per second. When the balloon is 60 meters above the ground, a ball is released from it and the ball falls freely up to the ground. Oh, okay. Makes sense. Define the term free fall. Well, I'm going to let you do that. And then what is the velocity and direction of the ball at the moment when it is released from the balloon? Okay. Another thing that we have talked about inside the course, right? We have said that the velocity, the initial velocity of a ball in a balloon is equals to the velocity at which it is projected plus the velocity of the hot air balloon. So what is the velocity at which it is projected? The ball is released, right? So the velocity at which it is projected is 0. What is the velocity of the hot air balloon? 5 meters per second. We're taking up as positive.
So we're gonna have 5 meters per second. So that is the initial velocity of the ball after it is released from the balloon. Okay, and then 4.3, calculate the maximum height above the ground reached by the ball. Okay, seems quite straightforward. So it has an initial velocity of 5 meters per second. So it will go up first, right? Reach a maximum height, and then it's gonna start going down. So we want to calculate the maximum height. What do we have? We have the initial velocity, we have the final velocity, which is 0 at maximum height. So we're looking for delta y, right? Because calculate the maximum height. Yeah, we're looking for delta y, and then we do have the acceleration. So we're gonna say vf squared is equals to vi squared plus 2a delta y. So vf squared, that is 0 squared, is equals to vi, which is 5 upwards. So that is 5 squared plus 2a is minus 9.8 delta y. So delta y is equals to 25, well, minus 25 divided by minus 19.6, and then this is equals to 1.28 meters. Right, let's go to 4.4. That is the mistake that most people do. The question says calculate the maximum height above the ground in bold, right? Not the displacement from the time in which it is projected. No, the maximum height above the ground. So the maximum height above the ground, right, maximum height is equals to 60 meters, as we can clearly see from the sketch, plus 1.28, which is going to give us 61.28 meters. Right, so make sure that you don't miss those kind of things, because most people do miss them. Okay, and then 4.4, how far apart will the ball and the balloon be 3 seconds after the ball is projected? Okay, so the balloon keeps rising at the constant velocity, and our ball, obviously it starts by going up for some time and then it starts going down. So we want to calculate how far apart they are. So let's start with the displacement of the balloon. It has an acceleration of 0, obviously. Vf, we do have it, is equals to vi, because it's moving at a constant velocity. And we're interested in delta y. We also have the time, which is 3 seconds. So which equation is the easiest? I think delta y is equals to vf plus vi over 2 multiplied by delta t is the easiest equation we can use here. So vf is 5, right, because it keeps moving with its velocity of 5 meters per second. Vi is also 5 because it's moving at a constant velocity, divided by 2 multiplied by 3. So that is 15 meters. Right, so the balloon has went up some 15 meters, right, in 3 seconds. So that is 15 meters. So we need to calculate how where the ball is after 3 seconds. So the information we have with regards to the ball, we obviously have delta t, we have acceleration, we have vi, we are interested in delta y. So what do we do here? It seems like delta y is equals to vi delta t will work, plus a half acceleration delta t squared. So vi is 5, delta t is 3, plus a half acceleration is minus 9.8. Delta t is 3, right, what's happening? And then we square that. And then when I put that in my calculator, I actually don't have a calculator, like I've said. 5.3 minus 9.83, we square that, we get minus 29.1 meters. Okay, so the displacement of the ball is downwards, so 29.1 meters. So we need to add these two numbers to find out how far apart they are. So how far apart? I need to add another page here. So let me just insert a blank page and then right. So how far apart? We're gonna have 15 plus 29.1 meters. Well, let me not put the SI unit as of yet. Okay, and then this is equals to 44.1 meters. So there we go, 4.4 and then 4.5. We're supposed to sketch a velocity time graph for the motion of the ball, right? And then we're supposed to just indicate the initial velocity as vi and not put the actual value. Okay, so let's say it starts somewhere there and then it goes to reach maximum height and then it goes to strike the ground. So what are we supposed to indicate? Well, first v in meters per second, because if you don't label your axis, I don't know what that thing is. Is it a graph? I don't know what's going on. So this is vi, the velocity as vf, and time as tf when the ball strikes the ground. So here we have tf, and then this is vf. Okay, and then what else are we supposed to indicate? The time taken by the stone to reach the maximum height, st max. Okay, so the second bullet point says the velocity vf and the time it hits the ground. Okay, no, I'm making a mistake here. So tf is supposed to be here. That is where tf is supposed to be. It's supposed to have tf, right? That is the velocity, or that is the time at which it strikes the ground. And then this is vf, the velocity at which it strikes the ground. So here I'm gonna have v t max, the time at which it reaches maximum height. So here we have t max. Okay, I think I have all that I need now. Okay, let's see. There's no instruction that restricts us from checking up is positive or down is positive. So even if you do it the other way around, you should be fine. Let's take a look at these four concepts, these four definitions, before we can talk about anything else. So the first definition I want us to take a look at is organic molecules. So organic molecules are molecules containing carbon atoms. That is what organic chemistry is all about. It's all about organic molecules, or molecules that contain carbon atoms, right? So any molecule that has a carbon, we deem that an organic molecule. And then everything else without is inorganic. For instance, H2SO4, NaOH, HCl, so on and so on. Those are inorganic molecules because they don't contain carbon. So that's the first term we need to wrap our head around, organic molecules. And then the second term, homologous series, is a series of organic compounds that can be described by the same general formula. This may not make sense at this point of time, but as we progress through the video, it will definitely make sense. So homologous series is a series of organic compounds that can be described by the same general formula, right? We can say it's more of function. Think of a function in math. Let's say, for instance, hyperbolic functions. They can all be defined by the same general formula, right? So here we're talking about collections of organic compounds that can be described by the same general formula. You're going to see what I'm talking about as we move on to the next slide. Okay. The third term I want us to take a look at is general formula. It's an expression used to indicate the distribution of atoms in an organic compound in a homologous series. Even though you're not going to come across a question in the exam saying define the term general formula, you're going to have to memorize a few general formulas for different homologous
series. So we are going to touch on that. And then the last term before we move to the second slide, where everything will start to make sense, is functional group, right? So there's two definitions for functional group, this first one right here and this second one. Taking a look at the first one, it says it's an atom or a group of atoms that determine the chemistry of a molecule. I don't like this definition because it's not on the exam guideline. This is the definition we should go with, which says that functional group is an atom or group of atoms that determines the physical and the chemical properties of a group of organic compounds. You guys have covered intermolecular forces in grade 11, right? So functional groups determine the intermolecular forces of a organic compound. Let's move to the second slide and see these concepts in play. We have 9 homologous series we are going to focus on. 1, 2, 3, 4, 5, 6, 7, 8, 9. Of those 9 homologous series, we are going to take a look at the structure of their functional group, the name of the functional group, and their general formula. So if you've forgotten already, what is a homologous series again? Let's go back and take a look. So a homologous series is a series of organic compounds that can be described by the same general formula, right? So let's go back to our table. The first homologous series we are going to pay attention to is alkanes. This is the first homologous series we are going to pay attention to. This is the structure of the functional group. We have 2 carbons with a single bond between them, right? And then the name of the functional group, there actually isn't a name for this functional group. We just know that between carbon atoms, there is single bonds. The general formula, I don't know if it's big enough, but it's CnH2n plus 2. Let's take another look. The name of the homologous series is alkanes. This is the structure of the functional group, and this is the general formula. So if the question says draw a structure of the functional group of alkanes, this is what we are expecting. The general formula says CnH2n plus 2. Let's make sense of that before we move to alkenes. Okay, let's say we have these 3 carbons that are bonded to each other, right? A carbon can only support 4 bonds, right? So you need to recall that so that you don't make mistakes while drawing your structures. So let's take a look at this compound. This is an alkane. Why am I saying it is an alkane? It is an alkane because between the carbon atoms, there is only single bonds, right? It is an alkane because of that. And then let's talk about the general formula. We say that the general formula for alkanes is CnH2n plus 2. So let's go ahead and make sense of this. Taking a look at the number of carbons we have, 1, 2, 3. We have 3 carbons. Let's take a look at the number of hydrogens we have. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 hydrogens. As you can see, if 3 is n, 8 is 2n plus 2, where 3 is our value of n, right? So if you have 3 carbons, you're going to have 8 hydrogens in an alkane. That's what we mean by the general formula of alkanes is CnH2n plus 2. Okay, let's go ahead and move to alkenes. So alkenes, this is the name of the homologous series. Structure of the functional group, we have a double bond between carbon atoms, and the general formula is CnH2n. Again, we have to do an example. Let's go ahead and have an example and see how it looks like. Okay, so let's have, we can have 4 carbons, no issues whatsoever. And then let's go ahead and have our hydrogens. So this carbon is fine, it's happy because it has 4 bonds. This carbon is also satisfied now. And let's take a look at this third one. It already has 1, 2, 3 bonds. So it only needs 1 hydrogen, okay? And then this carbon, 1 hydrogen, and another hydrogen. It has 1, 2, 3, 4 bonds. Okay, everything is okay. So the number of carbons, how many carbons do we have? We have 4 carbons. The number of hydrogens, let's take a look. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 hydrogens. And the general formula for alkenes is CnH2n. This is what we mean when we say the general formula for alkenes is CnH2n. Moving to the third homologous series, alkynes, we have a triple bond in between the carbon atoms. And the general formula is CnH2n minus 2. Let's go ahead and take a look. 1, 2, 3. Well, we can leave it like that with only 3 carbons. And then let's go ahead and fill out our hydrogens. This carbon has 4 bonds, so it's excited. And 1, 2, 3, 4. The second carbon already has 4 bonds. So let's just move to the third and add 1 hydrogen. Okay, so all carbons have 4 bonds. This is correct. So the general formula, let's take a look. We know that it is supposed to be CnH2n minus 2. Okay, how many carbons do we have? We have 3. How many hydrogens do we have? 1, 2, 3, 4. We have 4. Is it CnH2n minus 2 indeed? Okay, let's go ahead and find out. 2 multiplied by 3 is 6, minus 2 is equals to 4. So indeed, the general formula for alkynes is CnH2n minus 2, as you can clearly see. This is the general formula, and this is the functional group. That is the structure of the functional group. Alkane, alkene, and alkynes. Okay, I'm sure you can see the trend now. We have haloalkanes, also called alkyl halides, with this structure of functional group and this general formula, CnH2n plus 1x. Let me just draw you a structure to show you how haloalkanes look like. So a haloalkane is an alkane with a halogen, right? So for instance, 1, 2, 3. We have our 3 carbons. Let's go ahead and fill out the hydrogens. So instead of having hydrogens, we have a halogen, right? Maybe chlorine, for instance. And in a case like that, we would have a haloalkane, right? We now have a halogen. So the general formula here is CnH2n plus 1x, where this x is a halogen, right? A halogen can be fluorine, chlorine, iodine, and bromine, right? So there we go. This is how a haloalkane would look like. Moving back, we have an alcohol. This is the structure of the functional group. And then for alcohol, we actually have a name for the functional group. It is called the hydroxyl group. And then the formula is CnH2n plus 2 oxygen, right? And this is how you expect an alcohol to look like. 1, 2, well, let's just leave it to 2 carbons, because if I keep putting 3 carbons, people are going to start thinking that for all structures, we just need 3 carbons, and that is not the impression I want to make. So this is an alcohol, okay? We can see the structure of the functional group. Let's move to the following homologous series. Aldehydes. The structure of the functional group, it has a name, it's called the formyl group, okay? And then the general formula is CnH2n. Oh, let's go ahead and have a structure of an aldehyde. So an aldehyde, we have a carbon that is bonded with a double bond to an oxygen, and it has to be the last one on the chain. What do I even mean when I say on the chain? You will see that as, or you will understand as we move forward. So this is how an aldehyde would look like. This is the structure of our functional group. Let's go ahead and take a look at ketones. Structure of the functional group. The name of the functional group is carbonyl, and it has the same general formula as aldehydes. There's actually something special when homologous series have the same general formula. We're going to talk about that as we move forward. So how does a ketone differ from an aldehyde? Okay, here I have the aldehyde I just drew previously. So let me draw a ketone close to the aldehyde to show you the difference between ketones and aldehydes. So ketones, 1, 2, 3, double bond oxygen, hydrogens everywhere else, right? So this is the structure of the functional group. So a ketone, the carbon that is double bonded to the oxygen is sandwiched by 2 other carbons, right? If that is the case, then it is a ketone. But in an aldehyde, it's always at the end of the chain. So that is the difference between aldehydes and ketones. In ketones, the carbon is sandwiched by 2 other carbons, and in aldehydes, it is at the end. Right, back to our table. Carboxylic acids. This is our structure of the functional group. The name is carboxyl. So this is the carboxyl group. If the question says, what is the name of the functional group on carboxylic acid? It is carboxyl group. The general formula, CnH2n oxygen. And we have esters. Esters, this is the structure of the functional group. We don't have a name for the functional group, and the general formula is that of carboxylic acid, CnH2nO. So there's something special there again. So aldehydes and ketones, they share the same general formula. Same is true with carboxylic acids and esters. There's something special going on there. We're going to talk about it as we move forward. So, right, this is where we need to start with organic compounds. Before you can move forward, watch any other video, look at any other material, you have to memorize this table. You cannot do organic chemistry if this table is not memorized. So, I don't know, take 30 minutes, take an hour, however long it takes, but you cannot carry on before you memorize this table. So just go ahead and do that, and I'll see you on the next video. There's a system that we use, IUPAC naming. So this system, we use it to name organic compounds. If you're given a certain structure, there is certain steps you can take to name the structure. This actually makes things easier and not more difficult. Imagine you're working with a scientist from another country and there's no system for naming organic compounds. That comes with a lot of confusion. But if there is a system, then everybody knows what everyone is talking about. It just makes things that easy. So we use the IUPAC naming system to name organic compounds, of which IUPAC is just short for International Union of Pure and Applied Chemistry. That's what IUPAC stands for. So let's go ahead and take a look at the steps we need to take to name these organic compounds. So step 1, you identify the number of carbon atoms in the parent chain of the organic compound. And then after you've done that, the following prefixes are used. If you have 1 carbon, the prefix to use is meth, 2 eth, prop, bute, pent, and hex for 6, in that order. But what if you have 7 carbons? Then this is hept. And if you have 8 carbons, this is oct, right? I think you can have 9 carbons, you can have 10 carbons, but in our curriculum, we just focus on the first 8.
number of carbons in the longest chain. So we need to memorize this table. There is no way you can do organic chemistry without memorizing this table. There's a lot of things that we need to memorize in organic chemistry, and it's just the way it is, right? So 1, that is meth, 2 F, 3 prop, 4 is bute, 5 is pent, and 6 is hex, 7 is hept, and 8 is oct. All right, so take some time, take 10 minutes, I don't know, 15, 20, and make sure that you squeeze this table in, you memorize the table before we can do anything else. Right, so that is step number 1. After you've done that, what do you do? Step 2, you have to actually number the carbons in the parent chain. Start with the carbon at the end closest to the functional group. This is very key. We're going to be using this time and time again. But don't worry, when we are naming these compounds, we're going to come back to the rules to make reference of the rules. So you don't have to worry about that. And then the second point, functional group must have the lowest possible number, right? So if you start numbering your carbons from the carbon closest to the functional group, then the functional group must have the lowest possible number. So those two rules, they go hand in hand with each other. And then step number 3, identify the functional group of a homologous series in the compound. We know the structures of the functional groups. That's why it was important for us to memorize that table that we started with homologous series, general formula, and functional group, because we're going to use that time and time again. So this is going to help you with determining the suffix of the name. So for alkanes, we have ane. For alkenes, we have ene. For alkynes, we have yne. For alcohols, the name must end with all. For aldehydes, it's al. For ketones, it's on. For carboxylic acid, is oic acid. And for esters, is oit. Right, so you gotta see how that comes together, right? And then here we have the steps on naming haloalkanes, but there's a special case in haloalkanes. So let us focus on those other homologous series first. We're gonna do haloalkanes in a separate video, right? Hopefully you wrote the steps somewhere on a piece of paper, and now we're going to apply those steps to name our organic compounds. So step number 1, just to recall, is to identify the number of carbons in the parent chain of the organic compound, right? So let's go ahead and do that. How many carbons do we have in this case? So let's go ahead and circle our carbons in the longest chain. So there we go. We have 1, 2, 3, 4, 5, 6. We have 6 carbons. This is hex according to our rules. And now we can go ahead and identify the functional group. It is an alkane, right? Between carbon atoms, we have single bonds. We don't have any halogen. We don't have any double bond. We don't have any oxygen. We just have carbon and hydrogen. And between any 2 carbons, it's single bond. So this is going to be hexane, right? The name of this structure is hexane. It's a simple alkane with 6 carbons. So hex from the number of carbons, and ane from the mere fact that it is an alkane. So this is how we name these organic compounds. Let's go ahead and take a look at the following organic compound. So in this organic compound, we need to identify our longest chain. Let's see. So if we start numbering from this side, we're going to have 1, 2, 3, 4, 5, 6. Right, so we can have a longest chain with 6 carbons. Let's see what happens if we start numbering from this side. 1, 2, 3, 4, 5, 6. Even if we go straight, we still have 6. Even if we go down, we still have 6. So it seems like our longest carbon chain has 6 carbons. So let's go ahead and circle that. So there we go. We have 1, 2, 3, 4, 5, 6 carbons. So because we have 6 carbons, we know for sure that it is going to be hex, right? And then now let's identify the functional group. Do we have any double bond? Do we have any oxygen? Do we have any halogen? No, we don't. So this is still an alkene. So the name is going to be hexane, right? But you can see that it's not identical to the structure we have. There's something going on here which we needed to address. We have a branch. We can see this carbon here. We call this a branch. We have a branch and another one here and another one here. So what do we do in a case like this where we have a branch, right? So we need to start naming or numbering our carbons closest to a branch. So if we start numbering from this side, from the right hand side, we're gonna have 1, 2, 3. We're gonna have the branch on the third carbon. And then if we start numbering from the left, we're gonna have 1, 2. So our branch is on the second carbon. So we have to start numbering our carbons from the left hand side because that is the side closest to the branch. So 1, 2, 3, 4, 5, 6. We start numbering from the side closest to the branch on alkanes because we don't have a functional group. All the carbons function as a functional group, so that's why we start numbering from the side closest to the branch. So let's see how that will come together. Take a look at this. This is one carbon, so it is supposed to be meth, right? But when it is a branch, there is something we add. Now let's take a look at this branch also. It's one carbon, so that is meth. And then this one on the fourth carbon, we have 2 carbons, so that is eth. So how are we gonna then write the name, right? So the branch will come before hex, right? That's where we put the branch. So in this situation, we would say, let me just erase this and write the name in full. We would say 2.2 dash dimethyl dash 4 dash ethyl hexane, right? Don't get scared. I'm about to explain why I'm saying what I'm saying. So let's make sense of this. Hex is the number of carbons in the longest chain. Ane is the suffix for alkenes, right? So we know where this is coming from. Okay, now let's talk about 2.2 dash dimethyl. Okay, so this 2 is for one of the branches on the second carbon, but we have 2 branches, right? So that's why I'm having 2, 2, and then I have dimethyl to show that those branches, they have 1 carbon, right? So di is for the mere fact that we have 2. If we only had 1, it was going to be 2 dash methyl, but because we have 2, we have dimethyl. And then I'm telling you that on the fourth carbon there is a branch, and then the branch has 2 carbons. This is where the ethyl is coming from. If you have a branch with 3 carbons, then it was going to be 4 dash propyl, 4 carbons, 4 dash butyl. That is how it works, right? So this is the name of this organic compound if we are using the IUPAC naming, right? Let's move to the structure that follows. Let's take a look at this structure. So taking a look at this structure, the first thing to do is to identify the number of carbons in the parent chain. So let's see, 1, 2, 3. If we go down, we still have 3. So okay, we can conclude that in our longest carbon chain we have 3 carbons. So this is prop, right? This is prop. Now let's go ahead and do step number 2, which is identifying the functional group.
Our functional group is a double bond, right, between two carbon atoms. This is the characteristics of an alkene. So we know that we are dealing with an alkene here. But where is the double bond located? It's located between the first and the second carbon. So we're going to have prop 1 in, right? This one that you place here between the number of carbons and the suffix of the functional group is telling you where the functional group is located amongst the carbons. That is its purpose, right? So, okay, we've prop 1 in, and as you can see, we have a branch on the second carbon. So if we have a branch on the second carbon, what do we need to add? We need to add 2-methyl, right? 2 because it's on the second carbon, and the methyl because it's 1 carbon. So if we had another carbon here, let's say for instance we had another carbon here, then it was going to be 2, 2-dimethyl. But now because we only have 1, it's just going to be 2-methyl prop 1 in. Right, there we go. So let's move to this structure. How many carbons do we have in the longest chain? We have 1, 2, 3, 4. This one is easy to see. And then what is the functional group? We have a triple bond between carbons atom. So we know that that is an alkyne. Okay, so because we have 4 carbons, that is gonna be but. And then we have to start numbering from the side closest to the functional group. If we start numbering from the left hand side, we're gonna have 1, 2, 3, 4. If we start numbering from the right hand side, we're gonna have 1, 2, 3, 4. So whatever side we start numbering from in this situation, it's okay. We get to the functional group on the second carbon. So the functional group is on the second carbon, right? So we're gonna have but 2 YNE. Okay, this but the number of carbons, and then the 2 is for the position of the functional groups, making reference to the carbons. And we don't have any branch whatsoever. So this is the name of our organic compound, but 2 YNE. Right, let's move to the following one. The first step is to find the longest carbon chain, and it seems like we have it right here. So that is 1, 2, 3, 4. We have 4 carbons, so that is but, right? We're gonna worry about everything else later. Now we just know that we have but. Okay, now let's identify our functional group, right? Our functional group is OH. OH is alcohol. I'm assuming that you've memorized that table of homologous series and the structure of the functional groups. Which side do we start numbering our carbons from? Left or right? Obviously, we're going to start from right because that is closest to our functional group. So 1, 2, 3, 4. So our functional group is on the first carbon. So we're going to have butane 1 ol. But is from the number of carbons, ol is the suffix we use for alcohols, and then 1 is the position of the functional group. But there is something we're adding here. I'm not sure if you realize we have added butane, we've added an here. So we add an on everything else except from alkane, alkene, and alkyne, right? You're gonna see as we move forward. So yeah, you need to know this, that with everything else we have to add an. So there we go. We have butane 1 ol. But for the number of carbons, 1 for the position of the functional group, and then ol because we have an alcohol. Right, let's move to this structure. So there we go. I'm sure you can already see that we have an alcohol. We just need our longest carbon chain, and this is our longest carbon chain. But even if we go down, there's no issues whatsoever. So we can have this
being our longest carbon chain, because we still have 3 carbons, right? So which side are we going to start numbering from? We're going to start numbering from the right hand side, because that's the one closest to the functional group. So we have 1, 2, 3. If it is 3 carbons, we're going to have propane, that is for an alcohol, right? And then the functional group is on which position? It's on the first carbon, so that is propane 1 all. So there we go. And then we have a branch on the second carbon. Here's our branch on the second carbon. So it is gonna be 2-methyl propane 1 all. We always have to separate the numbers and the letters with a hyphen, just like you see here, and you can also see here. We separate the numbers and the letters with a hyphen. So there we go. 2-methyl, this is the branch. It's on the second carbon with 1 carbon on the branch. Propane, the number of carbons on the longest chain. 1, the position of the functional group. All, it is an alcohol, right? That is how the name ends. So there we go. We have managed to name another organic compound. Moving on, let's take a look at this structure. So this is, which organic compound is this one? Can you take a look at it and think about it? Which organic compound are we dealing with right now? Right, this is a ketone, because the carbon that is double bonded to the oxygen is sandwiched by 2 other carbons. In a case like this, we have ourselves a ketone. So let's go ahead and identify our longest carbon chain. We can have 1, 2, 3, 4, 5. Even if we go up, we still have 5. So let's just take the straight carbon chain, right? But I've showed you that even if you don't take the straight one, it still works. So we have 5. 5 is, so it's meth, eth, prop, but, and pent. So we have pent because we have 5 carbons on the longest chain. So there we go. We have pent. And the position of the functional group, if we start numbering from the left, 1, 2, 3. Even if we start numbering from the right, we have 1, 2, 3. But if we start numbering from the right, we get to the branch on the second carbon. So that is what we have to go with, because our position of the functional group is not a deciding factor in this case, as it is in the middle. So we have to go with the branch on the second carbon. Okay, so that is pentane 3 own, right? Pent, number of carbons on the longest chain. 3, position of functional group. Own, the suffix of ketones. And then we have a branch on the second carbon, so that is 2-methyl. It's that easy. There we go. We are done. We have named our ketone, right? Let's move to the following one. So in this case, we still have a ketone. Let's take a look. This is our longest carbon chain, and then this is just propane 2 own, right? So prop, number of carbons, 2, position of functional group, own, suffix of ketones. But as you advance in organic chemistry, you're gonna realize that there's actually no need to include these 2, right? Can you think about that? Do you see what I'm talking about when I say there's actually no need to include that 2? Yeah, if you can't think about it now, if you can't get to where I want you to go, don't worry. Eventually, it will make sense why there is no need to include that too. Right, another structure looks like a ketone. Let's have our longest carbon chain. 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5, 6. Right, so that is our longest carbon chain. We have 1, 2, 3, 4, 5, 6. So as you can clearly see,
It's not all the time where the longest carbon chain is the straight chain, just in this case, right? Because a lot of people, they will just rush and say, the longest chain, 1, 2, 3, 4, 5. So, okay, we have 5. But that is not the case. We have 6 carbons, so that should be hex. But then because it's a ketone, it's going to be hex N, and then hyphen. From which side do we start numbering? Let's go ahead and find out. If we start numbering from the left, we're going to have 1, 2, 3, 4. The functional group is on the 4th carbon. And if we start numbering from the right, we're going to have 1, 2, 3. So we have to start numbering from the right, because when we start numbering from the right, we get close to the functional group first compared to when we start numbering from the left. So this is 1, 2, 3, 4, 5, 6. So we have hexane, and then our functional group is on the 3rd carbon, and it is a ketone. But we have a branch on the 4th carbon, so that will be 4th dash methyl. And just like that, we've named our organic compound, right? 4 for the branch of which it has 1 carbon, so that is why it's methyl. Hexane, longest carbon chain. 3, position of functional group. Own suffix for ketones. There we go. We just need to follow the steps, really. Then the question that follows, we have an interesting structure. This is the longest carbon chain. First thing we need to do, and which functional group does it belong to? Take a look at this. Carbon double bond oxygen OH. That falls under what? Right. That is a carboxylic acid. That is a carboxylic acid. So how many carbons? We have prop, right? But on a carboxylic acid, this functional group is always at the end. So we don't have to include it in our name because it is always at the end. So this is propanoic acid. If we had 4 carbons, it will be butanoic acid, hexanoic acid, so on and so on, right? Obviously, if you have a branch, you would include your branch in there. But yeah, naming carboxylic acid is quite easy. Let's take a look at this one that follows. How many carbons? 1, 2, 3, 4, right? And then it's on the functional group is on the 1st carbon, as you can clearly see. It is always there. So this is butanoic acid, right? Like I was telling you that if we have 4 carbons, it would just be butanoic acid. So yeah, this is how you would name that structure. Let's move forward. Here we have an ester. This is the functional group of an ester. But there's a lot going on with regards to esters. So let's do it like this. Let's name haloalkanes. After naming haloalkanes, we're going to talk about how we name esters, right? And in doing that, we will talk about a process called esterification. So let's just leave it here for now. There's 3 cases I want us to take a look at. The compound in front of us being the first case. So according to the exam guideline, the branch doesn't take preference over the halogen. The halogen doesn't take preference over the branch in haloalkanes. So how do we name these compounds? Let me go ahead and show you. So the first thing, we will identify our longest carbon chain, which will be easy to do in this problem. So let me just go ahead and do that. There we go. We have our longest chain, right? Now we need to number our carbons from the side closest to the halogen or closest to the branch. So if we start counting from the left, we're going to have a branch on the 2nd carbon. And then if we start numbering from the right, we're going to have a halogen on the 2nd carbon. Okay? So in a situation like this, what do? We have chlorine in between
the branch and the halogen. It is right in between. If you start counting from the left, it's on the third carbon. If you start counting from the right, it's on the third carbon. So chlorine is playing no role in how we're gonna name our haloalkane. In a situation like this, we would start numbering our carbon from the right. So we would have 1, 2, 3, 4, 5, right? We're doing that because B from bromo comes before M from methyl. So the alphabetical significant. We're gonna start by now. We're gonna number our carbons from the right hand side. So let's go ahead and do that. We have bromo on the second carbon, we have chlorine on the third carbon, and we have methyl on the fourth carbon. So the name for this haloalkane would be 2-bromo dash 3 chloro dash 4 methyl pentane. Pent for the 5 carbons in our longest chain, ane the suffix of haloalkanes, 4-methyl, that is the branch we have on the fourth carbon, 3-chloro, the halogen we have on the third carbon, and the 2-bromo, the halogen we have on the second carbon. So this is the name of our haloalkane. Let's take a look at this structure. The first step, obviously, is to identify the longest carbon chain. So let's go ahead and do that. So this is going to be our longest carbon chain. Starting with this carbon, there we go. And this is what we have. Right. So there we go. We have our longest carbon chain with 6 carbons. Okay, if we start counting from the left, we have 2 branches on the third carbon, and then if we start counting from the right, we have a halogen on the third carbon. So where do we start numbering our carbons, from the left or from the right? Well, you might be tempted to say, from the previous example, we chose bromo because it comes before methyl. So in this case, we shall do the same because bromo still comes before methyl. But that is actually not correct. That is not what we are supposed to do in a situation like this. Let me show you why. Let's say we start numbering from the left, right? If we start numbering from the left, we're gonna have bromo on the fourth carbon. So we're gonna name our haloalkane as 4-bromo dash 3.3 dash dimethyl hexane, right? That is how we would name our haloalkane if we started numbering our carbons from the left, right? So this is from the left, how our IUPAC name will look like if we start numbering from the left. But if we start numbering from the right instead, we would have 3-bromo dash 4.4 dimethyl hexane. This is if we start naming from the right. So there's something I want to show you here. If we start naming from the left, we have 4 plus 3 plus 3, which is 10. And then if we start naming from the right, start numbering our carbons from the right, we have 3 plus 4 plus 4, which is equals to 11. So this is 10 in total, and this is 11. So we are actually gonna go with this first one because it leads to the least number. Right, so this is what I was referring to when I say sometimes it's not the alphabetical order that is going to decide. Here's another example of that. We have a haloalkane with 1, 2, 3, 4, 5, 6 carbons in the longest chain, of which if we start counting from the left, we have a halogen on the second carbon. And if we start counting from the right, we have a branch on the second carbon. So in a situation like this, once more, we're not going to start numbering from the left because of this fluoro that we have on the third carbon if we start numbering from the right. So we would actually start numbering from the right because ultimately we're going to have the lowest numbers in our IUPAC name compared to if we started counting our carbons from the left. Let me go ahead and show you. If in this case we start counting our carbons from the left, we're gonna have 2 bromo, and then our fluoro would be on the fourth carbon, so 4 fluoro, and our branch would be on the fifth carbon, so 5 methyl dash hexane. No, there's no hyphen. Hexane. So this is if we start numbering from the left. Let's take a look. We have 2 plus 4 plus 5, which is 11. Now let's start numbering from the right and see what happens. From the right, we're gonna have 5 bromo, and then fluoro is on the third carbon if we start numbering from the right, so that is 3 fluoro, and then 2 methyl hexane. So let's go ahead and take a look. 5 plus 3 plus 2, this is 10. Yeah, so clearly in a situation like this, we need to start numbering our carbons from the right hand side. I hope you can see the trend. But just one last thing, in the absence of this fluoro, let's say we didn't have fluoro there and we have just a regular hydrogen, then we would start numbering from the left because of the alphabetical order. But as soon as we have something in between and it is not placed equidistant from the halogen and the branch, then we start considering the numbers. But in a situation like this, we just take a look at the alphabetical significance. So another thing that I want to iron out, as you can see, when I start naming from the left, I say 2 bromo, and then when I start naming from the right, I say 5 bromo. So why do I insist on naming bromo first? That is because when you actually write your IUPAC name, alphabetical order should be followed. So when I'm writing this name, I cannot start by this. When I start from the right, I cannot start by saying 2 methyl and then 3 fluoro, 5 bromo. No, I cannot do that. I actually have to start with bromo. That is how it is. So make sure you don't forget that. When you write your IUPAC name, you are supposed to place the halogens and the alkyl groups in alphabetical order, right? When you jot down the IUPAC name in the grand scheme of things, when you have sorted everything out, when you have numbered your carbons, you have to put everything in alphabetical order. Right, so I think that is all that we need at this point to name our haloalkanes. If you have any questions, obviously you can go ahead and drop it on the physics Q&A, and I will respond to it as soon as I can. Let's talk about isomers. Isomers are organic compounds with the same molecular formula but different structural formula. They are mainly, well, in our context, divided into three. We have chain isomers, positional isomers, and functional isomers. So let's go ahead and take a look at chain isomers. So in chain isomers, they have the same molecular formula, but different types of chain. If they have different types of chains, then they're going to have different structures. So that's why we are calling them chain isomers. Let's go ahead and take a look at this example that we have. We have butane and 2-methyl propane. These two organic compounds have the same molecular formula. In butane, we have 4 carbons and 10 hydrogen. The same is true with 2-methyl propane. We have 4 carbons and 10 hydrogens. But as you can clearly see, we have two different chains, one with 4 carbons and the other one with 3 carbons. The 4th carbon from 2-methyl propane is coming from this branch right here. So butane and 2-methyl propane are chain isomers. They have the same molecular formula but different types of chain. We're going to touch more on that at a later stage. Let's take a look at positional isomers. In positional isomers, the same molecular formula but different position of functional group. So positional isomer, same molecular formula but different position of functional group. In our example here, we have 1 chloropropane and 2 chloropropane. These two compounds are haloalkanes. In the first compound, the functional group, which will be our halogen, is on the first carbon. And then in 2-chloropropane, the halogen is on the second carbon. Overall, they have the same molecular formula, but they have different position of functional group. We have 1 chloropropane and 2 chloropropane. That's how they differ. And then let's take a look at this other example we have here. But1-ene. Obviously, that double bond on the first carbon can be here on the second carbon in a different structure. And the name would be but2-ene. So but1-ene and but2-ene are positional isomers. They have the same molecular formula, same number of carbon and hydrogen, but different structural formulas because of the position of the functional group. We call them positional isomers. And then lastly, functional isomers. So same molecular formula but different functional group. We have two pairs of functional isomers. Esters and carboxylic acids are functional isomers of each other. And then ketone and aldehydes are functional isomers of each other. If you still remember, the general formula for ketone is CnH2nO. And then the general formula for aldehydes is CnH2nO. So if we are talking about an aldehyde with 4 carbons, for instance, it will have the same molecular formula with a ketone with 4 carbons because they have the same general formula. So ketones and aldehydes are functional isomers. Carboxylic acid and esters are functional isomers. They have the same molecular formula, which is not the same molecular formula but the same general formula. Carboxylic acids and esters, which is CnH2nO2. Let's take a look at this example. The ester we have is methyl methanoate. We have 2 carbons, and then the isomer, the functional isomer of this ester would be ethanoic acid because it also has 2 carbons.
Obviously, they're gonna both have 4 hydrogens and 2 oxygen. That's why we refer to them as functional isomers. Same molecular formula, but different functional group. Different organic compounds have different structures. How do those different structures affect the physical properties? For instance, the boiling point, melting point, and vapor pressure. Between butane and octane, which one will have a higher boiling point, melting point, and vapor pressure? Those are the type of questions we are going to be looking at from this point on. First of all, let's define the boiling point. And the definition I've provided here is the same exact definition you're supposed to state in the final exam word for word. So boiling point is the temperature at which the vapor pressure of a substance equals atmospheric pressure. Is the temperature at which the vapor pressure of a substance equals atmospheric pressure. While melting point, at the other hand, is the temperature at which the solid and liquid phases of a substance are at equilibrium. The temperature at which the solid and liquid phases of a substance are at equilibrium. And lastly, the vapor pressure. It is the pressure exerted by a vapor at equilibrium with its liquid in a closed system. So those are the physical properties we are interested in. We will talk about how the chain length affect the physical properties, how the branching affect the physical properties, and lastly, how the functional group affect the physical properties. So let's start with the chain length, okay? So we are interested in the relationship between boiling point, melting point, viscosity, vapor pressure, and chain length. So let's go ahead and take a look at what the theory is saying. When the chain length increases, the surface area increases, and that increases the strength of the intermolecular forces. From grade 11, you should know that if the intermolecular forces increases, then we will have an increase at the boiling point, melting point, and viscosity, but the vapor pressure will decrease. So that is the relationship between chain length and our physical properties. As the chain length increases, the surface area increases, the strength of the intermolecular increases, and boiling point, melting point, and viscosity increases, but the vapor pressure decreases. Let's take a look at the example we have. We start with propane. You can see that the boiling point of propane is minus 42 degrees Celsius. And let's compare it with butane. The boiling point of butane is minus 0.5 degrees Celsius. Obviously, minus 0.5 degrees Celsius is greater than minus 42 degrees Celsius, showing us that as the chain length increases, we have an increase in boiling point. Butane has a longer chain length compared to propane, and the same is true when we compare butane and pentane. The boiling point of pentane is 36 degrees Celsius, which is clearly greater than that of butane. As the chain length increases, the surface area increases. There will be an increase in the intermolecular force. Boiling point, melting point, and viscosity will increase, but the vapor pressure will actually decrease. That is the relationship between chain length and our physical properties. Let's go ahead and take a look at branching. Increase in branching decreases the surface area, decreasing the strength of the intermolecular forces. That will lead to a decrease in the boiling point, melting point, and viscosity, but an increase in the vapor pressure. So as the branching increases, the intermolecular forces weaken, and that will lead to lower boiling point and higher vapor pressure. Let's go ahead and look at the examples we have. 2.2 dimethyl propane. We're comparing that with 2-methyl butane. Obviously, these two compounds are isomers of each other. We have the same number of carbons, we have the same molecular formula, but different structural formula. But 2.2 dimethyl propane is more branched compared to 2-methyl butane. You can see, even if you just take a look at the structure here. Now let's take a look at the boiling point. The boiling point of 2.2 dimethyl propane is 10 degrees Celsius, while that of 2-methyl butane is 30 degrees Celsius. So you can see, as the branching decreases, the intermolecular forces increases, right? Because 2-methyl butane is less branched. We only have one branch. It is less branched and it has stronger intermolecular forces and higher boiling point as a consequence. And lastly, we can compare 2-methyl butane with just pentane. In pentane, there's no branching. Now let's take a look at the boiling point. The boiling point of pentane is 36 degrees Celsius, which is clearly greater than the boiling point of 2-methyl butane. Again, showing that when you increase the branching, the intermolecular forces will be weak. You can see that the intermolecular forces of 2-methyl butane are weaker than that of pentane because of an increase in branching. So when you phrase your answers in the final exam with regards to branching, it's either you can state your answer in terms of increasing branching, or you can state your answer in terms of decreasing branching. But this is what we're saying. An increase in branching leads to the strength of intermolecular forces decreasing, while a decrease in branching leads to an increase in the strength of the intermolecular forces. That is essentially the idea you need to wrap your head around. So we touched on chain length and physical properties, branching and physical properties. And now lastly, we need to take a look at the relationship between the functional group and the physical properties. So we have pentane, butanol, and butane 1-ol. So look at the boiling point of pentane. It's 36 degrees Celsius, and that of butanol is 76 degrees Celsius. So why is the boiling point of butanol way higher than that of pentane, even though pentane has the longer chain length? Why is that the case? That is because pentane and butanol have different functional groups. So let's go ahead and take a look at the homologous series we have and the functional groups they possess. We have divided this into three. We have alkane, alkenes, and alkynes, followed by aldehydes, ketones, and haloalkanes, and lastly, alcohols and carboxylic acids. We don't talk about esters when it comes to structure and physical properties. We just talk about these 8 homologous series we have in front of us. So all alkanes, alkenes, and alkynes possess London forces. We call alkane, alkenes, and alkynes hydrocarbons, by the way. They only consist of carbon and hydrogen only. So they possess London forces. Of all our intermolecular forces we're going to talk about here, London forces are the weakest. So if you're comparing alkanes and aldehydes, aldehydes are going to have stronger intermolecular forces. If you're comparing alkenes and haloalkanes will have stronger intermolecular forces because London forces is the weakest. And that's what alkanes, alkenes, and alkynes possesses, right? But then if you were to compare an alkane with another alkane, then we would have to look at the chain length or the branching because they have the same functional group, right? So the explanation, you can see here that the weakest intermolecular forces is London forces. You can see it here. And then the least amount of energy is required to break this intermolecular force. If it's weak, obviously it's going to require less energy to overcome the intermolecular force. And after that, we have aldehydes, ketones, and haloalkanes. Not only do they possess the London forces, they also possess dipole forces. This is one thing that a lot of people, they usually don't realize. In aldehydes, ketones, and haloalkanes, we actually do have London forces. But then on top of London forces, we have dipole-dipole forces, which are stronger than the London forces, leading to aldehydes, ketones, and haloalkanes having stronger intermolecular forces compared to hydrocarbons, alkanes, alkenes, and alkynes. So dipole-dipole forces are stronger than London forces, but weaker than hydrogen bond. We're going to talk about that later on. But right now, the point I just want to make is that dipole-dipole forces are stronger than London forces. So more energy will be required to overcome dipole-dipole forces compared to London forces. And lastly, we're going to look at alcohols and carboxylic acids. Alcohols and carboxylic acid, they possess London forces, dipole-dipole forces, and hydrogen bonds. This hydrogen bond is the strongest. It is stronger than London forces and dipole forces. This will lead to alcohols and carboxylic acids having the strongest intermolecular forces. And then the most amount of energy will be required to break these intermolecular forces in carboxylic acids and alcohols. So that's our homologous series and their functional groups. But let's just touch on alcohol and carboxylic acid for the time being. The intermolecular forces in carboxylic acids, well, let me say the hydrogen bond in carboxylic acid is stronger than that in alcohol. That is because carboxylic acids have 2 sites of hydrogen bonding, while alcohols only have 1 site of hydrogen bonding. So if you were to compare butanol and butanoic acid would have a higher boiling point because carboxylic acids have 2 sites of hydrogen bonding compared to alcohols with only 1 site of hydrogen bonding. Right, so that is functional group and physical properties. Now let's go ahead and see how we phrase our answers when we talk about the relationship between functional group and physical properties. Increasing polarity of functional group increases the strength of the intermolecular forces, increasing boiling point, melting point, and viscosity, but decreasing the vapor pressure. Right. Another way of phrasing when you're answering these questions, let's say we have a question that is saying, why is the boiling point of butane-1-ol higher than that of butanol? How would you phrase your answer in that question? You would say that alcohol consists of hydrogen bonding, which is stronger than dipole-dipole forces in aldehydes. So that will lead to alcohols having an increase in the strength of intermolecular forces. More energy required to overcome the intermolecular forces, increasing the boiling point, melting point, viscosity, but leading to a lower vapor pressure. We have talked about esterification, the formation of ester when an alcohol and carboxylic acid react in the presence of concentrated sulfuric acid and heat. Now let's take a look at addition reactions. This is a reaction where an unsaturated organic compound turns into a saturated organic compound. The first one, we have hydrogenation, which is an alkene plus hydrogen to form an alkane. The second reaction, halogenation, alkene plus halogens to form haloalkane. Hydrohalogenation, that's where we have an alkene plus a hydrogen and a halogen to form a haloalkane. And then lastly, hydration, we have an alkene plus H2O to form an alcohol. Let's go ahead and take a look at how these reactions take place. So our first example is hydrogenation. It is the addition of hydrogen, H2, to an alkene to form an alkene. It is hydrogenation because it is the addition of hydrogen, hydrogenation from hydrogen. Okay, so again, an alkene plus 2 hydrogen atoms to form an alkane. But how does this happen? Let's take a look at this example. We have built 2 in. We have this double bond right here. So in hydrogenation, that double bond is going to break, and these 2 hydrogens will go and fill those spots, right? One hydrogen is going to come to this carbon, and another hydrogen is going to go to the other carbon. And then as a result, we're going to end up with butane, our alkene. So this is hydrogenation. It is simply the addition of 2 hydrogen atoms to an alkene to form an alkane. So if it was pent 2 in, then our alkane that is formed when hydrogenation takes place would be pentane. That's how it works. The double bond breaks and the hydrogen atoms gets attached to the 2 carbons. The reaction conditions. For this reaction to take place, we need heat and a catalyst. Not just any catalyst. We need either platinum, nickel, or palladium. We do need to memorize these reaction conditions because time after time they are required in an exam. So that is hydrogenation. Let's take a look at hydration. Think about the word hydration in the everyday sense. You think about water when you hear hydration. So that's what's taking place here. It's an alkene plus H2O to form an alcohol, right? In the presence of concentrated sulfuric acid. So let's go ahead and take a look at how that comes about. So again, we're starting with an alkene. We have a double bond, and the double bond is going to break. Of these H2O, in H2O, we know that we have OH and a hydrogen, right? A hydrogen is going to get attached to the carbon, and the OH is also going to get attached to this carbon right here. And this is how we ending up with an alcohol during hydration. The reaction conditions, it's either we have excess water in concentrated sulfuric acid or diluted sulfuric acid. There's one thing I want us to talk about before we can move to the next addition reaction. I want us to talk about the position of this OH. The position of this OH, right? Why is the OH not on this carbon right here? Why is it not here on this last carbon? Why don't we have OH right there? Why is it on the second carbon? That is another concept we need to know. The hydrogen will always go to the carbon with the most number of hydrogens, and then the OH is going to go to the carbon with the least number of hydrogens, right? So here, that is why the hydrogen is coming to the first carbon, because the first carbon, it already has 1, 2 hydrogens, while the second carbon only has 1. So the hydrogen will go to the carbon with the most number of hydrogens, and the OH will go to the hydrogen with the least. So that is why that OH is in the carbon in the middle, right? You don't just randomly choose where to place the OH. You have to use this idea. Halogenation, obviously derived from halogen, is the addition of 2 of the same halogen atoms, Cl2, Br2, so on and so on. So we're starting with an alkene plus 2 halogens to form a haloalkane. So let's go ahead and take a look at our example. We have an alkene. There goes our double bond is going to get broken, obviously, and we can see that the halogens fill those 2 spots. Nothing really complicated here. And the reaction condition, non-polar solvent. That is halogenation. Nothing complicated really. And then now our last addition reaction, hydrohalogenation. This is the addition of a halogen atom attached to a hydrogen atom. You can clearly see that we have a hydrogen and a halogen. The double bond breaks. There goes our hydrogen and our halogen. So again, in this example, if we had 3 carbons, for instance, then the H would go to the carbon already having most number of hydrogen, and then the halogen is gonna go to the carbon with the least number of hydrogens. But in our case, they have the same, so there isn't really much we can do there. So this is the summary for the addition reactions we have, the reaction conditions, and the reaction equations. We always start with an alkene in all addition reactions. Let's talk about esterification. It's always better if we talk about esterification and then learn how to name esters. Okay, so in esterification, it is a reaction in which a molecule of water is removed from 2 compounds and a new bond is formed between what remains of the alcohol and the carboxylic acid. This is taking place in the presence of a catalyst, H2SO4, sulfuric acid. So what are we saying? We're saying that in order for esterification to take place, we need an alcohol and a carboxylic acid. Okay, so I have an example here in front of me. So let's go ahead and make sense of this example. Let's take a look at the alcohol we have. We have methanol because of 1 carbon, and here we have our OH, right? Functional group for alcohols, plus the methanoic acid. Methanoic acid because meth, 1 carbon, and oic acid is the suffix we use for carboxylic acids. So we have the functional group, double bond oxygen and OH. So what happens when this reaction takes place? The alcohol loses a hydrogen and the carboxylic acid loses OH. This will form H2O, as you can clearly see on the product side. And then what is left of the alcohol and the carboxylic acid bonds to form an ester. So as you can see, this is from the alcohol we have. This is from methanol. And this right here is from methanoic acid, right? So every time when we have an alcohol and a carboxylic acid in the presence of sulfuric acid, the alcohol loses a hydrogen, the acid loses OH, they form H2O, and what's left bonds together to form an ester. So this is esterification. Most of the time in the examination, they can tell you that we have propanol and butanoic acid. Write the reaction in terms of structural formula that will take place in the presence of sulfuric acid. Then you would have to draw something like this. But there's a few examples where we are going to do that. So don't worry about that. Okay. Now let's take a look at this structure. This is the structure of an ester. Okay. So why are we saying is an ester? Let's start there first. Obviously, we've went through the 9 homologous series and the structure of the functional group. And we can clearly see that this is the functional group of an ester. So we know for sure it's an ester. But what I want us to do is to name this ester. What would be the IUPAC name of this ester? So right, this is what you do. You come and you put a line between the 2 oxygens in this fashion. So the part with the single bond oxygen comes from the alcohol, and the part with the double bond oxygen come from the carboxylic acid. So the name for this ester would be ethanoate. I'm about to explain that in a second, right? So ethyl is coming from the alcohol that was used. We have ethanol that was used to form this ester. So it will be ethyl. And then we have ethanoic acid that is used to form this ester. So it is ethanoate. Okay, so what if the alcohol that is used is propanol? Then what will be the name of our ester?
What if the alcohol that was used is propanol? Then we would have propyl ethanoid. Propyl ethanoid. And then maybe another question we can ask is, what if the acid that was used was butanoic acid? Then the name would be ethyl butanoid. So the first part of the name is determined by the alcohol, and the second part of the name is determined by the carboxylic acid used. So that's how it works. Let's take a look at this following example. Do you want to do this first before I do it? Assuming that you did that, let's go ahead and take a look. So first things first, we need to put a line here to separate the oxygens. As soon as we do that, everything else becomes crystal clear. The part with a single oxygen bond, this is an alcohol, right? And then where we have a double bond on the oxygen is the carboxylic acid. So let's take a look. The alcohol that is used is ethanol, so we will have ethyl. And let's take a look at the acid used, that is propanoic acid. So we have ethyl propanoid. Ethyl propanoid. So ethyl from the alcohol used, ethanol, and propanoid from the acid used, propanoic acid. So this is how we name esters. It's not really that difficult. We just need to figure out which alcohol was used and which carboxylic acid was used, and we are good to go. Let's take a look at how we draw the structure when we are given the IUPAC name. Here we have ethyl hexanoid. So the alcohol that was used is ethanol, and the carboxylic acid that was used is hexanoic acid. So how will the structure look like? So let's go ahead and do that. So we have 1, 2, and then this is our alcohol. Well, let's just go ahead and draw the entire reaction, right? Let's not only draw the structure, let's just draw the entire reaction. So this is the alcohol that was used, ethanol, and then plus the acid that was used. The acid that is used is hexanoic acid. So this is the functional group of carboxylic acids, and now we just need to add hydrogens everywhere else. So we're just gonna go ahead and do that. We need 6 carbons since we have hexanoic acid. So let's see how many carbons we have. 1, 2, 3, 4, 5, 6. So there we good to go. We have our ethanol and our hexanoic acid. So like I've been proposing, the alcohol will lose a hydrogen and the carboxylic acid will lose OH. This is going to form H2O. So the product here of our reaction, we're gonna have 1, 2, and the oxygen that remains from the alcohol. So let's just leave that there. And then after that, we have a carbon from the hexanoic acid. So 1, 2, 3, 4, 5, 6. There we go. We have our ester, and the H2O that is removed, we write it like this. We don't write H2O, because if the question says in terms of structural formula, writing H2O in this manner is not correct, because that's not the structural formula. So this is how we must write it. That is the correct way of doing it. And for this reaction to take place, we need H2SO4. So there we go. That is the structure of ethyl hexanoid. It's a reaction between ethanol and hexanoic acid to give us the ester ethyl hexanoid. Let's move to the last question. So here we're supposed to draw the structural representations for the organic compound propyl ethanoid.
So propyl, the alcohol that was used is propanol. Ethanoate, the alcohol that was used, not the alcohol, but the acid. The carboxylic acid that was used is ethanoic acid. So how will the structure of our ester look like? Maybe if you're not familiar with the concept yet, if you didn't really make sense of the last example, draw the entire reaction in terms of structural formula and it will make more sense. But if you made sense of that, you would know that we would have 1, 2, 3. This is from the alcohol, and then from a carboxylic acid we have 1 double bond oxygen and the last carbon. So there we go. Now we just need hydrogens everywhere else and we are done. So yeah, it's not really a complicated reaction at all. Esterification is quite easy, it's quite straightforward, to be honest. So let's make sense of this. Let's see if we've done everything in the right way. So propyl, the alcohol that was used is propanol, that seems to work, and ethanoate, the carboxylic acid that was used is ethanoic acid. Let's take a look at elimination reactions. There's a relationship between addition reactions and elimination reactions. In all addition reactions, one of the reactants is alkene. And then in elimination reaction, one of the products is always an alkene. Let's take a look at the first one, crackine. You can see that one of the products is an alkene. If you take a look at dehydrogenation, the same is true. Alkene, dehydrohalogenation, alkene, and dehydration, alkene. So in addition, if you are adding H2O, the name of the reaction was hydration. And now in elimination, if you are removing H2O, the name of the reaction is dehydration. Same is true with hydrogen. When we were adding a hydrogen, it was hydrogenation. Now that we are removing a hydrogen, well, 2 hydrogen atoms, we have dehydrogenation. And the trend continues with dehydrohalogenation. We're removing a hydrogen and a halogen. So there we go. These are the 4 elimination reactions we have. Let's go ahead and take a look at them. Okay, first things first, let's take a look at dehydrohalogenation. In dehydrohalogenation, we are removing a hydrogen and a halogen. Let's go ahead and take a look at this example. We have a haloalkane. We can see that by the presence of a halogen, that bromine we have right here. And then we add NaOH, sodium hydroxide, and as you can see, we end up with an alkene. A hydrogen has been removed and a halogen has been removed. The halogen attaches to the sodium and the hydrogen attaches to the OH, and our byproduct is NaBr and H2O. And then now a double bond forms because we have 2 atoms that are now removed. The reaction conditions: concentrated strong base, right? We need this concentrated strong base to remove the hydrogen and the halogen. Right, there we go. So that is dehydrohalogenation. Let's go and take a look at dehydration. In dehydration, we start with an alcohol because that's where we will find our OH. And then we're just removing OH and a hydrogen. And then our byproduct will be H2O. As we have removed a hydrogen and OH, right? That will give us H2O. We need a dehydrating agent, H2SO4, H3PO4, plus heat. If we have that, then dehydration can take place. Right, so for dehydration, we start with an alcohol and we remove H2O. And then for hydration, we start with an alkene, we add H2O and we get alcohol. Hydration and dehydration You can almost say that they are the opposite of one another. Right, let's move to dehydrogenation. Obviously, in dehydrogenation, we are removing 2 hydrogens, as we can clearly see in this example. And the catalyst we need for dehydrogenation is platinum. Now what we need to talk about is cracking. We have thermal cracking, where we need heat and high pressure, and we have catalytic cracking, where we need a catalyst, silica, and also some heat. Let's go ahead and take a look at thermal cracking. So thermal cracking, we just apply heat, we just apply high pressure, and our alkane breaks into an alkane and an alkene. That is thermal cracking, nothing really complicated here. The same is true with catalytic cracking. We start with an alkane and then it breaks up to form an alkane plus an alkene. Let's take a look at substitution reactions. We have 2 substitution reactions we're going to focus on: halogenation and hydrolysis. Okay, let's take a look at halogenation. In halogenation, we start with an alkene, we add a halogen, and we end up with a haloalkane. In hydrolysis, we start with a haloalkane, we add NaOH diluted to form an alcohol, and NaX, where X is the halogen, right? So I want you to realize something here. We need NaOH, which is diluted, because in elimination reaction, when we want to eliminate a hydrogen and halogen, we need NaOH, which is concentrated. So when it is diluted, it substitutes. When it is concentrated, it eliminates. Right. This concept is going to be tested at some point of time. You need to memorize this.
This is an organic chemistry topic test. After we have went through all the videos, introduction, isomers, reactions, so on and so on, you should be able to get everything. Let's go ahead and take a look. So 1.1, which one of the following is the general formula of alkanes? This is just memory work, right? No need to solve anything. We should be able to see that the correct answer is C, because we have memorized that already. And then 1.2, which one of the formula below represents an alkane? Which one of the formula below represents an alkane? This is different from the first question. The first question was saying the general formula, and then in the second question we're looking for the formula that represents an alkane. So A cannot be the correct answer because it is C2H4. The general formula there is CnH2n, which will be an alkene. Same is true with option B, that is an alkene. And then option C, we have C14H30. In terms of N, this would be CnH2n. If we have 14 here, that would give us 28. So because we have 30, it means that is CnH2n plus 2. So the correct answer in 1.2 is C. Right. And then in 1.3, the empirical formula of hexanoic acid. So let's go ahead and look for hexanoic acid. In option A, we have C3, so that cannot be hex. And then B and C. B is not hexanoic acid because the formula there is CnHNO2. I don't know what that is. We don't have that in our context, right? But if you look at option C, that is hexanoic acid. So the answer to 1.3 is not C. It is actually not C. The answer is D. Let me show you how. The question says the empirical formula, right? Empirical formula is the smallest whole number ratio. So C is hexanoic acid, but C is not the empirical formula of hexanoic acid. Right. This is one of those questions where you walk out of the exam thinking, oh, okay, I got it right, only to find out that, damn, I missed the point. So What is written in all caps is very important in this question. Make sure you don't miss that. So the correct answer, 1.3, is actually D and not C. Right. 1.4. Which one of the following terms describes hydrocarbons that contain only single bonds? So isomers, that cannot be the answer. But if you look at B, it says saturated. Hydrocarbons with only single bonds, that is alkane. Right? And we know that alkanes are said to be saturated. So the correct answer to 1.4 is B. 1.5. Which one of the following combinations correctly indicates the strongest intermolecular forces found in ethanoic acid and methyl propanoate? Right, so ethanoic acid, we know that we have two sides of hydrogen bonding. So already we know that B cannot be the answer, right? We're looking at A, C, and D. But what is the strongest intermolecular force in methyl propanoate, which is an ester? The strongest intermolecular force there is dipole. So the answer to 1.5 is D. Right, in ethanoic acid we have hydrogen bonding, in methyl propanoate we have dipole. Okay. 1.6. The type of reaction that takes place when a carboxylic acid and an alcohol react in the presence of an acid. Obviously that is option D, which is esterification. 1.7. Which one of the following isomers has the lowest boiling point? So let's take a look. In A, we need to have, like, I'm gonna have some sort of a structural formula in order to see what is going on with these. In A, we have 1, 2, 3, 4, 5, 6 carbons. So that is 1, 2, 3, 4, 5, 6. We have something like that in A. And then in B, we have 1, 2, 3. And then this right here is a branch, right? 2 branches to be specific. Why do I say 2? I'm saying 2 because it's CH3. So it can only be a branch. It cannot be part of the chain, because where can you fit 3 carbons, 3 hydrogens in a carbon and have 2 other carbons attached to it? So that is a branch. So we have 1, 2, right? Followed by a carbon. So that is B. And then C, we have 1, 2, and then we have a branch, as you can clearly see there, CH3. If it was CH2, that's going to be part of the chain, followed by 1, 2, 3. And then D, we have 1, 2, 3, a branch, followed by 1, 2. We are looking for the isomer with the lowest boiling point. So the isomer with the lowest boiling point will be the one that is more branched, which is clearly B, right? So the answer to 1.7 is B. We know that the more spherical a compound is, the less surface area it has, lower boiling point, and so on. Okay, 1.8. Which one of the following pairs of compounds are functional isomers? Which one of the following pairs of compounds are functional isomers? So functional isomers should be ketone, aldehyde, or carboxylic acids and esters. Right, these are the only functional isomers we have in our context. So A has something to do with alcohol, so already we know that it cannot be the answer. B, I don't even know what this is, butane or something, so it cannot be the answer. And then C, proper 1-ol. What is proper 1-ol? Right, does not even exist. So clearly the answer here in 1.8 should be D, propanoic acid and methyl ethanoate. That is an acid and an ester. Both have 3 carbons. So the answer to 1.8 is D. Let's take a look at 1.9. So in 1.9, which one of the following structural formula of the functional group? Which one of the following is the structural formula of the functional group of ketones? Obviously the answer is C here, because we have memorized it. No need to solve anything. And then the IUPAC name of the compound given. Obviously the first thing that you're going to look for is the longest carbon chain. So let's take a look. 1, 2, 3, 4. 1 2 3 4 1 2 3 4. So we can just go straight to make our lives a bit simple. So that is 4, right? So we know that it is butane, but we have these branches here. We're going to start naming from the side closest to the branch. So that will be 2, 2-dimethyl, which is option C. So the answer to 1.10 is C. Right. The long questions. Question 2. This structure follows the same exact structure in the exam. In the exam, you'll come across a table like this. Usually, right? Let me say 19 out of 20 times, right? You'll come across a table like this, and you're going to answer some questions based on the table. So let's take a look. 2.1.1. The letters A to F in the table below represent 6 organic compounds. Right. The first question, name the functional group of compound B. So compound B is 2-methyl butanoic acid. So that is a carboxylic acid, right? But what is the name of the functional group? Carboxyl group. So carboxyl group. There we go. If it was an alcohol, it would be hydroxyl group. And then 2.1.2, homologous series to which compound C belongs. Compound C, obviously we have this carbon bonded to 2 other carbons, right? And then oxygen. So clearly that is ketones. That is ketones. The homologous series is ketones. And then 2.2.1, we're looking for the IUPAC name of C. We already know that C is a ketone. Now we're just looking for the longest carbon chain. So let's go ahead and, see what is happening. So we have 1, 2, 3, 4, 5. Let's see if we have a longer chain. If we start here, we're going to have 1, 2, 3, 4, 5, 6. So this is clearly our longest chain. Right. So which side is closest to the functional group? If we start from the right, we're going to have 1, 2, 3. If we start from the left, we're going to have 1, 2, 3, 4. So clearly we're starting from the right. And then how many carbons? 1, 2, 3, 4, 5, 6. So we have hexane 3-O, right? Now we just need to account for this branch, which is on the 4th carbon. So that is 4-methyl hexane 3-O. There we go. IUPAC name of compound C. Let's take a look at 2.2. 2.2.2, the IUPAC name of compound D. So compound D looks like it is an alkane, right? So first things first, the longest chain. So this is 1, 2, 3, 4. That cannot be the longest. Let's see another option. 1, 2, 3, 4, 5, 6. Okay. And then if you start here, we're gonna get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 1, 2, 3. Seems like 6 is our longest. So let's circle that and see where our branches are located and name the organic compound. So this gives us 6. So we are interested in this. Right. So because it gives us 6 and it's an alkene, we already know that we're going to have hexane, right, as the suffix. Now the position of the branches. If we start from the left, we have 1, 2, right? On the 2nd carbon, we're going to have a branch. If we start from the right, 1, 2, 3. So we have to start from the left. That is the side closest to the branch. Okay. Which will lead to the least number. Okay. So on the 2nd branch, we have 2.2 dimethyl. 1, 2, 3, 4. And then on the 4th branch, we have ethyl. So we're going to have 2.2 dimethyl 4 ethyl hexane. So if you write this, you'd be very close to the answer, but you still be wrong. So we have identified everything the way we're supposed to. Our branches are in the correct position. We've numbered our carbons in the correct way. but when we write our name, the order must be alphabetical. So we're supposed to actually write it as 4-ethyl 2.2 dimethylhexane. Right, we just changed and we started with ethyl before methyl because ethyl comes before methyl alphabetically. We don't care about the di, right? We don't care about the di. Right, so don't think that I'm being too strict. You will get penalized if you don't write the Arabic name in alphabetical order. Right, this is not a matter of preference, it's a must. We're supposed to write it like this. But anyway, stories. Let's carry on. 2.3, write down the name or formula of each product formed during the complete combustion of compound D. So compound D is an alkane, and combustion, burning in excess oxygen, right? And the products is always CO2 plus H2O. So the correct answer to 2.3, you shall write CO2 and H2O. This is the correct answer. Obviously, you can write carbon dioxide and water because we were looking for the name of formula, but that's what we are essentially looking for. 2.4.1, write down the structural formula of compound B. B is 2-methyl butanoic acid. So 1, 2, 3, 4, because it is but. It is butanoic acid, so it is an acid. That is where I'm going to position the functional group. And then 2-methyl, so we have a branch on the second carbon. So the second carbon has to be this one, right? Because we are going to start numbering from the side closest to the functional group, which is that one there, right? So this is 2-methyl butanoic acid. 1, 2, 3, 4. 1, 2, 3, 4. Right. I always make sure that I have the correct number of bonds. So there we go. 2-methyl butanoic acid. Right. 2.4.1. Let's go ahead and do 2.4.2. Structural formula of a chain isomer of compound A. Compound A is an alkene, right? So structural chain isomer is same molecular formula but different chains. So we can just write this. We can just write the but2 in because we're gonna have the same molecular formula but different position of the functional. But different chains. I'm sorry. That is different position of functional group is functional isomer. Here we're talking about different chains, right? So 1, 2, 3, 4. Let's put the double bond there and then fill out the hydrogens. So this is what we have, right? This is the chain isomer. Same molecular formula, different chains, right? So that is 2.4.2. I'm just trying to calculate the number of carbons, the number of bonds, and see if they're correct. Seems correct. 2.4.2. And then 2.5, let's go. A laboratory assistant uses bromine water to distinguish between compounds D and E. Okay, D is an alkane and E is an alkene. Right, let's hear the stories. She adds bromine water to a sample of each in 2 different test tubes. She observes that one compound decolorizes the bromine water immediately, while the other one only reacts after placing the test tube in direct sunlight. Write down the letter D or E of the compound that will immediately decolorizes the bromine water. So the compound that will immediately decolorizes the bromine water should be alkene, right? Because we're going to have an addition reaction take place there immediately without sunlight, as you would need if your compound is an alkene. And then 2.5.2, Name the type of reaction that takes place in the test tube containing compound D. Compound D is the alkane, right? Ane and in. My handwriting is so bad. So the type of reaction that takes place if your organic compound is an alkane should be substitution, right? Substitution. Yeah, because we have an alkane and then we are adding Br2 essentially. So we cannot be eliminating anything there. So obviously it is going to be substitution, because in an alkane you cannot have addition either way. 2.5.3 Structural formula of the organic compound formed in the test tube containing compound E. So compound E, when it reacts with bromine water, addition reaction is going to take place, because we have an alkene. I've said it before that if a reaction starts with an alkene, it is an addition reaction. No questions asked. So this is the alkene, right? 1, 2, 3, 4. Because it is said that we have built 2 in. Okay, so this is the alkene that we start with. And then we add, it is in bromine water. So it is essentially plus Br2. So obviously what is going to happen, this double bond is going to break. And what are we going to have? Right, we're going to have Br and Br, right? There we go. That is the structural. That is the structural formula of the organic compound formed in the test tube containing compound E, right? Which is built 2 in. That is question 2. These are the types of question that you expect. Question 3. Let's take a look. There's a mistake in this question, right? Compound A was supposed to be propanol and not propanol. So this is supposed to be propanol and not propanol, right? If it is propanol, 3.1.1 and 3.1.2 won't make sense. So that had to be propanol. Okay, so let's go through the questions after we fix the error. A is not propanol, it is propanol. And then the first question will be, to which homologous series do the above compounds belong? If A is propanol, you can see the issue that arises, right? Do you say alcohols or do you say ketones? But if A is propanol, then the answer is simply ketones. That is the homologous series to which they belong. All right. And then 3.1.2, the melting points of compound A, B, and C are compared. The question says, write down the control variable for this comparison. The control variable is what's the same throughout the compounds that you're comparing, right? If A is propanol, then the control variable would be functional group. Another possible answer would be homologous series. Homologous series. Right, that is another option you would have there. Okay, and then 3.1.3, the melting points the melting points of compounds C and D are compared. Fully explain the difference in melting points of these two compounds, C and D. So C is pentane 3-one, so it is 1, 2, 3, 4, 5 pentane 2, not pentane 3 but pentane 2. Okay, so this is what we have, that is compound C. Okay, and then compound D, we have 3-methyl butanol, so that is 1, 2, 3, 4, because it is but, so double bond oxygen, and then we have a carbon there. So you can see that these two organic compounds, they differ in terms of branching, right? D is more spherical, D is more branched compared to C. So how would you then answer this question? Look at the mark allocation. It is 4 marks, right? So you need to touch on quite a few things in order to get these entire 4 marks. So the first line, you have to state that compound D is more branched compared to compound C. We can clearly see that, right? And then the second line, here you have talked about branching. You write it in full, right? That compound D is more branched compared to compound C, right? And then now you will go on to say the less branched a compound is, the stronger the intermolecular forces. So compound C, so the intermolecular forces in compound C are stronger than the intermolecular forces in compound D. So right, the IMF, the intermolecular forces in C, are greater than the intermolecular forces in D. Please don't write it like this. Don't just say 1 branching 2 IMF greater. No, don't do that. Write it in full sentences, right? I'm just doing this for the sake of time. And then the third point, more energy would be required to overcome the intermolecular forces in compound C, right? More energy is going to be required to overcome the intermolecular forces in compound C, right? And then number 4, the finishing line, leading to a higher melting point, boiling point, viscosity, but a lower vapor pressure in compound C. So that is how you explain the difference in the melting points between these two compounds. 3.1.3. Let's take a look at 3.2. So 3.2, the table below shows the results obtained from an experiment to determine the vapor pressure of different straight chain primary alcohols at 300 kelvins, I would assume, right? And then 3.2.1, we're supposed to define the term vapor pressure. I'll let you do that. And then 3.2.2, write a suitable conclusion for this investigation. So let's take a look at our data. We have C1, C2, C3, C4, C5, C6. And then the vapor pressure 16.8, 7.88, it keeps going down. So clearly, as the chain length increases, the vapor pressure decreases. That is a suitable conclusion. As the chain length increases, the vapor pressure decreases. Okay. And then 3.2.3, write down the IUPAC name of the alcohol with the highest boiling point. Obviously, we know that the higher the boiling point, the lower the vapor pressure. So this is the alcohol with the highest boiling point, as it has the lowest vapor pressure. So that is C6. So because it is 6,6, we're going to have why am I saying bute? Wow. We're going to have hexane 1-ol. Hexane 1-ol. 3.2.3. Now let's do 3.2.4. The experiment is now repeated at 320 kelvins. Will the vapor pressure of each compound increase, decrease, or remain the same? Yes, the vapor pressure of each compound will increase. The vapor pressure of ethanol would still be greater than that of propanol, and that of propanol will still be greater than that of butanol. Let's see. 2.2.1, the IUPAC name of compound E. Okay, so let's go ahead and take a look at compound E. We have a carbon with a double bond, so that is a characteristic of an alkene. Okay, how many carbons do we have in our longest chain? Let's see. If we start numbering from this carbon, we're gonna have 1, 2, 3, 4. Even if we go down, we still have 4 carbons on our longest chain. So that seems like we have 4 carbons on our longest chain. So for 2.2.1, we know that we have bute. Let's go ahead and figure out everything else. We have to start numbering from the side closest to the double bond. Okay? If we are saying that we have 1, 2, 3, 4 carbons, then if we start numbering from this side, then we will get to the double bond first, okay? Because if we start numbering from this side, then the double bond will be on the third carbon, and that's not what we want. We want the side closest to the double bond, which will be this side. So this is our longest carbon chain, okay, which is bute. So we have bute 1 in 1 because our functional group is on the first carbon, okay? And as you can see, we have methyl and methyl.
1-methyl is on, so we have 2 point, so this is the second carbon and this is the third. 2.3 dash dimethyl but1-ene. Okay, right, so that is our IUPAC name of compound E. 2.2.2, we are looking for the IUPAC name of H. So let's go ahead and take a look at H. Okay, on H, carbon double bonded to oxygen, and this carbon is sandwiched by 2 other carbons. That is a ketone. So I'm gonna have butane 2-one. Okay, I think even if you don't include these 2, it would still be correct, because if you have 4 carbons and on a straight chain, right, and it is a ketone, then the oxygen bonded to the carbon should be on the second carbon. If that is not the case, then it becomes an aldehyde. So butane 2-on. But I also think that if you don't put these 2, you would still be correct. That is 2.2.2. Okay, let's move to the question that follows. We have butane 2-on. Okay, right. 2.3, we are looking for the structural formula of compound B. So let's go ahead and take a look at compound B. That is 2.3.1. So compound B, a carbon with 3 hydrogen, followed by 3 carbons with 2 hydrogen each. So 1, 2, 3 with 2 hydrogens each. Okay, and then after that we have another carbon which is double bonded to an oxygen, one other oxygen which is bonded to its carbon. Okay, so this is the structure you're supposed to have for compound B. Obviously, we need to fill out our hydrogens. Okay, you cannot leave it like this. Only I can do that and not you. So this is the structural formula of compound B. Let's see if we have the correct number of carbons. So we have 1, 2, 3, 4, 5, 6. This is 1, 3 makes it 4, 5, 6. I think we are good to go. Okay. Structural formula of compound C, 2.3.2. Let's go ahead and take a look at that. 2.3.2 structural formula of compound C. We have 4-ethyl-3.3 difluorohexane. So I'm going to start by taking care of hexane. I need 6 carbons. So 1, 2, 3, 4, 5, 6. On the third carbon, I have difluoro. There we go. And on the fourth carbon, I have ethyl. Ethyl will look something like this. Okay. I have a branch with 2 carbons. Right. So now I just need to fill out my hydrogens and I am done. Okay. So let me leave that for you. Go ahead and fill out all the hydrogens that are required. Okay, right, so this is the structural formula of compound C, 2.3.2. 2.3.3, general formula of the homologous series to which compound E belongs. Compound E is an alkene, so the general formula should be CnH2n. Yes, not plus 2, not minus 2. Just CnH2n. 2.3.4, structural formula of functional group of compound F. Compound F, carbon double bonded to an oxygen sandwiched by 2 other carbons. That is a ketone. The structure of the functional group should look like this. Okay, we should not have carbons on these. We should not have hydrogens on these 2 carbons. So if you put hydrogens on those carbons, then it is then not correct. Okay, you are now drawing the structure of propanone, right? And no longer the functional group of ketones. That is 2.3.4. 2.3.5, IUPAC name of the alcohol needed to produce compound B. So for compound B, we have the structure. Let's use the structure instead. Okay, if you come here and put a line, the carbon that is bonded, or the part of the structure that is bonded to one oxygen is from the alcohol. Which alcohol has one oxygen? Not one oxygen, but one carbon, okay? That is methanol, right? Yeah, the alcohol with one carbon is methanol. 2.4.1. 2.4.1, we're looking for letters of a compound that is the letter of a compound that is a functional isomer of compound G. So if you take a look at compound G, we have an acid because of the functional group, which we can identify right there. And that acid has 1, 2, 3, 4, 5, 6 carbons. So we are looking for an ester with 6 carbons. It will be a functional isomer of compound G. If you look at B, in B we have 6 carbons. So the answer to 2.4.1 is B. That ester right there with 6 carbons will be a functional isomer of G. And then two compounds that are chain isomers of each other, okay? G and D. D is hexanoic acid. It is a straight line hexanoic acid, okay? And compound G, it is an acid with 6 carbons. So they should be chain isomers of each other. Same molecular formula, just different chains.
Is this organic compound a primary, secondary, or tertiary alcohol? We're supposed to give a reason for the answer. So let's go ahead and take a look. Right, so in compound A, let's just zoom in on compound A. We have 1, 2, 3, 4 carbons. So that should be butanol, right? We do have a branch here that I'm not accounting for, but we're going to take care of that. So let's take a look. Let me just circle that. This is our longest chain. We can take this as our longest chain. Even though if we go up, we would still get the longest chain of 4 carbons. Let's just take that as our longest chain. And then we have a branch on the second carbon and the functional group. Right, that is what we are dealing with. Let's go back to the question. Is it a primary, secondary, or tertiary alcohol? Well, this is a tertiary alcohol. So let me just write that down first and then explain to you why I'm saying so. This is a tertiary alcohol, right? Why do we say that it is a tertiary alcohol? It is because, take a look at these. This carbon that is bonded to OH. The carbon that is bonded to OH is bonded to 1, 2, 3 carbons, right? So if the carbon that is bonded to OH is bonded to 3 carbons, it makes it a tertiary alcohol. If it was bonded to 2 carbons, it would make it a secondary alcohol. And then if it is only bonded to 1 carbon, it would make it a primary alcohol. So right, it is a tertiary alcohol because the carbon bonded to OH is bonded to 3 other carbons. There we go. So that is 2.1.1. Let's take a look at 2.1.2. Write down the IUPAC name for the above mentioned compound. Okay, so like we have figured out, we have 4 carbons on our longest chain. So that is butane. And then which carbon is our functional group found? Well, if we start counting from the left, we have 1, 2, 3. But if we start counting from the right, we have 1, 2. So clearly we have to start numbering our carbons from the right. So we're going to have butane, 2, all. But we need to account for that branch there. We need to account for that branch. So on the second carbon, we have 2-methyl. So there we go. 2-methyl butane 2-ol. That is the IUPAC name of our compound A. 2.1.3. 2.1.3. The above mentioned compound undergoes an elimination reaction. Write down the structural formula of the product that is formed. Elimination reaction. So let me just write that structural formula without condensing it. So this is OH,
and then hydrogen. We need another. Okay, here we have a branch, so let's put that there. And then elsewhere we have hydrogens. Okay, so which elimination reaction can an alcohol go through? Because this is an alcohol that you're dealing with, right? So the elimination that an alcohol can go through is dehydration. It is dehydration. The alcohol loses one hydrogen and an OH, right, making it H2O as dehydration. That is the only elimination reaction alcohols can undergo through, right? So it means that the structural formula of the major product formed should be an alkene, right? This question is very specific. Major product, right? We have a major product and a minor product for these reaction. We have a major, well, for the product of an elimination reaction of alcohol, right? Dehydration. We have a major product and a minor product. So this is just the alcohol. This is not the answer. This is not the answer. This is just the alcohol. We just draw in the structure of the alcohol so that we can better make sense of it. So the major product of dehydration that compound A will undergo will look like the following. So we have 1, 2, double bond, carbon, carbon. So there we go. And then hydrogen everywhere else. Hydrogen everywhere else. So 4 bonds on that carbon, it is satisfied, and let's just fill out hydrogens everywhere. So let's check the number of bonds. This 1, 2, 3, 4. So everything is fine. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, right. You have to calculate the number of bonds to avoid making any mistake. We also need our branch. I'm forgetting to put the branch here because we have a branch here on the second carbon. So we don't have a hydrogen here, but rather we have a branch. So that is what we have. That is what we are dealing with. Let's check if the number of carbons is still intact. 1, 2, 3, 4. 1, 2, 3, 4. Okay, I'm happy with that. Right, let's move to the question that follows. 2.2, 2.2.1. Consider the organic compound B. 2.2.1. Define the term functional isomer. Okay, so compound B is pentane 3-on, so that is a ketone. But well, the question wants us to define the term functional isomer, so let's go ahead and do that. Functional isomer, organic compounds with the same molecular formula but different functional groups. Same molecular formula but different functional group. That is a functional isomer. And then 2.2.2, I'm expecting that the question is going to have something to do with isomers. Write down the homologous series to which the above mentioned compound belongs. Okay, compound B. This is 2.2, and 2.2.2 is a sub-question of 2.2.2. Okay, I was starting to ask myself which above mentioned compound, because I was thinking 2.2.1, but it is compound B that we are referring to. So compound B is a ketone, but the name of the homologous series is actually not ketone. It is ketones. It is in plural, by the way. Yeah, it's one of those things that we usually overlook. But the name of the homologous series is not ketone. It is ketones. Yeah, if you go to your exam guidelines, that is exactly what you're going to find. You're not going to find the homologous series ketone. No, the homologous series is ketones, right? We just been, more precise. We leave in no stone unturned. Okay, that is 2.2.2. Let's do 2.2.3. IUPAC name of its functional isomer. So the functional isomer of ketones is aldehydes, right? The functional isomer of ketone is aldehydes, right? They have the same, well, you know, a aldehyde looks very similar to ketone, but the only difference is that the double bond oxygen is at the end. So here we have pentane 3-on. So the ketone that you're looking for is pentanol. That is, oh well, the aldehyde, not the ketone I meant. The aldehyde that we're looking for is pentanol. Pentanol and pentane 3-on are functional isomers. So what are we looking for? IUPAC name of its functional isomer. Oh, okay, we're done then. We're looking for the IUPAC name. I thought we were looking for the structure, right? But we're just looking for the IUPAC name. The IUPAC name is pentanol, right? 2.2.3. What about 2.2.4? Letter that represents its positional isomer. So we are dealing with pentane 3-on, right? So the positional isomer is pentane 2-on. It has only one positional isomer, right? Because we have 1, 2, 3, 4, 5 double bond oxygen, right? If you put this oxygen here, it is pentane 2-on. Same is true with when you put it here, you'll still have pentane 2-on, because we have to start numbering from the side closest to the functional group. So we're looking for pentane 2-on here on our table. Letter that represents its positional isomer. Okay, let's take a look. Pentane 2-on looks to be compound E. It looks to be compound E. Because take a look at compound E. We have 1, 2, 3, 4, 5. So that is where our pent is coming from. And then on the second carbon, double bond oxygen. So there we go, pentane 2-on. That is compound E. So the letter that represents its positional isomer, the answer is E there. The answer is E. It is compound E, pentane 2-on. Write down the balanced equation using molecular formula for the complete combustion of compound F. So let's take a look at compound F. Compound F is 1, 2, well, not 2 anymore, but actually 3, right? So we have 5 carbons in total. We have 5 carbons in total. So that is C5. How many hydrogens do we have in total? We have these 3 here. We have these, which gives us 6. And we have 3. So that is 12, right? So H12. And then it is a combustion reaction. So it is excess oxygen to give us CO2 plus H2O. We just need to balance this equation. So C5, C1. What do? We put 5. In putting 5, the carbons are balanced. And then we move to the hydrogen. H12, H2. So we put 6. We put 6 in attempt to balance the equation. And now take a look at this. We have O2 here. And here we have 5 multiplied by O2, which is 10. Plus 6 multiplied by O2, which is 6. So this is 16. And then in order to get 16 on the left hand side, we must multiply with 8. So there we go. We have our balanced combustion reaction. Here we go.
Homologous series to which compound B belongs to. So let's go to our compound B and see what is happening. It will be easy to see that compound B is an ester because of this functional group that we have here. Compound B is an ester. So the answer to 2.1.1, that compound B is an ester. And then the second question, 2.1.2, we're looking for the IUPAC name of the same compound. So this is how you actually name an ester, ladies and gentlemen. You're going to come here to the structure and you're going to put a line that divides the oxygen with the double bond from the oxygen with the single bond. And then the part of the structure that has the oxygen with the single bond is coming from the alcohol. And the part of the structure that has
the oxygen with a double bond is coming from the acid, because we know that in order to form an ester you need an alcohol and an acid in the presence of H2SO4. So let's look at our alcohol. Our alcohol that was used in making this ester is methanol. Why are we saying it is methanol? Because of this single carbon right here. And the acid that was used to make this ester is propanoic acid. Why are we saying so? These 3 carbons that we have there. So when we name this ester, the name is going to be methyl propanoid. Methyl propanoid. Right. So this methyl here is coming from the fact that the alcohol that was used is methanol. If the alcohol that was used was butanol, then the name would start by saying butyl. And then the propanoid is coming from the acid that was used, propanoic acid. Let's move to the second equation, 2.2 and 2.2.1. An alcohol and an acid are heated in the presence of concentrated sulfuric acid to form compound B. Write down the role of the concentrated sulfuric acid in this reaction. So sulfuric acid in an esterification acts as a catalyst. So the answer to 2.2.1 is catalyst. It acts as a catalyst. It speeds up the reaction. You can also say that. And then the answer to 2.2.2, names of the alcohol and the organic acid used to prepare compound B. So we have already deduced which alcohol was used and which acid was used when we were naming our compound B, right? So now we're just gonna say the alcohol that was used is methanol and the acid that was used is propanoic acid. The acid that was used is propanoic acid. 2.2.3, name of the type of reaction that is taking place. Obviously the name of the reaction that is taking place is esterification. And other books will say condensation, which is also correct. I see that option time after time in memos. That is 2.2. Let's move to 2.3. So in 2.3, from the table above, consider compound C. So let's go to compound C and see what I have. Compound C, we have an acid. This is the functional group of an acid. Ethanoic acid to be specific. Let's go to the equations. 2.3.1. So the first question, 2.3.1, write down the name of the functional group of compound C. So we've already deduced that compound C is an acid, right? The name of the functional group of acids is carboxyl. So we have carboxyl group. That is the name of the functional group. And then 2.3.2, to which homologous group does compound C belong to? It is a carboxylic acid. That's an easy question to answer. It is a carboxylic acid. 2.3.3, differentiate between the terms functional group and homologous series. This question is actually just asking you to define homologous series and functional group. So let me just remind you, homologous series is a series of organic compounds that can be described by the same general formula. A series of organic compounds that can be described by the same general formula. While functional group, on the other hand, is a bond or an atom or a group of atoms that determines the physical and chemical properties of a group of organic compounds. There we go. You just need to define functional group and homologous series for 2.3.3. 2.4, for the table above, from the table above actually, consider compounds A, D, and F. And then the first question, write down the homologous series to which they belong to. So let's go to compound A. Compound A, we have an OH, which is the functional group of an alcohol. So we know that compound A is an alcohol. And then compound D, we also have another OH, so that is another alcohol. Let's look at compound F. It ends with ol, so we have another alcohol again. So A, D, and F are alcohols as far as the homologous series is concerned. So the answer to 2.4.1 will be alcohols, because A, D, and F are all alcohols. 2.4.2, compound A and D are isomers. As what type of isomer will they be classified? So let's go to A and D. A and D. So A, let me just write down A real quick for the sake of clarity. So for A, we have something like this. We have hydrogens everywhere else. And then let's look at D. So for D, we have condensed structural formula, which we're gonna write in full now. So we have a carbon with 3 hydrogens. We have the second carbon, and then on the second carbon we have 1 hydrogen and an OH, and then the third carbon with 3 hydrogens. So what type of isomers is compound A and D, not B? Excuse me, compound A and D. So compound A, the OH is on the first carbon, and then for compound D, the OH is on the second carbon. So they have the same molecular formula, but just different position of the functional group. So those are called positional isomers. So 2.4.2, the answer here is positional isomers. They will be known or referred to as positional isomers, compound A and D. The third question, 2.4.3, we asked to draw the structure of compound F. Let's go ahead and look at compound F. So for compound F, 2-methyl propane 2-ol. So let's start with the prop. So as soon as we see prop, we know that we need 3 carbons. So we have 1, 2, 3, and then 2-ol. This 2-ol tells us that the OH is on the second carbon. So let's have that OH right here. And then this 2-methyl, we have a branch on the second carbon. So we're going to have 1 carbon there. And then now we just left out with the hydrogens. And we have the structural formula of compound F just like that. Let's go ahead and move to 2.5. So 2.5, we're interested in compound G and compound E. 2.5.1, we're supposed to name compound G. Let's go to compound G. So compound G, the first thing that we must look for is the longest carbon chain. It is easy to see that this will indeed be our longest carbon chain. Let's count that. 1, 2, 3, 4, 5, 6. That is hex. And then as soon as I see Br, I know that it is a haloalkane, right? So it will be hexane. Now I'm just left with the branches. Where do I start numbering? If you start numbering from the left, on the second carbon, you have Br, you have bromo. And then if you start numbering from the right, on the second carbon, you have methyl, you have dimethyl, right? So the question now is, what takes preference between a branch and a halogen? Well, according to the exam guideline, nothing takes preference between the halogen and the branch. You just have to start numbering from the side that will lead to the smallest number. What do I mean by that? If we start numbering from the left, then we're going to have 2 for brom, right? And then this is 2, 3, 4, 5. And then we're going to have 5,5 for that dimethyl. And then these numbers will give us 12. If we start numbering from the right, we're going to have 2.82 for the dimethyl, right? And then we're going to have 5 for the bromo. So this is 2 plus 2 plus 5, which is equals to 9. If we start numbering from the right, we have the smallest number, and that's what we need to do. Nothing is going to take preference between the halogen and the branch. So we're going to have 5 bromo we're gonna have 5 bromo dash 2.2 dash dimethylhexane. 2.2 dash dimethylhexane, and that is the name of our compound G. The last question, structural formula of compound E. Let's go ahead and look at compound E. So compound E, we have 2.4 dimethyl pent 1-ene. So pent 5 carbons, 1, 2, 3, 4, 5, and then we have a double bond on the first carbon. We can tell from this pent 1-ene. So there we go, we have a double bond. And then on the second carbon, we have a branch with 1 carbon. And then on the fourth carbon, we also have another branch with 1 carbon. So now we're essentially done. We just left with filling out the hydrogens. So let's go ahead and do that. Yeah. So 1, 2, 3, we still need another hydrogen. And then 1, 2, 3. It's a painful exercise, but yeah, we have to do what we have to do. Compound A and B are functional isomers, like we are told in 3.1.1. What we are actually required to do is define the term functional isomer. Like all isomers, we have the same molecular formula, but in this case, the compounds differ by functional group. So the definition for functional isomer, same molecular formula, but different functional groups. Let's look at 3.1.2. Write down the IUPAC name of compound B. So the first thing you want to do is to determine which homologous series this compound B belongs to. Because of the structure of the functional group, compound B, it's a ketone. This carbon that is bonded to the oxygen is bonded to 2 other carbons. And because of that, we can conclude and say that compound B is a ketone. Now what we need is the longest carbon chain. Clearly, it is easy to see that this will be our longest carbon chain with 1, 2, 3, 4, 5, with 5 carbons. So we know we have pentane. We have pentane. Now what we need, or what we're looking for, is the position of the carbon that is bonded to the oxygen. If we start numbering from the left, we're going to have 1, 2, 3. If we start numbering from the right, we're going to have 1, 2, 3. So where we start numbering really doesn't matter. Our functional group is on the 3rd carbon. So we're going to have pentane 3 own. That is the answer to 3.1.2. Let's look at 3.1.3. How does the boiling point of A compare to that of pentane 1-ol? So we have pentane 1-ol and compound A. Write down only greater than, equal to, or lower than. So let's go to compound A. Compound A is an aldehyde because the carbon that is bonded to the oxygen is only bonded to 1 other carbon. So that makes it an aldehyde. So we have pentane 1-ol and pentanol. Pentane 1-ol is an alcohol. So it consists of hydrogen bonding. We have hydrogen bonding in alcohols. And then pentanol is an aldehyde. It consists of dipole-dipole. So the intermolecular forces in pentanol is dipole-dipole. So in order to answer this question, you actually need to know which intermolecular force is generally stronger between hydrogen bonding and dipole-dipole. Compound A will have a lower than boiling point compared to pentane 1-ol. Let me explain why that is the case in 3.1.4. The intermolecular forces in pentane 1-ol, which happens to be hydrogen bonding, are stronger than the intermolecular forces in pentanol, which is dipole-dipole. And then you know that if you have stronger intermolecular forces, then more energy is required to overcome those intermolecular forces in that compound. And then as a consequence, the alcohol or pent 1-ol will have a higher boiling point.
That is the answer to 3.1.4. Let's look at 3.1.5. How will the vapor pressure of compound B compare to that of pentane 1-ol? Right, only higher than, lower than, or equal to. Explain the answer fully. So compound B, like we've already deduced, is a ketone. And which intermolecular forces do we find in ketones? We have dipole forces. And then again, in pentane 1-ol, we have hydrogen bonding. In pentane 1-ol, we have hydrogen bonding. So that will lead to ketone having a higher than vapor pressure compared to pentane 1-ol, higher than vapor pressure. So what you have to understand is that the weaker the intermolecular forces, then the higher the vapor pressure. So between compound B, our ketone, and pentane 1-ol, pentane 1-ol has stronger intermolecular forces. So it will require more energy to overcome the intermolecular forces. And then as a consequence, it is going to have a lower vapor pressure. It is going to have a lower vapor pressure compared to ketone. Ketone will actually have a higher vapor pressure. So what you need to memorize, or what you need to know, is that the stronger the intermolecular forces, the higher the boiling point, the higher the melting point, but the lower the vapor pressure. You need to know that. 3.2.1. Let's define the term boiling point. That is not the temperature at which liquid turns to gas. Please, we no longer use that definition at this level. It is actually the temperature at which the vapor pressure equals the atmospheric pressure. The temperature at which the vapor pressure equals the atmospheric pressure. That is boiling point. 3.2.2. Run down the independent variable for this investigation. Let's take a look at what is happening in this question. Let us use compound C to E to investigate one factor which influences the boiling points of organic compounds. What I'm realizing real quick is that in compound C we have 1, 2, 3, 4. We have 4 carbons, right? And then in compound D, we have 1, 2, 3, 4, 5. We have 5 carbons in compound D. And then in compound E, we have 1, 2, 3, 4, 5, 6. We have 6 carbons in compound E. So it seems like our independent variable here, what we are changing is actually the chain length. We can see that from the number of carbons we have in the compounds. So the answer to 3.2.2 would be chain length, or the molecular mass, because as the chain length increases, then the molecular mass is also going to increase. So that is the independent variable. And 3.2.3, write down the type of van der Waals force that occurs between these organic compounds. So these organic compounds are all alkanes, right? Well, you can draw compound C fairly quick by saying C, 1, 2, 3 hydrogens, and then another carbon with 2 hydrogens, another carbon with 2 hydrogens, and the last carbon with 3 hydrogens. The same thing with compound D and E, they're all alkenes. So the force that is occurring in compound C, D, and E is actually London force. That is London force, or induced dipole forces. Well, let's look at 3.2.4. Write down the conclusion that can be drawn about the boiling point of straight chain alkanes. So let's look at our diagram. We can see fully well that as the number of carbon is increasing, our boiling point is increasing from -1 to 36.1 and lastly to 69. So we can conclude and say that as the chain length increases, the boiling point increases. If you had said molecular mass in 3.2.2, you would say that as the molecular mass increases, the boiling point increases. How can we boil down these complex concepts to a few bullet points? Well, if a reaction starts with an alkene and you get whatever product you're going to get, then that reaction is an addition reaction. If a reaction starts with whatsoever it is starting with and it ends up with an alkene, then that reaction is an elimination reaction. And if our first condition is not met and our second condition is not met, then that reaction is a substitution reaction. What am I even saying?
Let me show you what I'm talking about by answering this question. Let's look at 4.1. Consider reaction A and write down the type of reaction that takes place. So reaction A is right here. So let me go through my conditions and see which one is met. Do we start with an alkene? No, we don't. We start with a secondary alcohol. Do we end up with an alkene? Yes, we do. We have propene as our product, right? So we know fully well that from that only, our reaction is an elimination reaction. Our second condition is met. So the answer to 4.1 is elimination. It's elimination. It's elimination. Just because we know that if a reaction ends with an alkene, it's elimination. If it starts with alkene, it's addition. And then if none of that is correct, then it is a substitution reaction. Let's do 4.2 and 4.2.1. Reaction B represents a hydration reaction. Let's look at B. At B, we're starting with propene and we end up with a secondary alcohol. And then we are told that that reaction is a hydration reaction. Right, and then now what we're asked to do is to define hydration reaction. It is the addition of water to a compound. That's it. That's the definition. It's the addition of water to a compound. That's what we mean when we talk about a hydration reaction. We add in H2O to a compound. And the follow-up question, 4.2.2, write down the name or formula of the catalyst used for this reaction. So a catalyst you can use for a hydration reaction is H2SO4. So we can use sulfuric acid as a catalyst for a hydration reaction. Let's look at 4.3 and 4.3.1. During reaction C, a specific rule is followed to determine the major product when HBr is added. Let's look at reaction C. So for reaction C, we're starting with propene and we end up with 2-bromopropene. So let's go back to our conditions. Do we start with an alkene? Yes, we do. So we know that reaction C is supposed to be an addition reaction. Well, the answer to 4.3.1 was actually very difficult to find. But if you visit the CAPS document and other relevant resources, you'll find out that for hydrohalogenation, our addition reaction in this case, we need no water because alkenes cannot react with pure water. And then apart from needing no water, we need a concentrated strong acid. So we need a concentrated strong acid for this reaction that we have in 4.3.1. It is an addition reaction, namely hydrohalogenation. We're adding a hydrogen and a halogen. 4.3.2, use structural formula and write down the balance equation for this reaction. So propene plus HBr. Let's go ahead and do that. So we're going to have 1, 2, 3 carbons, right? So 1, 2. Now we just need to add our hydrogens, and we're supposed to have something like that, plus HBr to give us something. If you look back to the equation statement, it says that during reaction C, a specific rule is followed to determine the major product when HBr is added. So now you actually have to know that rule in order to answer this question. Well, to some extent, we know that this double bond is going to break, and either one between H and Br is going to come to the second carbon, and then the other is going to come to the first carbon. So do we get Br on the second carbon, or do we get Br on the first carbon? You need to know where to place that Br, because if you place it at the wrong location, then you lose a mark. But there's a rule for that. There's a law for that. Markovnikov's rule. So basically what it is saying is that the hydrogen is going to go where there's a lot of hydrogens, and then the halogen is going to go to the other spot. So if you look at this carbon here, it has 2 hydrogens, and then the carbon in the middle has 1 hydrogen. So the hydrogen will tend to go to the carbon with a lot of hydrogens already. So that Br it will usually go to the middle because that's where we have the least number of hydrogen. So our product is gonna look like this. Br is gonna come to the carbon in the middle, and the hydrogen is gonna come to the first carbon. And then now it's just a matter of filling out our hydrogens. So this is our major product according to Markovnikov's rule. And then Br being on the first carbon and H being on the second carbon is our minor product. This is our major product. Yeah, usually when this reaction occurs, this is the product. Right. 4.1. Identify the type of reaction taking place at, so let's go to reaction D. Reaction D. Yeah, this one is going to be easy because we know our conditions. Do we start with an alkene? No. Do we end with an alkene? No. So we know that it is substitution. It is substitution. There isn't a lot to think about there. And then 4.2, which reaction are we interested in? We are interested in reaction F. In reaction F, do we start with an alkene? The answer is no. Do we end with an alkene? The answer is still no. So again, that is a substitution reaction. That is a substitution reaction. It cannot be otherwise. And then 4.5.1. Reaction E is a hydrogenation reaction. Let's look at reaction E real quick. We're starting with propene and we're ending up with propane. So it is indeed a hydrogenation, right? And then what does the equation say? Write down the two reaction conditions for this reaction. Two reaction conditions for hydrogenation. So we need heat, and another thing we need is a catalyst. We need a catalyst. Yeah, which catalyst in this case? We need palladium, platinum, nickel, and so on. Right. And then 4.5.2, name one use of hydrogenation in the food industry. Well, I will leave that one to you.
This question is difficult, okay? But let's go ahead and give it a try. The first question, 3.1, we're supposed to define the term boiling point. So boiling point is the TP at which the VP is equal to the ATP, right? So the temperature at which the vapor pressure is equal to the atmospheric pressure. 3.1. Let's take a look at 3.2. In 3.2, write down the conclusion that can be made for curve P. So let's go ahead and read through our question statement and sort of figure out what is happening. So the relationship between boiling point and the molecular mass of aldehydes, carboxylic acids, and primary alcohols is investigated. Curves P, R, and S are obtained. All compounds used as straight chain molecules. Right. And then write down the conclusion that can be made for curve P. As we can clearly see, as the molecular mass increases, the boiling point is increasing. So that is the conclusion we can make for curve P. Well, the same is true for curve R and the same is true for curve S. As the molecular mass increases, the boiling point also increases. Why is that the case? We're going to address that sometime later. That is 3.2. 3.3, explain the answer to question 3.2 in terms of the structures of the compounds. Okay, so now we actually have to support why we are saying that as the molecular mass increases, the boiling point increases. Well, not support, but justify why that is the case. So let's go ahead and try doing that. Okay, so when we're told that we have straight chain organic compounds, right? As the chain is increasing, the London forces are increasing.
Okay, so that is the reason why when the molecular mass is increasing, the boiling point is increasing. It is because when you increase the number of carbons on your straight chain, the London forces are going to be increasing between those carbons. So that is the reason we are supposed to give for 3.3. I wrote it down. It says, as the chain length increases, the London force increases, and the boiling point will increase as a consequence, because the intermolecular forces, the strength of the intermolecular forces is increasing. That is 3.3. 3.4, 3.4.1. Kev R represents alcohols. Well, we can deduce that Kev R represent alcohols without being told. We can deduce that because we have an alcohol, we have a carboxylic acid, and we have aldehydes. We know which compounds consist of which intermolecular forces and which intermolecular forces are stronger than which. We know all that. So yeah, they're telling us, but we already know. They don't have to. Okay, and then 3.4.1, which homologous series is represented by Kev S. So we have aldehydes, carboxylic acids, and alcohols. We know that R is alcohol. Why is R alcohol? Because we have one side of hydrogen bonding, and S is aldehyde, right? Dipole forces. And P is carboxylic acid, where we have two sides of hydrogen bonding. Okay, so this is our acid, this is our carboxylic acid. What is the question saying? Which homologous series is represented by Kev S? Aldehyde. Our homologous series is aldehyde. Aldehyde is the homologous series. Okay. 3.4.2. Explain the answer to question 3.4.1 by referring to the strength of intermolecular forces. So, okay, this is the train of thought. Between carboxylic acids consist of two sides of hydrogen bonding. Alcohol consists of one side of hydrogen bonding. Aldehydes consist of dipole, right? Hydrogen bonding is stronger than dipole. So for the same molecular mass, aldehyde should have the lowest boiling point compared to alcohols and carboxylic acids. So that is 3.4.2. Let's move ahead. Okay, we're moving up and not down. So we have 3.5. Let's take a look at 3.5 and hear the stories. 3.5.1, write down the molecular mass of the compound with a boiling point of 97 degrees Celsius. For Kev R, the molecular mass of the compound with a boiling point of 97 degrees Celsius. So let's go ahead and have a look. So here we have compound R. These are our boiling points on the y-axis. So let's go ahead and identify 97. 97 should be somewhere here, right? That's where we should have 97. And the molecular mass between 50 and 70, so that is 60. So the answer to 3.5.1, we have 60 grams per mole. 3.5.1. So a straight chain alcohol with a molecular mass of 60 grams per mole. Okay, so let's see. We have methanol. What else? We can also just write an equation for this. I think we can write an equation. Let's see. For an alcohol, we know fully well that we are supposed to have CnH2n plus 2O. Okay, this is the general formula of an alcohol. CnH2n plus 2O. We know that the molecular mass of carbon is 12. So we can say 12 multiplied by n plus that of hydrogen.
So hydrogen, we have 2n plus 2, okay? So we're going to have 2n plus 2 plus that of oxygen. Of oxygen, we have 16, okay? This is equals to 16. So let's find the value of n in attempt to finding the alcohol with the molecular mass of 60. So we're going to have 12n plus 2n, that will be 14n. 2 plus 16, that is 18. This is equals to 60. So I have 14n being equals to 60 minus 18. 60 minus 18 should give us 42. So n is equals to 42 divided by 14. I think this is supposed to be 3. Okay, let me just verify if it is indeed 3. 4, 4, 4, 12, 2 plus 1, 42. So, right, n is equals to 3. So we know that our alcohol is C3H3 multiplied by 2, that is 6, plus 2, 8. So 3, C3H8O. This is propanol. This is propanol. So there we go. We have identified the alcohol. I'm sure there's other ways you can use to identify alcohol, but that is just, yeah, the approach I'm deciding to take. 3.5.2. 3.6. Two compounds A and B used in this investigation have a molecular mass of 74 grams per mole. A has a boiling point of 118 degrees Celsius and B a boiling point of 142 degrees Celsius. Explain the difference in these boiling points by referring to the structures of these compounds. Okay, so we're looking for two molecular mass, two compounds. Okay, so let's focus on compound A. Compound A has a molecular mass of 74 grams per mole, and then it has a boiling point of 118 degrees Celsius. So let's identify what A is first. Okay, so let's go to our graph. The molecular mass is 74. How many blocks do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have 10 blocks between 70 and 90. So 1, 2, 3, 4, 5 should give us 80. So we have 80 right here. So that tells me that, let me see. That tells me that 1, 2 should be 74. So if I want to find a molecule with a compound with a molecular mass of 74 grams, then I need to draw a line like that. So, okay, we have 74 grams per mole and a boiling point of 118. So, where can I find it? 118 here. Okay, I think I find it on the alcohol. Okay, let me erase here so that I can see what is underneath. I think I find it on the alcohol. This right here should have a boiling point of around 118. So compound A is an alcohol. I know that for sure. It cannot be compound. It cannot be S because S is way below 100, and it cannot be P. It cannot be on the line P because you can see it is very close to 150. So A is the alcohol. Let's take a look at B. What is the data I have for B? So B also has a molecular mass of 74 grams per mole and a boiling point of 142 degrees. Okay, so 142, we can clearly see that it is this one that we have up here, which is our acid. So B is the acid. So what does the question say? The question says, the question is up here. The question says, explain the difference in these boiling points by referring to the structure of these compounds. Okay, so we have the alcohol and the acid. In alcohols, we have one side of hydrogen bonding, while in an acid, we have two sides of hydrogen bonding. The intermolecular forces on the acid will be stronger than that on the alcohol, requiring more energy to overcome the intermolecular forces. And that's a consequence. We're going to have a higher boiling point on compound B, the acid.
Compound A and B are functional isomers, like we are told in 3.1.1. What we are actually required to do is define the term functional isomer. Like all isomers, we have the same molecular formula, but in this case, the compounds differ by functional group. So the definition for functional isomer, same molecular formula, but different functional groups. Let's look at 3.1.2. Write down the IUPAC name of compound B. So the first thing you want to do is to determine which homologous series this compound B belongs to. Because of the structure of the functional group, compound B, it's a ketone. This carbon that is bonded to the oxygen is bonded to 2 other carbons. And because of that, we can conclude and say that compound B is a ketone. Now what we need is the longest carbon chain. Clearly, it is easy to see that this will be our longest carbon chain with 1, 2, 3, 4, 5, with 5 carbons. So we know we have pentane. We have pentane. Now what we need, or what we're looking for, is the position of the carbon that is bonded to the oxygen. If we start numbering from the left, we're going to have 1, 2, 3. If we start numbering from the right, we're going to have 1, 2, 3. So where we start numbering really doesn't matter. Our functional group is on the 3rd carbon. So we're going to have pentane 3 on. That is the answer to 3.1.2. Let's look at 3.1.3. How does the boiling point of A compare to that of pentane 1-ol? So we have pentane 1-ol and compound A. Write down only greater than, equal to, or lower than. So let's go to compound A. Compound A is an aldehyde because the carbon that is bonded to the oxygen is only bonded to 1 other carbon. So that makes it an aldehyde. So we have pentane 1-ol and pentanol. Pentane 1-ol is an alcohol. So it consists of hydrogen bonding. We have hydrogen bonding in alcohols. And then pentanol is an aldehyde. It consists of dipole-dipole. So the intermolecular forces in pentanol is dipole-dipole. So in order to answer this question, you actually need to know which intermolecular force is generally stronger between hydrogen bonding and dipole-dipole. Compound A will have a lower than boiling point compared to pentane 1-ol. Let me explain why that is the case in 3.1.4. The intermolecular forces in pentane 1-ol, which happens to be hydrogen bonding, are stronger than the intermolecular forces in pentanol, which is dipole-dipole. And then you know that if you have stronger intermolecular forces, then more energy is required to overcome those intermolecular forces in that compound. And then as a consequence, the alcohol or pent1-ol will have a higher boiling point. That is the answer to 3.1.4. Let's look at 3.1.5. How will the vapor pressure of compound B compare to that of pentane 1-ol? That only higher than, lower than, or equal to. Explain the answer fully. So compound B, like we've already deduced, is a ketone. And which intermolecular forces do we find in ketones? We have dipole forces. And then again in pentane 1-ol we have hydrogen bonding. In pentane 1-ol we have hydrogen bonding. So that will lead to ketone having a higher than vapor pressure compared to pentane 1-ol. Higher than vapor pressure. So what you have to understand is that the weaker the intermolecular forces, then the higher the vapor pressure. So between compound B, our ketone, and pentane 1-ol, pentane 1-ol has stronger intermolecular forces. So it will require more energy to overcome the intermolecular forces. And then as a consequence, it is going to have a lower vapor pressure. It is going to have a lower vapor pressure compared to ketone. Ketone will actually have a higher vapor pressure. So what you need to memorize, or what you need to know, is that the stronger the intermolecular forces, the higher the boiling point, the higher the melting point, but the lower the vapor pressure. You need to know that. 3.2.
3.2.1, let's define the term boiling point. That is not the temperature at which liquid turns to gas. Please, we no longer use that definition at this level. It is actually the temperature at which the vapor pressure equals the atmospheric pressure. The temperature at which the vapor pressure equals the atmospheric pressure. That is boiling point. 3.2.2. Run on the independent variable for this investigation. Let's take a look at what is happening in this question. Let us use compound C to E to investigate one factor which influences the boiling points of organic compounds. What I'm realizing real quick is that in compound C we have 1, 2, 3, 4. We have 4 carbons, right? And then in compound D, we have 1, 2, 3, 4, 5. We have 5 carbons in compound D. And then in compound E, we have 1, 2, 3, 4, 5, 6. We have 6 carbons in compound E. So it seems like our independent variable here, what we are changing is actually the chain length. We can see that from the number of carbons we have in the compounds. So the answer to 3.2.2 would be chain length, or the molecular mass, because as the chain length increases, then the molecular mass is also going to increase. So that is the independent variable. And 3.2.3, write down the type of van der Waals force that occurs between these organic compounds. So these organic compounds are all alkenes, right? Well, you can draw compound C fairly quick by saying C, 1, 2, 3 hydrogens, and then another carbon with 2 hydrogens, another carbon with 2 hydrogens, and the last carbon with 3 hydrogens. The same thing with compound D and E, they're all alkenes. So the force that is occurring in compound C, D, and E is actually London force. That is London force, or induced dipole forces. Well, let's look at 3.2.4. Write down the conclusion that can be drawn about the boiling point of straight chain alkenes. So let's look at our diagram. We can see fully well that as the number of carbon is increasing, our boiling point is increasing from -1 to 36.1 and lastly to 69. So we can conclude and say that as the chain length increases, the boiling point increases. If you had said molecular mass in 3.2.2, you would say that as the molecular mass increases, the boiling point increases.
The temperature at which the vapor pressure is equals to the atmospheric pressure is what we refer to as the boiling point, and that is 3.1. So from here on, let's go ahead and take a look at 3.1.2. What does the question say? Which of the compounds A, B, or C is mainly in the liquid phase at 100 degrees Celsius? My grade 10 learners can answer this question, but let's take a look and see what is happening. So we have organic compounds A, B, C, and D, but we are only concentrating on A, B, and C as our question instructs. So the question is, which compound of these three is mainly in the liquid phase at 100 degrees Celsius? Right, so it must not be a gas at 100 degrees Celsius. It must not have boiled at 100 degrees Celsius. So let's take a look. Compound A. The boiling point of compound A is 78 degrees Celsius. So at 100 degrees Celsius, we are above the boiling point of compound A. So it is already a gas at 100 degrees Celsius because it boils at 78. Same is true with compound B. Compound B has a boiling point of 46 degrees Celsius. So at 100 degrees Celsius, it is above its boiling point. So it has turned from liquid to gas already. So C is the compound that is in the liquid phase at 100 degrees Celsius. If we take a look at A, B, and C. So the answer here to 3.2, 3.2 and not 3.1.2. 3.2 is C. C is at the liquid phase at 100 degrees Celsius because it has not yet reached its boiling point. Okay, explain the difference in the boiling points of compound A and B. That is for 3 marks. So let's take a look at compound A and compound B and see how they differ. Well, they are all haloalkanes, but they differ in branching. The structure of compound A, let's take a look. 1, 2, 3, 1, 2, 1, 2, third carbon, fourth, 1, 2, and chloro. And then this is A. Let's take a look at B. Right. At B, we have 1, 2, carbon, hydrogen, 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 and then hydrogen. Well, let's just leave the dash there. And then we have another carbon that serves as a branch. And then carbon, hydrogen, hydrogen, chloro. So this is compound B. As you can see, in compound B, we have this branch here. And then in compound A, we don't have a branch. So the difference in the boiling points of compound A and B is because compound A is less branched compared to compound B. So compound A is going to have more surface area, stronger intermolecular forces, and thus more energy is required to overcome the intermolecular forces in compound A. That is why we see a higher boiling point compared to compound B, because it is less branched. Okay, so that is 3.3. What about 3.4 and 3.4.1? Let's go ahead and take a look. Consider the boiling points 75 degrees Celsius, 120 degrees Celsius, and 126 degrees Celsius. Which of these values represents X, the boiling point of compound D? So let's go ahead and take a look at compound D and see if we can make sense of this. Compound D seems to be an aldehyde. Let's take a look. Carbon, 3 hydrogens, carbon, 2 hydrogens, carbon, 2 hydrogens, carbon, oxygen, 1 hydrogen. So compound D is indeed a aldehyde, but compound C is an alcohol, right? So the boiling point of compound D must be lower than that of C, because aldehydes we have dipole, and then in alcohol we have hydrogen bonding, and hydrogen bonding is way stronger than dipole. So X should be less than 118 degrees Celsius at least. So take a look at this. We have 120. So this can't be correct, because D must have a lower boiling point compared to C, because D is dipole and C is hydrogen bonding. And then this is also not true, because it cannot be higher than that of alcohol. So the only thing that makes sense is 75 degrees Celsius. So 3.4.2, we have 75 degrees Celsius. So X makes sense to be 75 degrees Celsius. Well, 3.4.2 says explain, and we've explained that. Now let's take a look at 3.5. 3.5 is quite an interesting one. I had to take some time and think about that. The atmospheric pressure is now changed to 83 kilopascals. Well, under normal circumstances, we have 101 kilopascals. I think 101.3, something like that. But I know for sure it is around 101. And now it is changed to 83 kilopascals. Now it is changed to 83 kilopascals. Let's hear the stories. How will the boiling points of these organic compounds be affected? Choose from increase, decrease, or remain the same. So do the boiling points increase, decrease, or remain the same if we lower the vapor pressure? Well, let's stick to the definition. What is boiling point? Boiling point is the temperature at which the vapor pressure is equal to the atmospheric pressure. So you are essentially increasing the vapor pressure so that it reaches the atmospheric pressure, and we say that we have reached the boiling point. Essentially, if you are lowering the atmospheric pressure, you will reach a boiling point way sooner than you would under normal circumstances. Right, maybe for water, the boiling point is 100 degrees Celsius. So if you lower the atmospheric pressure, you would reach the boiling point, let's say at 80 degrees Celsius, way before what it usually is at 101 kilopascals. So this would actually make the boiling point to decrease. Right, this is the first time I'm actually coming across a question like this, but I'm quite convinced that decrease is our answer in 3.5. If you have any other ideas, just let me know in the comments and let's talk about it. Apart from that, which video do you want me to do next?
Pressure exerted by vapor at equilibrium with its liquid in a closed system. That is vapor pressure. 3.2. Which one of the compounds A or B has the higher vapor pressure? So what do we know? We know that the higher the boiling point, the higher the melting point, the higher the viscosity, but the lower the vapor pressure. So which one of the compounds A or B has the higher vapor pressure?
Well, the compound with the lowest boiling point will have the highest vapor pressure. So between A and B, which one has the lowest boiling point? It is compound A with minus 42 degrees Celsius. Compound B has a boiling point of 36 degrees Celsius. So the answer here is A. A has the lowest boiling point, so it should have the highest vapor pressure. Right, 3.3.1. Let's consider compound C, 2-methylbutane. Is compound C a saturated or unsaturated hydrocarbon? Well, it is easy to see that it is saturated. Why are we saying that it is saturated? A compound is saturated if it only consists of single bonds between the carbon atoms, no multiple bonds whatsoever. That is a saturated compound. Just like our compound C, it is a simple alkane saturated compound. Alkene and alkynes are unsaturated because we have double and triple bonds. Here we only have single bonds. 3.3 because we've just answered 3.3.2 there. Which type of intermolecular forces are mainly present between these compounds? Well, the compounds on our table, we have propane, pentane, 2-methylbutane, and then we have an outlier, pentane 1-ol. As you can see, one intermolecular force that is present from compound A to compound D is London forces. It is present even in compound D, pentan 1-ol. So that is the type of intermolecular force which is mainly present between these molecules. There is London forces in pentan 1-ol. It is just that the strongest intermolecular forces in pentan 1-ol will be hydrogen bonding, but London forces is present. 3.3.3. Let's go ahead and look at 3.4.1 and 3.4.2. Define the term structural isomer. Organic compounds with the same molecular formula but different structural formula. Same molecular formula but different structural formula. Just like compound B and C, we have C5H12. 3.4.2 refer to the structure, intermolecular forces, and energy in your explanation to explain why compound B has a higher boiling point than compound. Let's go ahead and have a sketch of compound B. 5 carbons in a straight line. So 1, 2, 3, 4, 5. While compound C on the other hand, we have 1, 2, 3, 4. And a branch on the second carbon. How does compound B differ from compound C? The only difference between these two compounds is the degree of branching. Compound B is less branched compared to compound C. Less branched means more surface area. So we have more surface area in compound B. From there on, our song starts. More surface area, stronger intermolecular forces. If the intermolecular forces are stronger, more energy will be required to overcome the intermolecular forces, and consequently a higher boiling point, just like we can see. Right, so B is less branched compared to compound C, as we can clearly see. This is straight, and here we have a branched. Less branched will mean more surface area. More surface area, stronger intermolecular forces, more energy is required to overcome those intermolecular forces. I hope that is clear. The last question, 3.5. Explain the difference in the boiling points of B and D. Refer to the intermolecular forces and energy in your explanation. Let's go ahead and look at B and D. B is pentane and D is pentane 1-ol. Look at the difference in the boiling point, even though they have the same number of carbons, 36 degrees Celsius and 137 degrees Celsius.
So why does compound D has a higher boiling point compared to compound B? Well, compound B consists of London forces, while compound D consists of hydrogen bonding. We know fully well that hydrogen bonding is a stronger intermolecular force compared to London forces. So compound D will have stronger intermolecular forces. More energy will be required to overcome the intermolecular forces in compound D, and as a consequence, it has a higher boiling point. If a reaction starts with an alkene, then it is an addition reaction. And then if it ends with an alkene, it is an elimination reaction. And if the first condition or the second conditions are not met, then it is a substitution reaction. So this is how you can easily identify the type of a reaction by just looking at the compound it starts with or the product that you have. If it starts with an alkene, it is an addition reaction. If it ends with an alkene, it is an elimination reaction. And if either of those are not true, it is a substitution reaction. So let's see how we can use this to answer this question. So 4.1.1, identify the type of reaction represented by B. So take a look at reaction B. Does it start with an alkene? No, it does not. It starts with an alcohol. So it cannot be an addition reaction. Does it end with an alkene? Yes, it does. As soon as we see that, we know that it is an elimination reaction because it ends with an alkene. Right, those are the only two things we need to look at. If it didn't end with an alkene, then it would be a substitution reaction. That is 4.1.1. Let's take a look at 4.1.2. Identify the type of reaction represented by D. So again, does it start with an alkene? No, it does not. Bromoethane is not an alkene. And does it end with an alkene? It is not. It ends with an alcohol. So because the first condition is not met and the second condition is also not met, then we are saying that it would be a substitution reaction. Those are the only two things that we need to look at. Does it start with an alkene? Does it end with an alkene? If that's not the case, then it is a substitution reaction. So there we go. That is 4.1. Let's take a look at 4.2. 4.2, we're supposed to write down two reaction conditions for reaction B. So reaction B, it's easy to see that we have a elimination reaction. So heat is a reaction condition for all elimination reactions. Heat is a reaction condition for all elimination reactions. Right, so heat is our first answer, right? As soon as we see a reaction condition and it is elimination, heat, we're going to think after that. So now let's find another reaction condition. So what is happening here? We have dehydration, right? We have an alcohol turning to an alkene. So we need a dehydrating agent, of which we can use a catalyst such as H2SO4. So we also need a catalyst as a reaction condition for this elimination reaction that we have. 4.2, let's take a look at 4.3 and 4.3.1. For reaction A, write down the name of the inorganic reactant. So reaction A, we are turning an alkene into an alcohol. Obviously, we need H2O to turn an alkene into an alcohol. And by our definition, H2O is inorganic because it does not contain carbon. So name of the inorganic reactant, it is water, right? Not H2O. The question is very specific. We are looking for the name of the inorganic reactant. And then 4.3.2, chemical formula of the catalyst used. Chemical formula, not the name, right? So don't confuse the two. Well, you know what they mean. Just be careful and not write a formula when they want a name, or write a name when they're looking for a formula. So here the chemical formula of a catalyst needed. We need H2SO4. Right. H2SO4 is not always the answer to equation with regards to catalyst. Right. It just happens that We have used it twice in this equation. Okay, 4.4, 4.4.1. Let's take a look. For reaction C, okay, so reaction C, we are turning an alkene to a haloalkane, right? And then 4.4.1, use structural formula and write down a balanced equation. Okay, we're supposed to use structural formula. So this is our alkene with 2 carbons. How many bonds do we have? 1, 2, 3. So we need another hydrogen. And we can see that our product is bromoethane. So what are we adding here? We're adding HBr. And this should give us bromoethane. So the double bond gets broken, and it's just a matter of filling out the hydrogen and the bromo in one of those bonds. So there we go. I don't think there's any wrongdoing that we do in there. I think all is well, right? Quite an easy reaction. We have our alkene, we add a hydrogen and a halogen, so it is a hydrohalogenation addition reaction, and then this is our product. Okay, there we go. 4.4.1. Let's take a look at 4.4.2. So 4.4.2, explain why no water should be present during this reaction. Explain why no water should be present during this reaction. We are avoiding the formation of OH instead, right? If you have water, it's very possible that instead of having Br there, you might have OH. So that is what we are running from. Yes, we are trying to avoid the formation of the hydroxyl group, right? That is 4.4.2. 4.5, let's go ahead and take a look. So we are now concentrating on reaction A. Okay, let's see what the first question says. Type of reaction. Okay, so reaction A represents the conversion of the alcohol into organic compound X. So reaction E. Okay, so we start with an alcohol, as we can clearly see, and then we add what looks like an acid to get compound X. So something should come to mind when you talk about alcohol plus acid. This is clearly a esterification. So the answer to 4.5.1 is esterification. An alcohol plus an acid in the presence of a suitable catalyst will give you esterification, right? It will give you an ester. So type of reaction, esterification, right? So esterification. There we go. That is 4.5.1. Let's take a look at 4.5.2. Chemical formula of the catalyst used. We know what suitable catalyst we need in esterification. We need concentrated H2SO4. That's what we use in our esterification reactions. And then 4.5.3, structural formula of compound X. Compound X, I would assume, is the product formed. Let's go ahead and take a look. Okay, there we go. So our alcohol has 2 carbons. 1, 2. Okay, that's easy to see. And then our acid, let's go ahead and find out. We have 1, 2, 5, right? That's C multiplied by 3 there. So we have 1, 2 from the alcohol, and then we still have our oxygen from the alcohol. And then as long as it comes, and the carboxylic acid, we still have our double bond oxygen. And then 1, 2, 3, 4. So in total, 1, 2, 3, 4, 5. We have our 5 carbons from the carboxylic acid. So now, what we just need to do is to fill out the hydrogens everywhere else. I hope we're looking for the structure of the product and not the entire reaction, right? So there we go. Yes, maybe we should just do the reaction, the entire reaction, so that you can see where it is coming from, right? Maybe We should do the entire thing so that you can see where it's coming from. But this is the answer. This is our product. This is compound X. Right. Let me show you where it is coming from either way. Let me show you where it is coming from. So we're saying that our alcohol has 2 carbons. Yes. So it means that we have 1, 2, OH, hydrogen, hydrogen, everywhere else. Okay, this is what we have. Plus the carboxylic acid. Our carboxylic acid has 5 carbons. So it is 1, 2, 3, 4, 5. Well, let me put these a little bit to the right so that it will be easy to see when we remove our H2O, so that it can be easy to see when we remove our H2O. So hydrogen everywhere else. Hydrogen everywhere else. Okay. There we go. So what happens is that the alcohol loses the hydrogen and the acid loses the OH. Okay. And then that is why a byproduct or an inorganic product of esterification is H2O. Right. So we essentially losing this. We'll lose this part because water is removed from, well, we get water when we add the two compounds. So that is why our product ends up looking like this. This is why our product ends up looking like that. Okay, so there we go. I hope you can see where it is coming from. Right, the alcohol loses a hydrogen and the carboxylic acid loses an OH. But anyway, stories. Let's take a look at the question that follows. Is it 4.5.4? I think so. We're looking for the IUPAC name of the compound. So how do we name an ester? Right, well, we started with the alcohol and then we finished off with the acid. So the alcohol here is ethanol, as it has 2 carbons. So we're going to have ethyl, and then the carboxylic acid is pentanoic acid, as we have 5 carbons. So we're going to have pentanoid. So the name of this ester is ethyl pentanoid. Right. If the alcohol had 3 carbons, it would be propyl pentanoid. If the carboxylic acid had 4 carbons, for instance, it would be ethyl butanoid. That is how it works. First part of the name comes from the alcohol, how many carbons we have, and the second part of the name comes from the acid, how many carbons we have. That is 4.5, 4.6. Let's go ahead and take a look. So 4.6, reaction F takes place in the presence of warm concentrated sodium hydroxide. Use condensed structural formula and write down a balance equation for this reaction. Let's go ahead and take a look at reaction F. So reaction F, bromoethane to give us an alkene. Okay, so let's take a look there. In the presence of concentrated NaOH. So in the presence of concentrated NaOH, that's where elimination is going to take place. If it was in the presence of dilute NaOH, then substitution would take place. So let's go ahead and take a look at that. We start off with our bromoethane. Okay, so Br, hydrogens everywhere else. Okay, this is what we're starting with. And then plus NaOH. Okay, so what happens here is that, well, we are supposed to use condensed structural formula, not the way I'm doing it here. But let me just carry on with this for the sake of clarity. After doing this, then we're going to write it in the correct form. We're going to use condensed structural formula. Okay, so let's just carry on with this for the time being. So what happens here is that Na will bond with Br, and then OH will bond with the hydrogen removed, right? And then it means that our product, well, our byproducts, we're gonna have NABR plus H2O. Okay, that's how it goes. So let me show you. It means here that the products, we're gonna have one double bond because now it is an alkene, hydrogens elsewhere, plus NABR plus H2O. This is how the reaction takes place in terms of the structural formula. But our equation, we're supposed to use condensed structural formula. So let's go ahead and do that. This is just for the sake of clarity. So condensed structural formula, CH3 CH2Br, okay, plus NaOH. And what does this give us? This gives us CH2 CH2. As you can clearly see, CH2 CH2, and then plus NaBr plus not NaOH but H2O, right? We have H2O there. So there we go. That is the condensed structural formula for reaction F. Okay, so 4.7, cracking. Let's take a look. We know fully well that this is still part of our syllabus, but it's one of those questions that they're not usually there in the exam. But let's go ahead and take a look at it. A large straight chain alkenes can be catalytically cracked to produce shorter chain alkenes and branched alkanes, which are more suitable for use in petrol. The reaction below indicates the catalytic cracking of octane. Okay, so octane, obviously we are expecting 8 carbons, and then here on the alkene we have 2 carbons. It means that on compound Y, which should be an alkane, we should have 6 carbons. So C6H14. That's what we expect compound Y to be, right? So what does the question say? Write down the IUPAC name of compound Y. So 6,6, that is hex. So this is hexane. 4.7.1 is hexane. So there we go, hexane. And then 4.7.2, briefly explain why shorter chain alkenes and branched alkanes are more suitable for use in petrol than larger straight chain alkenes. So what do you think it is the answer to this question? Explain why shorter chain alkenes and branched alkanes are more suitable for use in petrol than larger straight chain alkenes. Right, maybe just to give you a hint, think about intermolecular forces, energy required, so on and so on. Let me know in the comments what your answer to this question is.
The name or formula of the catalyst used. So let's go ahead and take a look and see what is happening. In an experiment, a test tube containing methanol, propanoic acid, and a catalyst is heated in a warm bath. Well, we have the setup in front of us. The warm bath. Under the warm bath, we have some heat, methanol, propanoic acid, and a catalyst. Already, you should be able to tell that we have a esterification taking place. Okay, so which catalyst is required when we are trying to have esterification? The catalyst is H2SO4. That is the catalyst. The question says name or formula. So if you say sulfuric acid, that would also be fine. But in some instances, the question would say the name, and then if you write H2SO4, it would be wrong, or it says the formula, of which if you write the name, it would be wrong. Right, so there we go. That is 4.1.1. What about 4.1.2? The type of reaction taking place. Even in, say, after doing all the questions, what does this comment say? Do you mind doing multiple choice for paper 2? We'll see about that, but I doubt I will. Multiple choice takes too much time and it doesn't get as much views, so it doesn't make sense for me to do it. The type of reaction taking place is esterification. So esterification, there we go, that is 4.1.2. And then 4.1.3, 2 reasons why the use of a water bath is preferred in this experiment over direct heat. One of the reasons is because alcohol is extremely flammable, right? So there we go. That is one reason. Alcohol is flammable. So if you put it on heat, if you put it directly on heat, then it's gonna burn, and that's not what we want. So that is one reason why we use a water bath over putting the reactions on heat themselves. So what is the other reason? I would like you guys to tell me. So please leave a comment and tell me which other reason you can think of. Well, in class, during the course of the year, at the beginning of the year, we actually performed this experiment, and we lost patience at some point of time because it was taking too long, and we put the test tube directly on heat, on the fire that was burning. Yeah, because we're using a sort of a Bunsen burner. I forgot the technical name of the apparatus we were using, and then we experienced some issues. Well, almost all the contents evaporated from the test tube, so we were not actually able to smell the contents, or because after an esterification you take a smell and then there's some things that you write, so on and so on. So we're not able to do that because we lost patience and put the test tube over the fire. But let me know, which other reason can you think of? That is 4.1.3. let's do 4.1.4. the balance equation for this reaction using structural formula. So we have methanol plus propanolic acid. So let's go ahead and take a look. Methanol, so alcohol with 1 carbon, okay, that is methanol, plus propanolic acid, acid with 3 carbons. So we're gonna have, let's take a look, carbon, well, we're supposed to have OH here, and let's see, we need more space. Let me start with the H instead. H, O, carbon double bond oxygen, right? And then let's 3 carbons and not 2 because it's prop. So hydrogen, and we need another hydrogen here. 1, 2, 3, 4. Okay, so this hydrogen, that carbon is fine, and then this will give us an ester. So what's gonna happen? The alcohol loses the hydrogen and the acid loses the OH. As a result, we're gonna have carbon, oxygen, and then now carbon. Okay, and then 1, 2, 3. Okay, there we go. And then now we just need to fill out the hydrogens, right? So let's do that. So there we go. We're supposed to have something like this, and then obviously here we can write H2SO4 as our catalyst. But what happened to the H2O that we removed is that it doesn't disappear. So we're gonna have plus oxygen HH, not plus H2O, because H2O is not a structural formula, right? You're supposed to write it in this manner. If you write it as H2O, that is technically wrong because H2O is not a structural formula. So this is what we have. Let me just check and see if I'm not making any mistake. Okay, let me take a look. I'm supposed to have an oxygen here and not hydrogen. 1, 2, 3, 4, 5. Okay, another mistake. Hydrogen. I've removed that hydrogen. It's all going well now. I think I have everything covered now. So that is 4.1.4. I hope you didn't make those mistakes that I was making there. The IUPAC name of the organic product for this reaction. The organic product is the ester and not the H2O. So what is the name of this ester? We're gonna have methyl propanoate, right? This part of the name comes from the alcohol, and this part of the name comes from the acid, methyl propanoate. Right, I think we have that covered. Let's take a look at 4.2. Compound A is a 6-carbon branched haloalkane, and it is used in a 2-step reaction to prepare compound C. Okay, so compound A, and then we go to B, and lastly we go to C. Reaction 2 is an addition reaction. If reaction 2 is an addition reaction, then here we have an alkene, because you can only add it to an alkene. Okay, we know that for sure. And then 4.2.1, the name or formula of the inorganic reactant needed in reaction 2. So we have an alkene, and our product is an alkane. So we have an alkene, and our product is an alkene. So I think, it is quite easy to deduce here that we have a hydrogenation. We have a hydrogenation. So what is the inorganic reaction needed for hydrogenation? Platinum, palladium, nickel. I wonder what else, but those are the ones that I can recall from my head on the spot. Okay, 4.2.2, the IUPAC name of compound B. So compound B is an alkene. Let's try sketching the alkene. We can try sketching the alkene using compound C. We're sort of removing 2 hydrogens there. So the question says the IUPAC name, but it's better to sketch before we actually name the compound, right? It becomes easier. So let's see. One, okay, and then carbon, and then carbon, and then here we're gonna have carbon, and then another carbon, but we are removing 2 hydrogens in reaction 1, right? Not 2 hydrogens, but let's say, yeah, we are removing the compound that is here, and another compound, not compound but element, another element that is there, right? So we have a double bond here as a consequence. In compound B we have a double bond, because how are we adding these 2 hydrogens in reaction 2 if compound B doesn't have a double bond? It will not make sense. So we have a double bond there. So now we can name compound B using that knowledge. So if we're to name compound B, obviously we would have butane 1 in, okay, and then so this is 1, 2, 3, 4. So on the 3rd carbon we have 2 point, not 2, because like I said on the 3rd, so why do I say on the 3rd and say 2? Right, let me just, I'm trying to drag this to the right. So I'm gonna have 2.2 dash dimethyl butane 1 in. So let me hide the structure and try drawing it and see if I'm gonna end up with the same thing. So butane, so 1, 2, 3, 4, 1 in, double bond, 2.2 dimethyl, so 2 is here, so carbon, carbon. Is that what we have? Is that what we're dealing with? That is not quite what we are dealing with, because if I reveal that structure, let me do that. I have, okay, the carbons are on the 3rd, so this is 3.3 and not 2.2. Right, if I didn't do that, if I didn't try to verify, I was actually going to get it wrong. So yeah, I'm glad I did try to verify, because I had made a mistake. But anyway, stories, that's what we have. That is 4.2.2. And then what about 4.2.3? The type of reaction represented by reaction 1. In reaction 1 we have a haloalkane. Oh well, in compound A, in reaction 1 we start with a haloalkane and we end up with an alkene. Clearly it is an elimination reaction. Yeah, because we start with a saturated compound and we end up with an unsaturated compound. So that is 4.2.3.
Using structural formulas, write down a balance equation for reaction 1. Let's go ahead and take a look at reaction 1. We are starting with but 1 in. We are adding a hydrogen and a halogen to get some product X. Well, in our previous videos, I've made it very clear. If a reaction starts with an alkene, it is an addition reaction. Without looking at any other thing, if it starts with an alkene, it is an addition reaction. No questions asked.
What are we adding in this reaction? We're adding a hydrogen and a halogen. Well, let's start and see what we're going to have. We're starting with but1-ene. So that is 1, 2, 3, 4. And on the first carbon, we have a double bond. So now it's just a matter of filling out the hydrogens. Let's go ahead and do that and see where we end up. Right, there we go. We have but1-ene. Let's make sure that we have the correct number of hydrogens. On this carbon, we have 1, 2, 3, 4 bonds. So that is okay. On the second carbon, we have 1, 2, 3, 4. So it seems like everything checks out. So what are we adding? We add in a hydrogen and a halogen. The name of this addition reaction would be hydrohalogenation. The name of an addition reaction comes from what you are adding. Well, let's go ahead and have our products. It is easy to see that this double bond is going to break to accommodate the hydrogen and the halogen. But where is the hydrogen going to go? Where is the halogen going to go? The hydrogen is going to go to the carbon with the most number of hydrogens already. If you look at our situation, this first carbon here has 2 hydrogens and the second one has 1 hydrogen. So the hydrogen is going to go to the carbon with the most number of hydrogens. That is Markovnikov's law. So let's go ahead and have our product now. We're saying that our hydrogen is going to go to the first carbon as it has the highest number of carbons compared to the other carbon that it can possibly occupy. Yeah, so from this reaction, this is our major product. Our minor product is when the halogen is on the first carbon. That is 4.1, 4 marks. Let's go ahead and do 4.2. Write down the name of the type of reaction that occurs when but1-ene is converted to compound X. We already know that if a reaction starts with an alkene, we have an addition reaction. Quite an easy question to answer. 4.3. Write the structural formula and IUPAC name of the secondary alcohol Y that forms. So we've but1-ene, and through some reaction 3, our product is a secondary alcohol. Well, it is starting with an alkene, so we know that it is an addition reaction. Which addition reaction leads to an alcohol hydration, right? So given that it is a secondary alcohol, but we would also be able to get to a conclusion that the alcohol that is formed is secondary. But anyway, let's go ahead and have our alcohol. 1, 2, 3, 4. On the second carbon, we have OH. Yeah, that is wrong. It's not supposed to be like that. We're supposed to have a dash here to show that OH is not one thing. It is an oxygen bonded to a hydrogen. If you are writing the structural formula, you need to put that bond there. Well, everywhere else we have hydrogens. So we can just go ahead and put that there. Again, our product is a secondary alcohol because of the Markovnikov's law. Let's go ahead and name this alcohol. How many carbons? 1, 2, 3, 4. Which side are we numbering from? From the right, because our OH is going to be on the second carbon. But if we start numbering from the left, it is going to be on the third carbon. Well, it means that our IUPAC name will be butane right? The functional group is on the second carbon. That is 4.3. Let's do 4.4. Name the type of substitution reaction that occurs when compound X is converted to the secondary alcohol Y. So there is only one substitution reaction that can give you an alcohol. It is hydrolysis. There is no other substitution reaction that leads to the formation of an alcohol. So without thinking very hard, we know that the answer is hydrolysis there. If your alcohol is formed through a substitution reaction, it is hydrolysis. If it is formed through an addition reaction, it is hydration. Yes, 4.5, 4.5.1. We butane in can be converted directly to the secondary alcohol without the formation of the intermediate product X with the help of a catalyst. 4.5.1, except butane in, write the name of the reactant needed for this reaction. Well, a reaction that takes us from butane in to the secondary alcohol, it is an addition reaction. But they don't want to say now in 4.5.1 because it is equation in 4.2. So if they tell you what it is, then you can actually say, oh, okay, it means that the answer to 4.2 is addition. What do you need to add to butane in order to have an alcohol as your product? You need to add H2O, but they say the name. So if you write H2O, it is wrong because H2O is not a name. The name is water, right? That is another trick to the question, because if you write H2O, I'm telling you, your answer is wrong. You need to write water. And 4.52, write down 4.5.2, write down the formula of the catalyst that can be used. If you write sulfuric acid, your answer is wrong. The question says formula, so you're supposed to write H2SO4 and 4.5.3. Name the type of reaction that will occur during this direct conversion. It's 2 marks for one question because the same question is getting asked in 4.2. The type of reaction that will occur is addition.
Which letter represents an alkene, right? So what we want to do here is to have a functional group of an alkene, right? So we know that in an alkene, we have a double bond, right? And then the name ends as E-N-E. So when we go to our table here, whatever that has a double bond or the name ends with E-N-E, we know fully well that that's an alkene, right? Clearly on A here, we have a double bond. So as soon as we see that there's a double bond, we know that it's an alkene, right? So right now we can just write A. And then B, we don't have any double bond between carbon atoms. And then on C, we have a double bond here. So C is part of our solution. So for 2.1.1, we have A and C. And then for D, there's no double bond, and then it doesn't end with E and E. And then for E, no double bond. And then for F, there's a triple bond, right? And that's not what we're looking for. So the answer for 2.1.1, we just have A and C. Now let's go to 2.1.2, which letter represents a ketone. Again, we're going to look at the functional group of a ketone. For a ketone, we need something like this, right? We need a carbon that is bonded to an oxygen and then bonded to 2 other carbons, right? So if we see something like that, or a name that ends with O-N-E, then we know that we have a ketone, right? So for A, we already know that A is an alkene, so there's no way it can be part of our solution. But then if you look at B, we have a carbon here bonded to an oxygen and 2 other carbons. So clearly B is our ketone, right? So for 2.1.2, we have B. C is also an alkene, so it cannot be part of our solution. D doesn't have what we're requiring. E and F also doesn't have what we're requiring. So now we can go to 2.1.3. 2.1.3 says, let's look for a compound with a general formula CnH2n minus 2. Right? If you're not already familiar with this, this is an alkyne, right? The name ends with Y-N-E. Another way of identifying it, we have triple bonds, right? So a carbon is bonded to another carbon and there's triple bonds in between the two. So again, we go to our table and we look for that. A cannot be part of our solution. B cannot be a part of the solution. C also cannot be part of our solution, right? And then D, we don't have a triple bond or Y-N-E, right? So that cannot be part of our solution. For E, no triple bond. And then F, that's where we have our triple bond, right? You can see it here. So for 2.1.3, we can put F as our answer. right? The way of approaching this problem, you have to know exactly what you're looking for, right? It becomes extremely easy when you do that. And then 2.1.4 says, let's look for a structural isomer of octanoic acid, right? Octanoic acid. So for an acid, if we're looking for a structural isomer, we're looking for another acid, or we're looking for an ester, right? Because acids and esters are functional isomers. So if the structural isomer is an acid, then we should find something of this manner, right? Or something that ends with the name acid, right? And then if it's an ester, then we're looking for something like this, right? Or a name that ends with ATE, right? A cannot be part of our solution, B cannot be part of our solution, C cannot be part of our solution. But obviously, if you look at D, this name here ends with ATE, right? And then not only does it end with ATE, it also has 8 carbons, right? Like the octanoic acid, which is of our interest, right? So the answer of 2.1.4, we are going with D. And then now we can do 2.2. 2.2 starts by saying that let's write down the UPEC name of compound A. So what you want to do first, step number 1, is that to identify the longest carbon chain, right? So we have 1, 2, 3, 4, 5, 6. Even if you take any other way, you'll end up with 6, right? So now we know that as part of our name, we should have hex. Now we are going to look for the side which leads us to the functional group first. Obviously, if we start counting from this side, if we say 1 here, 2 here, and then we have our functional group, right? So it will say hex 2 in, right? But then if you start on the other side, you'll say 1, 2, 3, 4, and then it will be on carbon number 4, right? So we prioritize the side that leads us to the functional group first. So we have hex 2 in, right? Now we can look for the branches. So let's name our carbons first. So that is carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, and carbon number 6, right? On carbon number 4, we have a branch. We have 1 carbon, right? And then on carbon number 5, we also have a branch. So now we can say 4, 5 dash. We don't say methyl, right? Because we have 2. Instead of saying methyl, we say dimethyl. 4, 5 dash methyl, right? And between words, there's no need to put a dash. Now we can go and do 2.2.2. We need the UPEC name of compound E. So let's go look at compound E. Let's look for the longest carbon chain. So if we say this is 1, 2, 3, 4, 5, 6, 7, and then if we take this way and we keep going forward, we get 6, right? So we can conclude that the longest carbon chain has 7 carbons. So what is 7? We know fully well that 7 is hept, right? So we have hept. And then let's look for the functional group. It's an alkane, right? Every carbon is essentially the functional group. So we don't put anything there for an alkane. We can just say heptane. You only put something when you have an alkene or you have an alkyne. And then all the other complicated organic compounds with other functional groups. Now you will realize that we have an ambiguity here. We have a halogen on the second carbon, right? When you start counting from the left, and then we have a branch on the third carbon when you start counting from the right, right? So which one do we prioritize between the carbon and the halogen? Between the carbon and the halogen, we prioritize neither. So whatever that comes first is what we take, right? If a certain path gives us methyl first, then we're going to take methyl. But then if we start counting from the left, then we get to bromo first. So we're going to take bromo, right? But then you can get a situation where on the left path, you get to bromo, and then on the right path, you get methyl. What do you do when you have a situation like that? Then you have to check the alphabet, right? You have bromo and methyl. So you would take bromo because alphabetically wise, bromo comes first. But then now, because bromo is on the second carbon from the left, and then the methyl is on the third carbon from the right, you just take bromo automatically. And then if the methyl was on the second carbon and the bromo was on the third carbon, then you would take the path that leads to the methyl first. So we have carbon 1, 2, 3. So on carbon 2 and 3, we have 2 halogens, right? So we're gonna have 2,3 dash dibromo, right? Because we have 2. And then we can then look for the branch, right? Carbon number 4, carbon number 5, and then on carbon number 5 we have methyl, right? So we're gonna have dash 5 dash methyl, and then there goes our UPEC name. And then last but not least, we have 2.23, which says let's write the UPEC name of compound F. In compound F, we have an alkyne, right? Because we have an alkyne, we have a functional group. So naming will be much easier because we always prioritize the functional group. So we're going to start naming from this carbon here. So we're going to have 1, 2, right? And then 3, 4, 5. Even if you go up, you still have 5 carbons, right? So now it's easy to see that we'll have pent, right? And then now let's look for the position of the functional group on the second carbon. So we're going to have pent 2YNE. Now we can look at the branches and so on. We have a branch on the 4th carbon. So we're going to have 4 dash methyl. Now let's do 2.3. So 2.3 says that compound D is prepared by reacting 2 organic compounds in the presence of an acid as a catalyst. And then 2.3.1, let's write down the structural formula of compound D. So let's go and look at compound D. So compound D is pentyl propanoate, right? We know that if it ends with propanoate, it's an ester, right? One thing about an ester, the first part of the name is the alcohol and the last part of the name is the acid. So let's write the structural formula. We know fully well that pent is 5, right? So we're going to have 1, 2, 3, 4, 5. We're saying that the first part is the alcohol, right? So here we were supposed to have OH, but then when it forms an ester, it loses this hydrogen here, and everywhere else where I'm putting a dash, you fill that with hydrogens, right? And then the last part, propanoid, that is the acid. So propanoic acid was supposed to look like this, right? But what happens is that when it forms an ester, it loses this OH here, right? The alcohol loses an H, and then the acid loses an OH, and then the byproduct is then H2O, right? So let's put it in our structural formula. So here we're gonna have dash a carbon, an oxygen, carbon, and then there we go. So like I said, everywhere when there's a dash, we just put hydrogens, right? For the sake of time. Now let's do 2.3.2. 2.3.2 says the UPEC name of the organic acid used to prepare compound D. Yeah, we went through it, right? I say that the last part comes from the acid and the first part comes from the alcohol. It is saying prop, so we know that the acid that was used there should be propanoic acid, right? So 2.3.2, the answer is propanoic acid. And then if the question was saying let's name the alcohol, then it was going to be pentanol. 2.3.3 says let's name or give the formula of the catalyst that is used, right? In esterification, we always use H2SO4 or sulfuric acid. Question 2, organic chemistry. We have a table there. We have 6 organic compounds. And then 2.1.1 it says write down the letters that represents the following. 2.1.1 says a ketone. So A is an acid, B is an aldehyde, C is an alkane, D it's a haloalkane, and then E is an alcohol, and then F is the ketone. Why am I saying F is the ketone? I'm saying that because of the functional group. Let me do something real quick so that I can show you what I'm talking about. So here's the functional group here. This is the functional group for ketone. So as soon as I see that, I know that I have a ketone. So that is F. We have 2.1.2. 2.1.2 says two compounds that are functional isomers. Functional isomer, a ketone is a functional isomer of an aldehyde, and then a ester is a functional isomer of a carboxylic acid, right? These are the only two functional isomers we have. So the only ketone we have is F. It has 1, 2, 3, 4, 5. It has 5. It has 5 carbons. Let's look and see if we have an aldehyde that has 5 carbons. E is not an aldehyde. D is not an aldehyde. C is not an aldehyde. B is an aldehyde, and it says pentanol. You know that it says meth, eth, prop, bute, pent, right? So it has 5 carbons. So the functional two compounds that are functional isomers is B and F. It's aldehyde and ketone. Let's move ahead. 2.1.3. 2.1.3 says write down the letter that represent a hydrocarbon. That's a alkane, an alkene, or an alkyne. For this question, the only hydrocarbon we have is number C, which has 10 carbons and 22 hydrogens. Let's move ahead. 2.2 says for compound D. Let's look at compound D. There it is there. I just put some brackets over it to highlight it. It says write down the homologous series to which it belongs. We know that it's a haloalkane, like we've already said. So we're just gonna go ahead and write that down. Why are we saying it's a haloalkene? It's a hydrocarbon that has a halogen, or in this case it has halogens because it has two bromine. There we go. That was 2.2.1. Let's move ahead to 2.2.2. 2.2.2 says write down the UPEG name of compound D. So we're going to calculate the carbons. So we have 1, 2, 3, 4, 5, 6, 7. We have these 2 here on the outside, and then 8, right? So as soon as we get 8, we know that that is going to be oct. So we have oct, and then it's a haloalkane, so it's just going to be octane. And then now we look for where the halogens are positioned. If we count from the right hand side, it's 1, 2, 3, and then if we count from the left hand side, is 1, 2, 3, 4. So the closest path to a halogen is from the right hand side. So we're going to have 3 comma, and then the other position for the other halogen. So that's 1, 2, 3, 4, 5. So it's 3 comma 5 dash dibromo octane. 3.5 dibromo octane. Yeah, there we have it. Let's move ahead. 2.3.1 says consider compound F. Compound F is a ketone. It's a ketone. Then 2.3.1 says write down the UPEC name of its positional isomer. Okay, so positional isomer, same molecular formula, but different position of the functional group. So we have 1, 2, 3, 4, 5 carbons, and then the functional group is on this second carbon from the right. If we for an element to be a ketone, the oxygen double bond should be sandwiched by carbons, right? So we cannot put an oxygen here. It becomes an aldehyde. It's no longer a ketone. But then if we come and we put it on this carbon here, then it's going to be the same name, because we'll start naming from this side, so it will still remain what it is. So we are supposed to put it in the carbon in the middle. It will have a different position of the isomer, that's different UPEC name, but it's still a ketone that has the same molecular formula. So that's how we draw it. So we no longer have these. The oxygen double bond is there, and then you can fill out the rest of the carbons. So now the name becomes 1, 2, 3, 4, 5. That is pent, right? Penten, and then 1, 2, 3. 1, 2, 3. If you count from any way, from the left or from the right, you get to the oxygen double bond after you've moved past 2 carbon. So that is penten 3 on. And then, yeah, that's it. That's how you name the positional isomer of compound F. 2.3.2 says a chain isomer of compound M, compound F. So still same molecular formula, but different structural formula. So again, let's go back to the basics. We have 1, 2, 3, 4, 5. And then we know that the oxygen double bond should be sandwiched between 2 carbons. So let's say it's still here. If you take this carbon here and then you put it here, that's virtually impossible because the carbon can only support 4 bonds. If you put it here, then you're gonna count from you're gonna start counting from this one, because it's not, there won't be anything else here. So you'll start counting from 1, 2, 3. So it will remain the same ketone. But then if you don't do that and you take this carbon here and then you put it here, you're thus going to get a different chain, a different name, but still the same molecular formula. Yeah, maybe there's another way that I'm not seeing that you can use, but as long as you play around with it, it has a different name, it still has the same molecular formula, then you're good to go. So in this instance, if this is what we are going to have, it's going to be let me see, it's going to be butane 2-on, right? So if this is 1 and we're saying this is 2, then this is 3. So we're gonna have 3-methyl butane 2-on, and then that's a chain isomer for compound F. 2.4.1 says during the reaction of compound A with compound E, compound A is an acid, right? And then compound E is alcohol. There we go. And then you know that when you mix an acid and an alcohol in the presence of an acid catalyst, you're going to get esterification. So let's see. 2.4.1 says okay, they have reacted. It says write the UPEC name of the organic compound formed. So you know that if you have an alcohol and then acid, you add the acid and then you get the ester. The naming, you start by the alcohol, right? The alcohol is in this instance, okay, 1, 2, 3, 4, 5, 6 is hexanol, right? So we have hexanol for the alcohol, and then for the acid we have methanoic acid. If you mix these two and you form an ester, this is how you write the name. You take the alcohol is hexanol, it will become hexyl when you start writing the name of the ester. And then this one says methanoic acid, it will become methanoid, methanoid. The spelling is just confusing me there for a second, but then okay, it's not really visible. Methanoid. Yeah, so that's it. That's the name of the ester. So if you had butanol, you're going to have butyl methanoid, and then for a different acid, you know what to do. So we done with 2.4.1. Okay, 2.4.2 says the structural formula of its functional group. That's the functional group of ester. So you have a double bond, and then you have an oxygen here, you have a carbon, and then it can be bonded to something there. This is the functional group. There's really no trick. There's no formula. It's just the functional group of an ester. Yeah. But if you pay attention to detail, you can see that this part will come from the alcohol, and then this part will come from the acid. But other than that, just straightforward. 2.5.1 compound C, 10 carbons, 12 hydrogens, reacts at high temperatures and pressure to form a 3-carbon alkene. 3-carbon alkene, so that's propyl. It has formed propyl, and then some alkene Q. And then the first question is write down the type of reaction that takes place. This is cracking. You can see that is this big compound, and then now it has cracked to P and Q. It's cracking, or you can even write elimination. This is also acceptable. Then 2.5.2 says molecular formula of compound Q. Okay, so we start with 10 carbons, and then we have 22 hydrogens, right? And then we have a 3-carbon alkene. So that's 3 carbons is an alkene. So this is supposed to be H of 2N, N is 3 in this instance, so that will give us 6. So what's left? 10 carbons, and then we subtract 3 carbons. We're left with 7 carbons, and then 22 hydrogens, and then we subtract 6 hydrogen. We're left with 16. So that is CnH2n plus 2. So this is so this is the question says we should write the molecular formula. So this is the molecular formula. This is the molecular formula we're looking for. And then 2.5.3 structural formula of compound P. We already know that compound P is propyl, so C. We can put the double bond here, or we can put it there. It doesn't matter. I will still have the same name. And then carbon, saturated, carbon, and then saturated. So yeah, there we have it.
Learners investigate factors that influence the boiling point of organic compounds. The boiling points of some organic compounds obtained are shown in the table below. And then 3.1 says define the term boiling point. So we know fully well that the boiling point is the temperature at which the vapor pressure is equals to the atmospheric pressure, right? So the temperature in which the vapor pressure is equals to the atmospheric pressure. But
you have to write it in full. I'm just writing it like this for the sake of time. And then 3.2 says the boiling points of compounds A, B, and C are compared. And then 3.2.1 says, how do the boiling points vary from compound A to C? So we come in here from compound A going to C. So we have minus 42, minus 0.5, and 36. Clearly, the boiling points are increasing, right? So for 3.2.1, we're going to write increases. And then we have 3.2.2, which says, explain the answer to question 3.2.1. So why are these boiling points increases? When you're coming from A to C, you will realize that A has 3 carbons, and then B has 4 carbons, and C have 5 carbons. So we can see clearly that the chain length is increasing, right? So we can say that the chain length increases. And then it doesn't end there. What is the consequence of the chain length increasing? When the chain length increases, we'll have an increase in the strength of the induced dipole forces, right? So we're going to say that the strength of induced dipole forces goes up, and then in conclusion, more energy will be required to overcome the forces. So that's exactly what you're gonna write. More energy required to overcome the forces. I'm just gonna leave it like this for the sake of time, but you have to write it in full when you sit for your exam. And then 3.3 says the boiling points of compounds B, C, and D are compared. Is this a fair comparison? So let's go look at B. Here's B, which is butane, C, which is pentane, and D, which is methyl butane. And then, is this a fair comparison? If we look at the molar mass of B, is 58. The molar mass of C is 72, and the molar mass of D is 72. So no, I don't think this is a fair comparison. And then obviously they're gonna ask us why, because compound B has a different molar mass, right? Has a different molar mass, because when we investigating, when we are doing these experiments in chemistry, we are only supposed to be changing the independent variable, right? We're not supposed to change the control, which we need the molecular mass to be. So if we were comparing only C and D, then that would be fine because they have the same molecular mass. Or if we were comparing A and F, but then as for B, it has a different molar mass, so it's not a fair comparison. So we have 3.4, which says the boiling points of compounds E and F are compared. So let's just erase this and look at E and F. So here's E, which is ethanol, and F, which is ethanol. And then 3.4.1 says state the independent variable for this comparison. So the dependent is what we're looking for, right? In this instance, it will be the boiling point. And now the control is what's kept the same, which is the molecular mass, right? We have 46 and 44. They're not really kept the same, but then they're pretty much close to each other. And then what we are changing here is the functional group, right? You can see that here we have ethanol, and here we have ethanol, alcohol, and an aldehyde. So the independent variable we can say is the functional group. You can even say is the homologous series, and it will still be fine. And then this is 3.4.1, my bad. And now we have 3.4.2, which says write down the name of the strongest van der Waals force present in compound F. So in compound F, the strongest is dipole forces. This question is more of content knowledge than solving any problem. And then 3.5 says which compound D or E has a higher vapor pressure. So the higher the VP, the lower the BP. BP being the boiling point, right? So compound D, which is methyl butane, has a boiling point of 28, and then compound E has a boiling point of 78. So the higher the VP, the lower the BP. Compound D has a lower boiling point compared to compound E, so we're gonna say D has the higher vapor pressure. As a consequence, they say give a reason. So the reason is what we just talked about. The higher the vapor pressure, the lower the boiling point. Clearly, methyl butane has a lower boiling point. As a result, it has a higher vapor pressure. If a compound has a higher vapor pressure, what does that say about the boiling point? What does that say about the melting point? Before we do that, let's do 3.1, which says let's define the term melting point. So melting point is the temperature at which the solid and liquid phase are at equilibrium. The temperature at which the solid and the liquid phase are at equilibrium. And then now 3.2 says which one of C or D has the higher vapor pressure? Give a reason for your answer. So here we are given compounds and their melting point. So for you to be able to answer this question, you need to know the relationship between vapor pressure and melting point. So what is the relationship between the two? We know fully well that the higher the vapor pressure, the lower the boiling point. The same is true for melting point. The higher the vapor pressure, the lower the melting point. So between C or D, the one with the lower melting point has the higher pressure based on this relationship we're proposing. So which one between C or D has a lower melting point? It's clear to see that C has a lower melting point, right? At minus 16 degrees Celsius versus D, which has a melting point of 16.7. So our answer for 3.2, we would say C. And then why are we saying C? We are saying C because it has a lower melting point. We know fully well that the higher the vapor pressure, the lower the melting point. 3.3.1 says let's define the term structural isomer. So structural isomers are organic compounds that have the same molecular formula but different structural formula. The same molecular formula but different structural formula. Right? And then 3.3.2 says explain why B has a higher melting point than A. Refer to structure, intermolecular forces, and energy in your explanation. So A and B are structural isomers. They have the same molecular formula but different structural formula. So let's look at A. A is clearly branched, right? It says 2-methylhexane. So on the second carbon, we're supposed to have a branch. And then B just says heptane. So B is a straight alkane. That is the only difference between the two. And we're going to use that
to explain our answer. So we are already told that B has a higher melting point. If B has a higher melting point, we will know consequently that it has a lower vapor pressure, right? Because the higher the vapor pressure, the lower the melting point. So here we have higher melting point, so we need lower vapor pressure. But why does it have lower vapor pressure but A doesn't have? So the difference between A and B is that B is less branched, right? As we are proposing, B is a straight alkane while A is a branched alkane. But then if it's less branched, then what will that mean? That will mean that we have stronger intermolecular forces. So we have strong IMF. Right, and then stronger intermolecular forces will mean that we need more energy to break bonds in compound B, right? So more energy required to overcome IMF. Just to recap, we are comparing A and B. B has a higher melting point, so we know that it has lower vapor pressure. If it has lower vapor pressure, it has stronger IMF, and if it has stronger IMF, then it requires more energy to overcome the intermolecular forces, right? But then what's the difference between A and B? The only difference between A and B is that B is less branched. So this tells us that if you have two structural isomers, the one that is less branched will always have a higher melting point versus the one that is more branched. Now let's do 3.4. 3.4 says let's explain the difference in the boiling points of C and D, referring to the intermolecular forces and the energy in our explanations, right?
Let's go back to the basics real quick here. So we know that compound C, right, is an alcohol, and then compound D is an acid, right? So because compound C and compound D we have an alcohol and an acid, we know fully well that they both possess hydrogen bonding, right? We know that they both have hydrogen bonding, right? So we can say that they both have hydrogen bonding. But then if they both have hydrogen bonding, then why do they have different melting points and consequently different boiling points? That is because compound D, right, which is our acid, has two sides of hydrogen bonding versus compound C that has only one side of hydrogen bonding. Now the question you're asking yourself might be, wait a minute, what are we talking about? Why are you saying compound D has two sides of hydrogen bonding? That is because acids can go under a process called dimerization, right? And then alcohols cannot. So we say that compound D has two sides of hydrogen bonding, right? If it has two sides of hydrogen bonding, then what does it mean? It means our compound D has stronger intermolecular forces, right? And then what do we know about compounds that have stronger intermolecular forces? They require more energy. They require more energy to overcome the intermolecular forces. And if it requires more energy to overcome the intermolecular forces, then the boiling point of compound D, right, will be greater than that of compound C.
But1 an unsaturated hydrocarbon, and compound X, a saturated hydrocarbon, reacts with bromine as represented by the incomplete equations below. 4.1.1 give a reason why but1 is classified unsaturated. It is classified unsaturated because it has double bonds, right? If an organic compound has double bonds or triple bonds, then it is unsaturated, right? It can still go under addition reaction. So 4.1.1 it contains a double bond. So it contains
a double bond. Now let's move to 4.1.2, which says that what type of reaction, addition or substitution, takes place in the following. Reaction 1. Reaction 1, we have but1 plus bromine, right? Because this organic compound here is unsaturated, it can only go under addition reaction, right? And then now we can move to reaction number 2. Reaction number 2, we have X, which is said to be a saturated hydrocarbon, right? So it's an alkane, and then we are adding bromine. So an alkane can only go elimination or substitution, right? But then we're already told here that we have to choose between addition or substitution, right? So clearly our answer here will be substitution. So for B, we have substitution. 4.1.3, write down the reaction condition necessary for reaction 2 to take place. For reaction 2 to take place, we need heat, or we need sunlight, but from sunlight we're still looking for heat from the sunlight, right? Or we need UV light. And then 4.1.4 says write down the UPEC name of reactant X, right? Reactant X is a hydrocarbon, and when we substitute bromine, we get 2-bromobutane, right? It should be quite clear that the UPEC name of reactant X will be butane, right? A hydrocarbon. And then 4.1.5, write down the name or formula of product Y. Okay, so again, when we have a chemical equation, whatever that is on the left must be present in the right, right? It needs to be balanced. So we have butane, right? And then we add in bromine, and then we get 2-bromobutane. So in place of a hydrogen in butane, right, a hydrogen is replaced with bromine, right? And in place of bromine here, we're replacing it with the hydrogen. So Y will be hydrogen and bromine, right? So what is the it is the name of the formula of product Y. So let's not complicate our lives and try coming up with the name. Let's just say HBr, hydrogen bromide. 4.2 says 2-chlorobutane can either undergo elimination or substitution in the presence of a strong base such as sodium hydroxide. 4.2.1, which reaction will preferably take place when 2-chlorobutane is heated in the presence of concentrated sodium hydroxide in ethanol? Write down only substitution or elimination. So if you pay attention, you will realize that concentrated is in bold, right? So that should give us an idea of the knowledge we're supposed to apply. So what is the knowledge that we're supposed to apply? If the base is dilute, we go under substitution. If the base is concentrated, we go under elimination. So since here we are told that the base is concentrated, we are going to go under elimination. If it was dilute, we're going to go under substitution. And then 4.2.2 says write down the UPEC name of the major compound formed in 4.2.1. So we had 2-chlorobutane, right? And it is going under elimination. So when it goes under elimination, we are going to lose the chloro, right? And we're going to be left with but2. So 4.2.2, we have but2. And then 4.2.3 says use the structural formulae to write down a balanced equation for the reaction that takes place when 2-chlorobutane reacts with a dilute sodium hydroxide solution. Now we're using a dilute base, right? And I've said that if we use a dilute base, we go under substitution, and if you use a concentrated base, we go under elimination. So let's write a structural formula for the substitution reaction that would take place. I will start by writing the structural formula of 2-chlorobutane, right? So we have 4 carbons, 1, 2, 3, and 4. And then on the second carbon, we have chloro. So let's have our Cl there. And everywhere else, we just have hydrogens, right? So let me just fill them in real quick, and then we move to the next step. So we're saying that we're using dilute sodium hydroxide solution, right? So let's have plus NaOH, right? And this is going to give us, now the substitution happens, right? How does it happen? This OH here is going to replace the halogen Cl, right? So if that happens, we're going to get 4 carbons again, and then in place of the Cl, we have OH, right? Instead of a haloalkane, we now have an alcohol, right? And then we have a hydrogen, and then there goes another hydrogen. And then plus, we know that in a chemical reaction, whatever you have on the left, you should have on the right, right? So we're going to have NaCl.